here, and then we get like, uh, what is it? Improving.
Do you know if we have a remote speaker?
I'm not sure. I'm not sure. I'm gonna just follow the series. So I mean,
Writing my slides for this. So who wants to be the MC?
what? Uploaded the slides, and
Yep.
he asked it, he checked it, and it's there. Just click plus
here,
here.
and it should have
First one is improving.
improving.
Yeah, that's it. That's
So
the
all you
first.
do, you know how to switch, right? You just go and
Just
select
just
it.
click there, and that's it.
Yep. So all you need to do is thank our sponsors,
Yeah.
mention the code of conduct, and you do the slides by doing that. These little buttons.
This is just at the beginning. Yes?
Just the beginning.
Yeah.
Don't spend more than 1 minute on that. Just so thank
Yeah.
your sponsors. Boom.
Thank your sponsors. Please follow the code of conduct. That's it. Yeah. Okay.
Did I switch with Matthew?
Oh, shoot. Should we, I guess we didn't officially do that. I was going to, but I've been so effing busy. I didn't switch. But we could switch it still.
Switch what?
So Matthew didn't know it because he was giving. Wait.
No, he said that he will not be here at the beginning.
Right. So because that was he originally at the beginning or no? No.
He said he had a conflict at the
Yes.
Yes.
Oh, at the end he had a conflict. Where does it go?
end. So I'm flexible.
So we'll whenever it does we'll do it, and if someone comes in.
What I understood was that he's resolved the conflict, so he will not
did you
need
okay.
to be, he'll not be here at the
Let me
beginning of
use-
the event.
I'm going to have to use the restaurant right now. So.
Yeah, go ahead.
I'll let you do it.
Yeah. Thanks to the sponsors. Please follow the code of conduct, and here.
Usually I list this one, like to mention it. I always do a call out for Linux Foundation because Linux Foundation, Linux Foundation is not a sponsor.
Yeah.
Because we actually pay them. I know that they helped. I always do
Right.
thank you.
Okay.
things. Oh, so it's right behind this. At the top. I am not noise.
Good morning. Thanks for coming to the combined Perf events and tracing micro conference. This is the first time I tried to organize to run such a conference, so it's everything new to me. But we want to thank our sponsors, the list of those, and to the Linux Foundation. As usual, let's all follow the code of conduct, and without much delay, I am Rogers talking about improvements to the Perf event subsystem.
Okay, so good morning. I'll stand at the microphone. It's nice to see a lot of faces I recognize. I'm Ian Rogers. I work for Google. I write lots of patches. And I'm going to talk about improving perf events, the perf event subsystem after 15 years. When I come to these conferences, I kind of like see a lot of people talking about active development and things which are going into the tree at this moment in time. We've got all these wonderful people. I wanted to do something which is kind of forward-looking and talk about the problems that we have in the subsystem and what can we do and improve. And so these are my opinions. I want other people to contribute and tell us what we can be doing better and so on. And why am I even vaguely qualified to do things? So I started working like 26 years ago on Linux things. We were working on binary translators. The best known of which was Rosetta. But long before Rosetta, we were doing many obscure binary translators. And to do profiling on Linux in those days, we had access to performance counters because we had Pentium MMX machines and so on. But the only thing you could do is do system-wide profiling. So you'd use tools like Rabbit to program the performance counters. You'd go to init level 1 so that you didn't get lots of other noise affecting your profiling. And this was frustrating because as poor students, we only had one development machine. So when you were doing benchmarking, you couldn't read your email. So from that, we did a master's project, and this became OProfile. So this was John Levon's work that John was thoroughly responsible for. I was in no way, shape, or form, but that's where OProfile came from. So that was 26 years ago. We've got Pentium MMXs, we've got Pentium Pros. And 15 years ago, the perf event subsystem came about. And so OProfile was seeing less and less maintenance. It also wasn't deeply integrated into the kernel, so it was loaded as a module. There were a lot of similarities between what OProfile could do and what perf events could do, but over time, the perf event subsystem has taken over from that. And when this was happening, the machines of the day were, we'd gone from Pentium Pros to Core 2 Duos and Athlon 2s. So we've got multi-core systems, but it's still looking like SMP. It's not that radical. Something interesting, in my opinion, happened 8 years ago. The nice thing is that Intel did this work, and they actually wrote it up in their device driver. So go into the kernel tree, go and look at i915 perf.c, and you'll see various explanations of why the perf event subsystem was not used for the i915 GPU. Now, they have some events in there, but the summary is that when you're doing things on GPUs, being able to do things like objdump it's not that useful. So what are they really getting out of the Perf tool? And then the Perf tool is oriented around threads and CPUs and virtual addresses, and these things didn't translate well onto the GPU. So it was a lot of churn for everybody, so they decided to do their own thing, do their own separate subsystem for doing performance events. The standard way to do this is to do everything through I/O control. So 8 years ago, the machines of the day, we're starting to see heterogeneous systems. So what Intel likes to call hybrid, ARM likes to call big little. And we're also starting to see ever more accelerators. So I work for Google, so we've got TPUs down there as well. So forward-looking, what needs fixing? I would say that more and more of your interest in compute isn't on your CPU. I gave a talk last year about top-down profiling, and everybody's familiar with that problem that they have to work out why their machine is running slow, and so they run Task Manager, they run Top, they run Perf Top, they run all of these things, but that's not where your interest in compute is these days. And how are we showing you where that interest in compute is? The vendors have solved this problem. The problem is that they're all solving this problem. So we have one API, we have CUDA, we have ROCm. We have many different open standards, none of which are properly integrated into the Linux kernel. For uncore events, I already mentioned that they're interested in things like DRM job IDs. They're not necessarily interested in threads and CPUs. And topologies have become much more complicated than they were in the past. We have things like L3 caches, chiplets, and so on. So there's a need for the subsystem to keep up with these things. So in the Perf tool, can we meet the APIs where they are at the moment? Because trying to change everybody overnight, it's going to be a long process. I sent these patches out 2 weeks ago. Arnoldo's already picked up a few of them, which is great. And what this is showing is it's showing HWMon kind of things alongside regular Perf events. So at the bottom, we've got some Perf events which are being used to compute a metric, which is the uncore frequency of the machine. But then above that, we've got kind of like the CPU temperature and the fan speeds, which are all coming from HWMon. And in the same way as we're able to add a HWMon PMU into the Perf tool, we can also add additional PMUs for things like GPUs and so on. So that's something which is going on. A different problem is on scalability. So when you're doing system-wide profiling, samples in the Perf tool come in with a virtual address. BPF for a long while has been using build ID plus offset as another way of doing this. So when you have a virtual address, you want to know where the file and offset so that you can turn that into a line of code where you're seeing performance issues. And so the way the Perf tool does this, it takes a virtual address, but it also has memory map events which describe the layout of memory. Build ID offset avoids this because the build ID identifies the file, and the offset is the offset within the file. Now, the problem with this is that build ID offset is much larger than a virtual address. It's 4 times the size, or 24 bytes larger. And these mmap events are only, if we take off the file name, which Jerry didn't do, but if we did, then we can get them down to 72 bytes. So it looks on the face of it that build ID offset doesn't really win as much inside the Perf tool because if we switch to sampling that way, we're going to have much larger sample addresses for everything, and file sizes are going to go up, which is bad. But I'm still quite keen on it as a mechanism. One of the proposals that I have is that we can open an event in build ID offset mode. We can open an event in virtual address mode. We don't need to synthesize all of the memory layout for the full system. When we start seeing that we're getting samples in the build ID offset way of doing things, then we can transition over to using virtual addresses. But before we transition over to doing virtual addresses, we have to synthesize the memory layout for the processes where we're getting virtual address samples. So again, it's a problem that we see when we have heavily consolidated servers, and I know that there's been various other proposals on how to deal with this. So other things which, areas for improvement, I think BPF and Perf events have kind of like diverged, and we try to pull them together. I think the build ID offset shows how we can try and share infrastructure within the kernel for things like stack trace mechanisms. The build IDs require access to the page cache. There's an overlap with the S-frame stuff. We're seeing issues around context switch performance. So you're starting to see hundreds, if not thousands, of uncore events. They tend to all move on to CPU 0, regardless of what we try to do with the tool. And so context switching on CPU 0 is becoming increasingly expensive. The PMU abstractions within the kernel, people just tend to kind of pick up somebody else's driver and then kind of copy it and change it so it matches their system. So we see things on ARM. Hot plug support just isn't there at all. These things like the use of the EF flag is kind of like, it depends who's cargo culted from who. So there are challenges with inside the kernel abstraction. The I915 guys were pointing out that they were not reference counting the PMU from the perf event, and so they were adding to the API for that. There are long-standing points of pain. One that gets forgotten about, but I have a background in doing just-in-time compilers, is that the way that memory map events are represented is the length and address that you get from a memory map event in the perf tool. It comes from the VMA. It's not actually what the user requested. So this leads to confusion when you put two M maps next to each other because the VMA gets extended. And we do various tricks in the tool to try and make this look like your jittered code is behaving like an ELF binary. It would be nice not to be doing this and have a fuller representation of what's going on. Precise events work well on Intel, don't work well on anything else. It's getting better. It's a work in progress. But even within that, we have things like capabilities files saying what the maximum precision is. Everybody else says 0, and Intel says 3. It would be nice to be able to get richer information. We've been adding, Nam Young's done work on lock contention analysis within the kernel, but we're lacking information on, say, on who's holding the lock. We know where the contention is. We don't know who's holding the lock when that contention happens. So some themes for kind of like the accelerator work, some of the things that are missing, bulk APIs. So the ability to open multiple events at once. We kind of need this for the Intel top-down support, the top-down metric events. They're a complete mess in Intel, and they cause us no end of grief in the perf tool. They have special requirements that the first event has to be slots, and they have to be groups, and this, that, and the other. And it comes about because of the way the system call is implemented. Accelerators tend to be asynchronous. You batch up all of the update information that you have. And so one of the problems that I915 describes is that when they DMA over all of their events, then they end up getting throttled because all of a sudden the driver is seeing a lot of events coming all at once. And the subsystem is assuming that you're running on the CPU. And then we need to be able to identify things like DRM jobs and have different ways of describing memory and so on. There's lots of other things going on. Maybe Mingwei's heard and other people who've been working on the pass-through PMU stuff for guest operating systems. But this is enabling kind of guest operating systems to have full access to performance events on systems. But this causes lots of challenges. So we tended in the perf tool to say, hey, we should exclude sampling on guests. That's good for this because it means that the guest operating systems can have full control over the MSRs and so on that control the performance events. But if we get rid of this exclude guest OS flag, which is good for PMUs like AMD IBS, then we're forever doing a dance. And whenever we change a default, people shout at us. Or at me. There's kind of what should we be doing in the tool to evolve it. And then one of the things we face is licensing challenges. A lot of people want to be able to use the thing that the Perf tool is doing, but they don't necessarily want to invoke the Perf tool every time, and they want to use it as a library. libbpf has kind of a permissive license. It's using BSD2 and LGPL. But the Perf tool code all comes in as GPL, and this creates a problem with sharing. So in summary, it's 26 years. Things have changed a lot. We need to update the system. There's a lot of challenges with heterogeneous and systems and complex topologies. Thanks to everybody who's contributing in this area. I shouldn't take credit for things, and so on. And I was asked to put this slide in saying that we're hiring. So if you have interest in working in this area, then Google is on the lookout. Okay, that's everything.
Can I just check a couple of things you mentioned with uncore PMUs, the problem with CPU zero and context switching?
Mm-hmm.
Are you talking about, are you actually talking about context switching? Because obviously they don't have a task context. So are they just slowing that down due to like false contention on some shared locking, or is that just?
So it's funny because when you're doing uncore profiling, you're talking about things like L3 cache, which is shared by multiple CPUs. We do support C group context switching on system-wide events, so Google uses this. And if you're doing that, it becomes slow because of the number of write MSRs and so on.
Okay, I didn't realize we supported C group switching on those events that were CPU bound.
I probably like 5 years ago rewrote and optimized that to some extent. It's
Yeah, there was some bug during the rewriting the context management code during around 6.2 kernels, and it rewrites the way we manage the PMU context, but it misses to filter out non-C group events when you context switch. But so it needs to talk to the encore PMU unnecessary, but it was fixed recently.
yeah. There's improvements, but still, like there are newer machines with hundreds of memory controllers, and if you have hundreds of memory controllers, you have more than that events on those memory controllers, and just that number of events and the need to do write MSRs is becoming a performance problem because it all lands on CPU 0 on Intel.
If you can repeat the part on guest OSs, I didn't quite catch if your desired state of things is for the guest to have visibility into the perf events, or you consider that something undesirable?
Yeah, so it's not my work. There's people like Mingwei in the corner and people like that who've been doing this work. But what it is that previously, if you had an event in a guest OS, then the KVM and so on would try and map that to a perf event in the host OS. So there was this mapping between MSRs and perf events. That was a pain. And so what happens now is the guest OS directly writes through to the MSRs in the host OS, if it can. Some of you intercept some of the things to say what events can be programmed, but after they're programmed, you can directly read the counters and things like that.
Yes.
I survived.
And thanks to Ian for the presentation. And now to Namyoung about using type info in the perf tools.
Hello. I got 3 more minutes. And
Get 3 more extra minutes. Start now.
okay. Okay, thank you for coming to my talk. My name is Namyoung. I'm going to talk about the data type profiling and current progress and future plans and ideas and how we want to make better use of this type information. So quick status updates. Since last LPC, we have merged the full features I initially proposed for the data type profiling. And 6.10 is the first edition that has the data type profiling support, but I strongly encourage you to use the latest version, which will be 6.12, since it has much more improvements and some bug fixes. So I'm not go through the details about the data type, how to use this information and how to do data type profiling, but essentially it's just adding a new sort keys to the perf report. So by using just this type sort key with -s option, you can use data type profiling, given that you already recoded the profile with correct event information. So essentially, type is to list the name of the data type you accesses, and type of is type name plus offset, which is the name of the field inside the type. And perf annotate, I added the -- data type option to list all the fields in the data type with access profile information. So this is just basic way of using the data type access profiling. But we want to improve the perf tools to use this information more useful way. So one obvious place to add is perf mem command, which deals with the memory access information. So I added -T option to enable type information, but it's just short for the using the mentioned sort keys like type and data source and snoop and TLB access like that. So it will enable type level memory access profile. So in this example, you can see we have 4 types, but first one is unknown, which means you don't have enough DWARF information, or the function or that instruction doesn't have enough full information to analyze data type from that instruction. Second one is stack operation, which means it's a push or pop instruction to put your data into the stack and get from the stack. And the next one is the actual data. And I focused on the data task struct, and it got 78 samples. And in this hierarchy mode, you expand to a next level of access, and then it will show the 7 of them is from the RAM, and 48 is from L1 cache, and so on and so on. So I think this kind of information is the hierarchy mode is much more useful than the regular flat report mode. And next one is perf C2C command, which is focused on cache line level access analysis, with focus on the hit modified status, especially for remote node, for catching force sharing. It has various output field and sort keys. I think the output is too verbose, but anyway, it's useful for sometimes, and it shows the memory load and store information together. So I added type CLN, which is short for the type cache line, as a new sort key, which will aggregate the access in a data in a cache line together, which means offset 0 from 63 will go to the cache line 0, and offset offset 64 to 127 will go to the cache line 1, and so on. So this will make the cache line level memory access profile more concise and easy to read. So I plan to do it with Perf C2C, but I actually don't have a concrete plan how to integrate it into the Perf C2C level, but yeah, that will be my future work. But this is the general sort key, so you can use it to the perf mem or even just regular perf reports as well. So thinking about the use case of the data type profiling, I think essentially we want to help developers to optimize their data structure layouts, which means we need to put related data structure in the same cache line to make better use of the cache lines. So you need to figure out which fields in a data type is related and accessed together. But sometimes it may not be intuitive from the source code. But with this information, we can help to figure out which data fields are related and needs to be put together. So I talked with Arnaldo about this topic, and he suggested to analyze the example with the basic block it belongs to. Then it will give another memory access in the same block, and we will have a sample, and it tells you which data fields in this block is accessed together. Then it will help you to optimize your data structures to put these fields information. And another thing is about the temporal locality information. So we may want to know if this field is accessed and how long it will be accessed again. And this kind of information is sometimes useful. We don't have a good way to visualize this information in the Perf tool, but maybe we can add a new output mode to like time chart style output to show the field level accesses with the sample timestamp information.
Sorry, what field level?
Field means in the member of your data structure. Okay.
Hello? Yes, in your previous slide, you suggested a visualization that you were calling field level time chart. Can you...
Yeah, I need to clarify the terms. So here, time means your data structure, like a task struct or struct, things like that. And field means the member of that type, like a task struct has p, t, or things like that. That is the field I mentioned. Yeah. And thinking about further, if we have this information, maybe we can hint other tools to do the actual better layout. Maybe we can add support to the Perf tool itself to suggest some layout changes, or we can use PA hole. As far as I know, PA hole already suggests something to pack your data structure to remove some paddings inside the struct. But with this information, maybe it can suggest this and this field is accessed together. So you need you better put them together in a cache line, or we can maybe hint compiler to generate code to change the layout if we have the freedom to do that. Like we have a randomized data structure option in the kernel. Maybe something like that with the data type information, you can suggest that changes.
So in the kernel, you have already ways for you to say that some fields are related, like adding compiler attributes like cache line align on SMP. So some of this work was done already for lots of data structures. For networking, people did more recently like cache line groups. You group together, and then there is some validation. And overhaul has a reorganization algorithm that tries back together, but it's naive because it moves just based on alignment holes and moves things together. But then you don't get the cache effects that we are wanting. So with this information that gets from what we have in data type profiling, plus the extra work that we have been discussing about finding related fields, we can feed this to overhaul and then improve its reorganization algorithm so that it takes this into account, takes the compiler groups that the networking people did into account, takes the alignment that this is there as well, and tries to reorganize things. And then you can produce a compilable new definition for the structure, and rebuild, and then profile again. So that would be like data type profiling based optimization, like similar to PGO, so kind of like that. That's the idea that I have been discussing.
Yeah, thank you. So besides that, we have some issues with this, with using data type profiling. First one is availability of the DWARF debug information. Sometimes we might not have full debug information because the binary size is too big. We have a lot, have a big static linked binary, and in this case, it's not possible for some resource reasons. Not possible to have the full dwarf information. In that case, how can we deal with that? My idea is, in that case, they might have line number information and list. Then we recode that line number information for later, and then ask compiler to give some type information in that line or something.
It's very easy to have multiple dereference, up to 10 or something in a single line of code. I don't think this is granular enough. Better compiler tools like the LVM debug info for profiling. I think that really is the way to go. I mean, if you know you want to do this, build with a toolchain that supports it. It's really that simple.
Yeah, I'm not sure we can do that, but just with the line number information. Maybe we need some more information like a column number or some discriminator or something, but I'm not sure, yeah. So another option is to use BTF for the kernels. So BTF is more available than DWARF. You can probably use BTF to get some type of information. And another way is maybe rather than creating DWARF information in the binary stuff, maybe we can have another option to dump all the type information for each instruction during the compilation. I'm not sure it's possible, but that will be another option. Or Perf tools can generate type information regardless of samples, and then we can save it to a file and then later we import that file to match samples with type information.
So I think that currently BTF is also based on the DWARF, so that anyway, yeah, user will have the DWARF information, DWARF file, or something like that, so that you can use that anyway, isn't it?
I will talk about the BTF in the next slide, so
Okay.
I can talk about that.
So I'm from compiler group. So we can use something called discriminators to differentiate line in addition to line numbers. So we use a lot in the AutoFDU.
So do you think it's possible to recode line number plus discriminator and later ask compiler to type its access?
Discriminator is like a 32-bit integer. You can have your encodings.
Yes.
But we are considering expand this to a larger group.
But I'm not sure if the current line number table has discriminator. For
DWARF have this.
Okay.
Yeah.
Thanks. Oh. Okay, so yeah, that's the one issue, and another one is the quality of the DWARF debug information. I found sometimes it lacks location expression at all, but sometimes it doesn't match the instruction with the actual location expression. It's like general problem with the DWARF quality, but the more important problem is that DWARF only generates the variables. Debug information for variables. So if you have an access without variable, so DWARF doesn't generate anything. Fortunately, LLVM recently has an option. I don't think it's added recently, but they had a feature to generate more debug information without explicit variables in that case. Yeah, some pseudo kind of variables. And with all that, sometimes it needs to go the instruction tracking, I call it, to figure out the actual data type because of the issues in the DWARF quality of the location expressions. I tried my best to figure out the correct data type, but it might have some bugs, so I encourage you to test and report anything you find something weird. And yeah, that's it. And oops. Yeah, regarding the BTF, as mentioned, the BTF is generated from DWARF, so it has basically similar information than DWARF. But basically, BTF, as far as I know, doesn't have location expression, so you cannot simply match this location to a variable or something. So you need to go to the instruction tracking, starting with the initial type information and pass it to locations as instruction goes. So BTF, we have a function parameter information and per CPU variables. Function parameters are usually located by the calling conventions, but I remember yesterday's talk, some compiler optimization unfortunately put it in a different way, so sometimes it misses, but I guess that's the rare cases. But anyway, we can start with the function parameter by the calling conventions. And another showed me there's a patch to support global variables in BTF. Oh, that's good. Thank you. Yeah, that would be helpful to figure out time information. But still, we don't have local variables and location expressions. But yeah, it's still limited. But I think it's.
But that was an idea that we discussed on LSFMM, I think, about memory that comes from slab cache that we could somehow try to identify. Did you do some work on that?
Yeah. Last meal, I suggested that, but it's a different use case. It's for the log contention.
Sure.
Yeah. And the slab cache doesn't have type information. It just shows the name of the slab cache. It doesn't match to the actual types. So.
There's ongoing work by Case Cook that eventually slab might have type information, but not yet, but we might get there.
Oh, you will add the type information to the slab caches?
Yeah, but it means like a rewrite of all kmalloc call sites, hopefully with some automatic script to the new format that passes the type to it.
Okay, cool. Yeah. Will I add the BTF type ID or something there?
No, it's from type in whatever the thing you have in the.
Oh, okay. I'll take a look later. Thank you. Question. Oh.
So on this slide, there are a few things, right? So you run into cases where, say, dwarf does not have location expression. So maybe we treat that as a bug, right? But coming to no local variable support, so is the overall intention to go more towards dwarf, or maybe we figure out we figure out a way to get dwarf more crisp. But the other way of going forward is getting this information into BTF. So which one are we picking? Are we picking the way where we put more of this information into BTF? So no local variable support, and the cases where you say you need location.
Yeah.
Is the intention to bring this into BTF?
No, I don't think so. But I don't know. Yeah, it's nice to have, but I'm not sure they will allow. It will bloat the BTF size a lot, I think.
Yes. Because I think if you look at the cases why dwarf is bloated, it is because of these cases of location information, call sites, recover the original value of arguments at each point in the program. So if we are getting there, I think maybe we sort of take a step back and see which is the best format to support the use cases here.
Okay, thank you.
It almost sounds like we need a dwarf light. Seriously. Yeah.
The reason for BTF is to be compact, to be always available. So, but then people want the per CPU variables, and then it entered there. So all the things that are coming, not from dwarf, but coming from all the parts of the all the source of information. So, but there are other ways of using dwarf without having to install the whole big thing. You have debug info servers. You can ask for just that specific object file. So we are trying to explore these kinds of things in tooling and GDB and Perf, etc. So instead of requiring users to install this big debug info package, we can automatically try to bring those to the local cache and things. So it's a combination of things. BTF is always available, so we should first try to use it for like function signatures, the types for global variables, for per CPU variables, for what it's there. And then the tool could say, oh, but if you want more, then enable the debug info server, or install or use a binary with dwarf information. So you use what's available.
By the way, BTF is not always there because it could be turned off. I turn it off all the time because it's bloated. It takes the compiler. It does do a lot of work. It makes the compiler go longer. So no, I do actually turn it off. And there's on system. Then you have systems that are like memory constrained where it is actually light. And I'm a little bit worried about adding more to BTF because it is getting big. But maybe BTF needs to have basically options.
So So yeah, I mean the idea is, for instance, for BTF is for extra information to be on a separate module. Like let's say instead of you have the base thing and you have something that extra that you would load, and then you're going to get this information. It doesn't have to use kernel memory. You could use just it from the file system. There are ideas in that direction. And for building the kernel, there was talks here about not using p-hole to convert from DWARF but for the compiler to generate the VM Linux, the BTF information directly, so it speeds up. So all those things are being discussed in several different forums, different groups, trying to get the best of this and remove the bad parts about having a DWARF generator as an intermediate step. So yeah.
So this is a good reason why we have kernel developers at GNU Caldrum. So we need to go back to GNU Caldrum. More of you guys need to go to GNU Caldrum, and also we need to start interacting more with the.
And I think with this, the time is over for.
Yep. Yeah, that's my last slide. Thank you.
Thanks. And now we're gonna have Masami Hiramatsu with where probes go.
Okay.
Okay. Yep. Thank you. Okay.
It was great. It was great. Nice discussion.
So this one is actually that are not only the presentation, but also something like discussion or brainstorming or something like that. Yeah, last year we have our doing that similar thing. Let's say that for function graph tracer. So that our function graph tracer can, what we can do with the function graph tracer. And actually that now we have our, yeah, last time we have some ideas about that, like function graph tracer with our function parameters, function return address, or let's say that something like that. And now we get our let's say that patch series from Sven and also Don Lin about that ideas. So that I would like to doing this, do similar things on the K-probes. Not only not only the K-probes, but also the kernel probes. So, but before that, I need to explain that what the probes we have now. So in the kernel we have some probes, especially let's say that the K probes and the U probes are very let's say that are famous, but we have another type of the probes. Let's say that we have three types of probes. One is breakpoint probes, and another one is wrapper probes. And that is something like a function or function graph tracer wrapper probe. And also we have probes in only in the trace FS. So that are like E probes and T probes are only in the let's say that the trace FS. Okay. At first, I would like to explain that what the K probes and the U probes and how it runs. So that are K probes and the U probes both using that software breakpoint. So that it put that some software breakpoint instruction in our kernel code or user space code, and that will hit that code let's say that the kernel software breakpoint handler and call the user's K probes or U probes, which depends on the where the software breakpoint hit. Yeah, and these probes are already used by your eProbes, eBPF, ftrace, and Perf. So those can be used. And actually, there is some tool like a Perf probe can use analyze the user space and the kernel dwarf and find that which line of the code and also which local variable or function parameter can be traced or something like that. And we have some KRET probes and URET probes, so that you can also prove that some function return in the kernel or in the user space. So that's those are the K probes. And then new probes, F probe. This one is actually similar to the K probes, but only for the kernel function entry and exit. So that so this one is originally for boosting up the registration of the probes. Usually, I used to the K probes or U probes. Only the K probes. Actually, the K probes registration take a time, so that some the maintainer she asked me to speed up the registration. So I replied that that couldn't do that, because we need to wait for some RCU synchronization or something like that for the K probes the registration and unregistration. Instead of that, we can use our ftrace, because that ftrace, well, we can specify that there are multiple addresses to probe. Yeah. So that this one is has been made. This one, so that F probe is only for the function entry and exit, because that this one is originally for the eBPF. eBPF usually only probe function entry and exit. So that is okay. So anyway, so that this one just called when F trace hit the function entry, and that will call back that F probe. And we have our E probes and T probes. These are the different, bit different, but actually this one is only for the F trace currently. The E probes we can put that E probe on the some trace event, so that there are more than hundreds of the trace events in the kernel, defined in the kernel. But some are E probes, some events pass that some are kernel pointers or data pointers or something like that, and we don't. The user sometimes need to refer the internal of that, or change that. Wanna change the expression of the data type or something like that, so that our eProbes will get when the trace events hit. eProbes will get that information and convert the information and show that. And T-probes is very similar to the eProbes, but it actually hit the trace event is based on the trace point, and T-probes is for the trace point. Yeah, trace point actually usually get some data structure. And it trace event convert the data structure field, so that are the members, and to the the event parameters. So that are several event parameters. But of course, it will not cover that all the field. So that some field, only some field will be recorded. But so the user will wanna try to get more information from that data structure. In that case, you can use the T-probes. And T-probes, with the T-probes, you can get the data structure address and save that dereference that the data structure pointer and get the field. And you can get the field value. Yeah. So those three types of the probes we have. And now we have another features for the F-trace, F-probes and K-probes. Not U-probes yet. Yeah, F-trace features, one is the BTF support. So that from the F-trace, K-probes, you can use that something like data structure name and data structure field name and something like that. So that for example, this example shows that BFS open the function. There is a pass. Pass. The kernel parameter, and it is actually that function pass data structure pointer. So that you need to default that to get the D entry field, and also the default to to get the DI name, which actually that pass name. So that it's getting that the name and store as a string. So something like that, so that you can get those the file name or file flags or something like that. Save it. This can be used from the K-probes and the F-probes, and also T-probes. Yeah, T-probes you need this feature because you have only the tracing trace point data, and also the entry data support is also supported. For the K-ret probes or something like that, the return probes. So that when we are running the probes on the function exit, sometimes we would like to check that what field value is changing to what. And in that case, you need to make a two event. Function entry and the function exit, but that order, execution order, is not always the same, because some other CPU will call that, or in a function the thread can be sleep and another thread will run it. So that in that case which you need to find that the pair of the function entry and the function exit. This one will remove that pain, so that you can save that the entry data in by function exit prove. So that is the latest feature of the probes. So I would like to ask you some question about that. What kind of probes you wanna add? Yeah. For example, there's currently I'm in my brain, mind. For example, that are hardware breakpoint probes can maybe possible to add. So that if you hit that the function entry and wanna trace that one parameter's access, so that then you can specify that this hardware breakpoint and set to the parameter address or something like that. Then you can find that when the parameter is accessed or something like that. Or another one is a monitor probe, which one is something like the time. Time scale probes. So that currently all the probes is the place the based one. So that the kernel running that some code, then the probe is hit. But instead, maybe we can use the timer to run the probe and get some information, static information like statistic information like procfs or sysfs or something like that. That will help to monitor the kernel by using the tracing. Yeah. Yep.
Thank you. So just a quick idea with the hardware breakpoints. This might be useful, but most variables that I would be interested in are not static in memory. So this would probably need to be somehow scoped. Like when I enter a function, I can dereference one of the parameters, find a field, and dereference and find a field. This is the location I'm interested in. Yeah. And when I leave this function again, you can delete the hardware pointer until you enter it again. Yeah. So that would be probably one way to make it useful.
Yeah. Of course, I think that this one should use with K probes or F probes. So that those function entry and the function exit probe. Yeah.
So in Perf trace, we are using BPF to collect the contents of data structure that are passed to syscalls. Let's say you are doing a nanosleep, so you have the RKTP, the timestamp, the time vol. And so we copy it and send it to the end of the payload for that syscall trace point. So do you have anything in there that could help with that? Let's say instead of asking for a specific pointer, I would say get that pointer argument for this trace point or for this syscall, which is a trace point, and add it to the end so that I get this augmented trace points. And then in user space, Perf trace already uses BTF to do the ready printing, because you have to do all this stuff. Like you have an integer, and you know that the integer in fact is an enumeration, so you translate that. Or I use CTL. You have so this kinds of thing. You get the values from data structures, and you translate it further. You see, sometimes you use one field and refer to what's in another one, but we need the contents of the data structure.
Yeah, so that are something like a GDB's pretty print feature.
Well,
like
wait, are you talking about? So basically, are you saying that this event is hit, and when I hit this event, I want that field from the previous event, or is that no?
I want the contents of the data structure, like a syscall. I want to see what they use as best. It's basically replicating as trace.
Yeah. So basically this. So basically, or
without features.
Right. So basically, you have a syscall. Okay, syscall enter. Yeah. You have like the file path.
Yeah.
And then on exit, you want that file path that was passed in.
Enter, I want the file path.
No, you want the file path, but you want to pass that to the. No. It's not that. But so basically, wait. So you want to, or you just want to be able to trace
the content
of the contents of that. Yes.
So that's everything in there.
But you can do that right now with the. Well, you get. Wait.
No, we need to specify that there's something the special one. We don't. Maybe we can use that the BTF to find that how big.
We have the raw data, so we have it now in Perf. We get the raw data, and then use a specific path to a pretty printer that will get, let's say, this is nanoseconds, this is microseconds. In other case, let's say the Perf event or BPF, that there is an attribute, there are lots of fields. All of those fields have to be interpreted in some way. So this is a frequency, it's megahertz. This is so on and so forth. So we need to, when you do the syscall, you copy this thing, you put on the ring buffer, use the space, will do the pretty printing, or we'll save this into a perf data that later on another machine, I will pretty print. I don't want to pretty print it in the kernel. I mean, there are use cases for pretty printing. In the kernel, you are doing it. What I'm wanting is the raw data at the end of the trace point for the syscall, or for any other trace point that has pointers to structs. We are doing this in Perf, but using a method that's different from what you are doing here. So perhaps that I think that there is space for consolidation, you see?
Yeah, so that are some sides of the chunk of the data we can save that there is no pretty printer and no checking that the data data structure size or something like that. So that we need to add that.
Right.
That is a good idea.
Yeah, it's sometimes like soccer did here.
Yeah.
You have the size. It's another field for the syscall.
Yeah.
You see? So, I mean, the collector we have associated with that in the BPF knows about that, so it knows how much data to copy. It's working now. But if you had this mechanism, then we would switch to that instead of having to do these things. So we can talk about more later to tell about the experience we have on the perf trace and see how it could be done with your mechanism.
Okay, yeah. Thank you very much. And maybe one more.
1 minute.
Anything else?
Okay, thank you.
Yeah, thank you.
Thank you very much.
So now we have Alessandro talking about integrating Kas-alias into the kernel build.
Shall I start? Okay, hello everyone and welcome. I'm Alessandro Carminati, I'm from Red Hat and I'm working in the automotive effort for Red Hat. I've been around with this Kas-alias, which is a solution I am pushing upstream to solve the problem of the duplicate symbol in the kernel. In the kernel, as you may know, there are duplicate symbols that are due from various reasons, and the solution I am pushing to solve this problem is to provide an alias for all those duplicate symbols such that the symbols can be recognized and unique at the same time. Now, I arrived at the version 7 of this patch, and there is still some problem in order to make it to to make it in the kernel. So in this slide, you can see how the patch should provide its result. You can see that any symbol has a duplicate. The duplicate is made by using the file name and the address and the line number where the symbol is declared, so that this is enough resistant to be unique, even if it happens that you have duplicate within the same compiler unit, which is possible by using, for example, static variable inside the function. So the state as for version 7 is that the patch already provide the aliases service for VM Linux. It provides alias for the in-tree modules and export the symbol data to be used, for example, if you need to build an out-of-tree module. There is something that you need to be aware, but still it can be used. And for the minus side, we have that the makefile machinery I choose to implement is not that polite with the rules of makefile, because I have done something that the maintainer didn't like, and the patch as for now does not consider the LTO produced symbols, both the thin LTO and monolithic LTO1. You may know that monolithic LTO is mangling each symbol to make it unique. So in a certain sense, it already solved one of the problems I'm trying to tackle, but the way it's solved is by adding a numeric prefix that doesn't allow to recognize the symbol. So even though the symbol is unique, you cannot be sure of what symbol you are dealing with. And in this moment, my patch doesn't consider this symbol because they are formally not duplicates. So, but then there is another problem that is derived from header inclusion. As you may know, the header file defines static inline variable, but those static inline variable not always are effectively inlined. And when it happens, you have fully fledged function that get copied each time you use that particular header. And this creates not only duplicate name, but also duplicate function. And the way I am currently using to tackle this problem is not solving this problem, because they arrive to have the same alias because they are effectively defined in the same file at the same line. Another problem that I have came from C file inclusion. This, for example, you may see this, for example, in the compat binfmt elf.c, where the 32-bit version of the service is implemented by using macro and including another C file. This causes the function in that file to be duplicate as name, but different as contents, because the macro inside the file does change the contents of the at least there is another problem that derives from the build of out-of-tree module, or however later build. In the current approach, I export a symbol statistic, but there is a problem when a symbol that was previously unique is made become a duplicate from a later build, because in this case you have that the original build doesn't have any alias because it doesn't need at the time, but the new module that gets built on the second time as an alias, and this is not something that you may want. So here is my proposition to solve this issue. About the pipeline issue, I have modified the flow and fixed the problem of not being respectful of the rules, which I were modifying input file, which is not properly polite in the makefile etiquette. Let's put in this way. About LTO symbol, I was proposing to remove the mangling that is made by the linker at the link time, that is only used at link time. Kernel doesn't use this number. So my proposition is remove the suffix that LTO linker appends and treat this as they were duplicate symbol, normal duplicate symbol, and make an alias for this. As for C inclusion, this is more tricky because in the problem is that the file got the same exact source file and line number. Here my proposition. I propose to use the dash line preprocessor instruction to modify on the fly the debug information and make them accordingly to the same macro that change the function. In this way, you can have a properly tagged file by appending some kind of descriptive string at the source file name. In the QR, you see a small repository where I put a POC of this thing. Another thing that may be worth mentioning is that for doing this, I need a simple operation to be made at preprocessor level, which is not something that preprocessor usually do. And the way that I found to solve this problem is a little bit hacky, which is define for each line the successive number. In this way, I can simulate an increment to have the successive line in the debug information and have the correct line in the debug information. Okay, about the ladder build issue, I don't see any way out for this, because if you build the kernel in a certain moment and you don't know that in another time someone else would build another module that have a duplicate, there is nothing you can do. The only thing that may be said about this is that it could be possible to add an alias to each and every symbol of the kernel, but I don't see this as a solution because it would add an unnecessary overload to the call sims that is not necessary. And by the way, the out of three modules or ladder build is not that common to require something like this. But otherwise, I see this as a no-exit strategy, like trying to solving the Rubik cube in the dark. There is no solution for this, in my opinion. So, the alias strategy is something that I'm pushing upstream. I had some feedback for this. The conversation has somehow stopped in the upstream. I was hoping by this talk to sparkle a new interest interest in this topic and maybe have some feedback from people, from the community. And this is what I wanted to say in this meeting, and if anyone has any, please.
So I can understand why having duplicate symbols is ugly, but what's the actual functional requirement for these being unique?
Sorry?
So I can understand why having duplicate symbols in KALSIMS is ugly, but what's the functional requirement for these being unique? Like, how are these being consumed that requires them to be unique? Because I think that's missing from the presentation, I don't know.
Why they need to be unique. So when you want to make a tracing of anything, for example, for you are chasing a bug, there is one problem that I stepped personally, that was searching a bug into an interrupt issue on AR64. There is the geek that have multiple...
Git handle IRQ by any chance? Because we should just rename Git handle IRQ to be Git v3 handle IRQ. Like, a lot of those we should just fix.
Okay.
Yeah. So I mean, I guess, okay, to jump real quick, I mean, the real thing is, it's basically like, if you look for a symbol you want to attach to, basically you want to attach a BPF program or something like that. It's a lot of time it's done through a text name, and when you have 6 different functions for the same name, how do we differentiate? Yes, that's the thing. And but basically,
Yeah, sorry, I get that, and that's useful. But like, for the thing with, we've got a module, why do we just not always prepend the module name to the symbol in KALSIMS to make it unique for the late load case, for example? Yeah, it's ugly, but then if you don't care, you can just ignore the module part of it.
well, actually, we should just change the interface for the attachment, because the name is already there on the module. So in fact, actually, there is, like in ftrace, you can actually put, if you want to say I want to enable a function that's only in a module and nothing else, you just put the function name :mod : and the module name, and it will only enable the module, the function names in that module.
In the module, you can have several object files, and then there are static functions on different object files in there, and then you have different, the same name in the same module.
Sure, but if we've already got the other solution to do this per object unique, then scoping it by module gives us the late module case. That gives us everything, right?
So as far as I can tell, some compiler may make optimization, say they take a part of the function and inline and make the other part like mark with the code or something. How do you plan to handle such case? Because it's the line number going to be, for example, at least there's null number going to be confusing or missing.
Well, if they are duplicate, it's something that I'm going to tackle. If they are just modified for other reason, I do not have any plan for this. If this modified function are by chance duplicate, my approach would be remove the suffix and treat it as they were duplicate, and so add an alias to them in the same way. This would be my approach.
I mean, so if it's duplicated, the line number may be missing because this is only part of your function.
Mm-hmm.
Right? You also use the beginning of the function as the line.
I use what the its address is reporting me. So, for example, if I have only the first part, I will have the line where the function is defined. If by chance I have only the last part, I will have the line number where the last part begin, because I'm going to use the debug information with respect to the address that is in the KALSIM.
I think what Song is trying to tell you is that there's no connection to line. If a function is optimized to several parts and you like to attach to any of those, it's a different binary thing than what's in the source code.
Oh. In this case, probably I haven't met this case yet, so I do not have any solution ready yet. Still, if it happens, I will find out something. I do not have a solution for the moment.
Thank you.
Yeah. So that I just wanna also clarify that the problem of the scope. So that if there is some also that the same name function that it's in the different files, different C files. Those are easy to find the differentiate. But if the compiler makes from the same file, same symbol to the different symbols with different types, it is hard to sometimes hard to trace those with the same as the same the trace event or something like that. Yeah, because that some it will change the parameters. Some parameters are gone. Yeah, with one symbol, but another symbol will go, have two parameters or something like that. So yeah,
I'm not sure to have your, because yes, indeed, during the compilation, the function may change the signature, and this is but they remain the same name, so their address can still be recovered from the debug information. But I'm not sure this is what you asked.
Oh, so that you will use that debug information?
Yes.
Okay.
I take the address directly from the DWARF.
If I understand correctly, you're saying that if you have two symbols with the same name but different prototypes, and you're using that as the key to look up, that's a pain. Yeah. Whereas if you can get the address, and then that's a unique key.
The one that is effectively implemented. I do not relate with the source code. I take the information directly on the DWARF information. So it is something that comes after the compiler has do all its magic.
You mentioned the inline functions actually not inline and present in several instances, right?
Mm-hmm.
So I think it's okay to have same name for that, because they are actually the same function, right?
Hmm?
If you declare some function as an inline, but it's not actually inline in some cases, right?
Mm-hmm.
In that case, you maybe want to change the names to differentiate.
Well, in that case, they are not on the call scenes, so they are not. If a function is inlined, I don't see it in the. Oh, sorry. If a function gets inlined, the function doesn't appear in the call scene table, so I don't need to tackle this problem, if this is the question.
I think you mentioned some cases the functions are not inline, right? And
well,
have several instances.
You have this typical scenario for duplicate symbol. You have another file where you have an inline function, a static inline function. The compiler, for some reason, decide to not inline this function.
Mm-hmm.
This, as consequence of this, each C file that includes that header file as a copy of the exact function. In this case, I have several functions that are identical and they came from the same exact file name and line number.
Yeah.
The solution for this doesn't exist. My proposition is just to append a number, because to make them unique.
I think in that case it's just leave it as is, because they are.
You may want to trace one
just
of these.
One of those instances. So I want to trace this in line if it happens here.
I'm not sure that's the reasonable use case, because you want to trace that function, you may want to trace all of that instance.
Not, if you want to trace all of them, you put all the copies in the trace.
But the problem is you can't. You can't trace all of them because whether or not it gets inlined is going to differ per compilation unit. So it's already not guaranteed, I think is the point being made, right? So if you really want to trace that instance, trace the caller. Or trace by address, right?
Anything else?
Thank you.
And now we go from break. Meet it back at a half hour. Oh, people were taking notes, I believe. Oh, so it was you? Oh, yeah. We can tell people to take notes. Well, actually, what I plan on doing is also just going back and watching the videos and taking notes again. That's what I end up doing. It's just like, okay, I'm supposed to take notes, go back and watch. Because when I try to take notes, it's the delay is so hard. I'm like, I just gave up on taking notes. Hey.
Are you running summer? If I just do it, that's what we're doing. So if we have multiple. I'm not speaker.
Well, the current version is not released yet. So it's the same idea. I want to keep the list open debug. If the next sample will hit the same way.
Yes.
Thank you.
Hi, I'm Charlie. I've sent a couple of Perf patches recently. You reviewed one of them, so I did a patch about like getting the ED cell from a Perf event ID. I don't know. I've sent a couple of patches and I haven't gotten much feedback. So I was wondering if like for like libperf, like a 3 or 4 series from libperf. So I was wondering.
To get the idea of the EDCell, right?
Yeah, so that was yeah, you responded to that one, but there's a handful of other ones I've sent recently, so I don't know. Is like libperf not a point of interest, or is it like not something I should mess with?
It's a part of the Perf tools. Yeah, because of the lack of the time for reviewer to read.
Right. No, yeah. So what I've developed, like it's very simple, but like I wanted a tool to be able to, is like for checkpointing, save and restore. So it's like I have a program that I have checkpointed, and then I want to execute that program for a certain number of instructions, and then after that number of instructions, it's not going to kill the program. So like I had to add not very many, just some changes in libperf so I can like have triggers, so like after that number of instructions has happened, I can stop the program. So I guess, and then so I was using libperf for that, but
say that the Python is not interesting part of the
right.
And this for me, so I haven't looked at that part for a while.
I see, I see.
I think it's better to put it in the part.
Okay. Yeah, it's kind of interesting where I feel like libperf is very under-featured.
yeah,
and then like
true,
the
true.
Python is like catching a lot of internals that aren't being exposed by libperf. So like it seems like it's using some of libperf, but then it's also using internals. So like if you want to just use libperf, there's a lot of framework around it that the Python is using. Like the C part that Python is using.
Actually, there is some interest to improve libperf part, as Ian mentioned in the first talk.
Yeah.
We have the colleagues to want to improve perf features, but because of the license issue, they didn't put much effort into it. So I'm not sure.
Okay.
Yeah,
Interesting.
but in general, I think you need to improve libperf and move more things to the.
Oh, you think so? Okay.
Yeah, I missed your views patches release.
Okay, yeah, no worries. Just want to make sure, like, I was just worried that it was just something that people didn't, like, if people don't care about it, like, I can just keep it, like, if I just have it internally, it's like something makes it, like, it feels bad. Like, it would be nice if I could help people.
That's what padding is for. Yesterday I was like the BTF. You want that I can run the... Yeah, I'll run this.
I see Alexander's online, so that's good.
Yeah, hi. Can you hear me?
Yeah, I can hear you. Perfect. We'll start in about 3 minutes.
Thank you. And I'm getting in some kind of a presenter
Okay,
mode
hold on a second. Wait.
Yeah.
Is the sound person here? The sound person. Yeah, she's not here right now. Hopefully she comes back soon, or maybe probably get...
Okay.
Alexander, speak again. Alexander, can you speak again?
Yeah, I can say something for the sound test, I guess.
Okay, yeah, exactly. It's like, so how well does everyone hear?
Yeah.
Like, oh, yes, there she is. Like, so we will have a virtual person or someone, a virtual person. Alexander, you're virtual. So we're having a virtual a speaker today. So, and I think it's about time to start. So our next speaker is, Alexander Arling. And whoops, let me give you presenter. You're going to need that.
Yeah, thank you. And I hope you had a good break.
And now you could click, since I gave you presenter before I switched to slides, you could go and click the plus, find your, that big plus at the bottom, find your presentation and select it.
Oops, I'm in Zoom in. No.
For you. No, the plus on the bottom. You see the blue plus on the bottom of your screen. Click that.
Yeah. I see it.
There you go.
Yeah. Thank you. So, hello everybody. I hope you had a nice break. My talk is about networking and tracing, and I My name is Alexander Aring, and let's start. So the topics I want to discuss is more about my use case which I have, and some things my tracing use case, and some things I was going over it. I was using the time synchronized tracing. I don't know if everybody's familiar with it. You can actually have time synchronized tracing over among of different machines which are doing tracing at the same time, and then you have the events in order coming in. Then because my use case has more to do with distributed networking tracing, I was thinking about how to bring the tracing buffer to a remote machine and how to access this buffer then. And when we have this, then I was thinking about, it's going over a networking interface, and a networking interface has a tracing offload engine, and I got some more ideas about it. So my main use case, I already said, it's about distributed tracing. So the person here, it's me. I'm sitting in front of my computer with a monitor, and I have a tracing application, and I want to trace a cluster. For example, Linux cluster, which has several nodes, and those nodes are connected over a LAN. It doesn't need to be an IP protocol involved. It can be also only link layer because I don't have any routing or something like that. And those nodes have time synchronized tracing with a global clock source. And I was thinking here, when those nodes need to get the tracing buffer to my user machine, we need to have networking involved. And I was thinking about to have directly the tracing buffer on the networking interface. And when it arrives the networking interface on the user side, then why we cannot just do something like filtering or classification. So the PTP implementation in TriCD, I already used it. I did an announcement several years ago about my distributed log manager viewer, which is my protocol which I want to trace over in the Linux cluster. And for me personally, I tried to use it, and when I have the machines in a virtual machine and using the vSOCs, there's different kinds of how you can do the tracing, time synchronized tracing, and the KVM method, which is not using PTP, it always works. It was using some KVM clock source and over vSOCs, but this only works with the virtual machines. But when I was looking into TraceCMD and wanted to have it on a network like I showed you with the LAN, I cannot use this. I need to use PTP, and also TraceCMD has a PTP implementation. And then I looked into the source code, and I was seeing that clock get time is done in user space directly in TraceCMD. And I see that there's probably a big error gap, because we're doing this clock source, the clock get time in user space, and then we have OS noise involved, like scheduling, queuing up things. And what you really want to have is that when you transmit the PTP message, then on the NIC, the timestamp is done to reduce this error, not in the application. And why we care about this? Because when we want to trace the Linux cluster, then we have always causality correctness, like action and then followed reaction. And I think when we get, in the ideal case, when we get the accuracy of PTP under nanoseconds, and our clock source is running in nanoseconds, then we have directly causality involved. And that's why we need to care about to have the accuracy of PTP best as we can. So then I was thinking why we don't use Nick Harvey's timestamp. This is done what we want to have. So the timestamp is done directly on the NIC. You can get this over auxiliary data on the socket, and then you're getting that. And I think I'm not a totally PTP expert, but I think we can improve the TraceCMD PTP implementation by using that. And then also a NIC, a modern NIC has also a PHC, that's the physical hardware clock, that's abstracting like they work like a POSIX clock. You have adjust time, but always when you want to get the source code, the clock, then I think it costs you a lot of time to get that. And but I was thinking about why we cannot use directly the NIC PHC. Also, there's also a term which is time-sensitive networks. There's a lot of research into that to knowing the time of every machine in your network. And then this has a lot of to do with Linux PTP. And I don't know, the TraceCMD, how it's currently working is that it only saves the timestamp offset as a metadata on your recorded traces. And there is no real global clock which is synchronized as -C. But I think this has good reason, because you want to handle that only in user space. It's a whole user space concept with handling the time synchronized traces. But I still think about how we can maybe use Linux PTP with, they have several tools, and then you can synchronize clocks with it. For example, PHC2sys, that's for synchronize the system clock, but we are also keeping a clock in the TraceCMD user space tool. And why not synchronize that after some interval? I know there's a tsync interval argument as well. And maybe I was not looking into that, but I think it's already good to know to make the hardware timestamping. So that was my point about PTP in TraceCMD and how to transmit. So now I want to talk more about we need somehow to get the trace events to a remote machine. Again, I'm somehow the client here, and then we have the agents in TraceCMD. You have these agents and the -A command, and then it records the nodes here. And what I was thinking about how much data copies we have there. So I think we have at first from TraceCMD, from tracing buffer to user space, and then putting it into the socket buffer. There we can maybe get rid of this with splice, some splice magic. I'm not sure but this will only connect the tracing buffer in the kernel to a socket, and they're still a copy because you always have the tracing buffer. But then I was thinking about why not directly operate to get rid of the tracing buffer and directly filling the NIC hardware. And yeah, but you can already see on the networking side, they have a special page pool also, which offers you struct pages which are directly DMA mapped to the NIC ring buffers. And the NIC, they have several ring buffers, so you need to fill them up, and then you can transmit them. And then, yeah, but this is only for the raw tracing data. We still need to think about what we do with all the metadata of TraceCMD, of TraceFS. for example, when we have the raw trace data, we cannot interpret the data yet, but we need also to somehow to the client, to the remote machine, to transport the metadata. And yeah, I already was mentioned that on the mailing list, and directly there came something with we don't have any cache locality, because currently how the trace buffer works, that is that we have a per CPU buffer, but when we have a NIC attached, then this NIC is probably on some NUMA node attached when you trace on a different CPU, and then want to transmit that it costs you time because it's not directly attached. It need to go over the other CPU and then where the NIC is attached to the NUMA node. But in my opinion, this is a general networking problem that people want to handle better. They currently handle it like, you need to pin something to this CPU where your NIC is attached to. I don't know if something similar can happen with tracing, but I see for my use case, which I have, maybe we don't care, because we need to transmit the tracing data anyway to the network, to the NIC, to the remote side, and the user sees a stream of trace events and want to get them fast as possible, and the machines are not interested into tracing. And yeah, when we having the raw tracing data arriving on our NIC, then we can use something like AFXDP. This is a socket buffer which is express data path. It's named express data path, and this is directly operating on the NIC buffer. But I also see that currently there are some, it just got merged into the Linux kernel with TCP devmem, device memory. That means that the payload of a TCP is also directly accessible over the NIC buffer, and there's no copy anymore. And yeah, I was thinking something like a Wireshark. When we have that, then we can directly use without any more things to be changed. We can use Wireshark as a user space tracer. I know there's a project around kernel shark, which is somehow the pardon to Wireshark for tracing. But in this scenario, we maybe can use Wireshark. And Wireshark has these dissectors that's according how the protocol data, the raw data is interpreted. And I think we can use the tracefs to directly build a dissector during runtime. And yeah, when we get the tracing data, a NIC has always an egress port, ingress port. Egress is outgoing and ingress is incoming. Yeah.
Wait, Alexander, can you hear me? Oh.
Yeah.
Okay, yeah. So real quick, first of all, quick question. Do you know any of the Wireshark maintainers?
No.
Because
I submitted something to Wireshark.
So way back when, I think 2009 or early 2009, I sent an email to the Wireshark developer list saying, hey, it would be great if we could hook Wireshark to the tracing systems. Would you be interested in anything? And all I heard was crickets. I got nothing back, nothing there. So that's when it was inspired to write Kernel Shark. So Kernel Shark was just because if the Wireshark people came back and said something, Kernel Shark would never existed. Just FYI. So that's why I would love to have Kernel Wireshark to be able to hook into something, but I don't know any of the maintainers. Anyone here know any of the Wireshark maintainers? So actually the networking people are here. I should go around asking them, because that would be something I would be happy to have or happy to help with. So, but if you can't modify Wireshark, I don't know.
I don't know how, when we make it so that it looks like a normal networking interface, and then we say something like, okay, this is my protocol. The trace data is my protocol. I don't know how much they. It sounds for me that that's what trace Wireshark is made for. But okay, when maybe we can bring this topic again up on the mailing list with them. Yeah.
Yep, we'll continue.
Yeah, and yeah, I don't know. I was also this. There is in kernel there's actually an interpreter for making filtering on trace events. I showed you the .c file. I think there's also, of course, other ways to do that, but another way would be then, because I said that when you're getting the tracing data or on your NIC as receive, you can directly filter out trace events, because a NIC has mostly some generic offloading mechanism. Like in there's traffic control, it has U32, that's a very basic classifier that's only masking, shift, and compare operation. And this combination of trace FS and a nice CLI interface or a GUI even, then you can directly, oh yeah, I want to form this specific match for my trace event, and it pops out your TC commands, which then getting involved into your NIC, and then I think you can match on some trace events, and then when you can match, then you can run actions like drop, and there's also classification, which is my use case. You can give trace events a unique number, or there exists also P4. That's a programming protocol independent packet processor. There's several ways, and then you can do that in software, but you can also say, okay, with the right NIC, you can say offload that to the hardware, and then we don't interpret anything anymore on the CPU. And yeah, it's only U32. I talked about it. When it's only a bunch of TLVs, it should be very simple to do that on an Ethernet frame. For example, Ethernet, it can be also some other link layers. And mark is for classification of trace events. Like I put, when specific fields has a specific number, I want to give them, in general, a number to hash them. And you can also redirect and other things. And I was asking me, maybe even a local case where we have the cache locality problem could be useful when you have a lot of offload things to do. I never tried it out yet, but you need to see. And as next, I want to see into the TraceCMD PTP implementation. And I think to have the hardware timestamps, that would be the first step to get that I get more involved into this implementation. And then how maybe I can combine that with Linux PTP, because Linux PTP is not, I would say it's not simple, because I also was hearing some talks about it, that they have some PD controller, they have some PI controller, forgot it, there's some controlling mechanism. And this is a lot of research involved to have the starting problem, and that it doesn't oscillate so much, and have the error rate of your time synchronization very low. And as next, yeah, with the NIC ring buffer, I would forget about this NIC ring buffer, but I would catch up what Steve already said before, to have something like Wireshark, to have a virtual network interface that we have the user space view about a networking interface, which offer me the tracing data, and then try out Wireshark, also trying out filtering, because I said before, yeah, there's always software solutions. And with U32, you can try out if you actually can filter, you have a different approach to have the kernel interpreter running. And then look, afterwards we can look about how operating on real hardware and sending it to a remote machine. Yeah, and that's it. So are there any questions?
Yep.
Discussions about this idea? Yeah.
Yeah, I mean, one thing I'm not seeing here, I'd really like to see is benchmarks, because you're assuming that by sending things over to the NIC and offload computation of filters and stuff like that, you're, I guess, making things faster. But I would say, well, yeah. I would presume that keeping things CPU local and, I mean, keeping in L1 whatever you have as data set to perform the filtering on the CPU would be faster. But then, so you'd really need to bring good, convincing benchmarks to show that it's actually better to try to offload or send it farther away from the CPU from a tracing perspective.
Yeah, but one of the problems that he's dealing with is not just speed, but the accuracy of the timestamp. And I think one of the problems is he wants the accuracy of like when I believe some of the changes was very NIC centric, where the NIC actually added the timestamp to the so.
Yeah. I mean, for the timestamp part, I mean, what you want is correlation points between whatever time source you have locally in your machine and what time source you have on the NIC. So if you could bound those communication points, maybe that could help you. It might not have to be all the events that carry those NIC timestamps.
Before, time's up, if there's any last question, let's do one more question and we'll do time.
I'm just curious, Alexander, did you look at using XTP maybe as a mechanism to send events out over the wire? Yeah, I think you mentioned AFXTP, but actually triggering an XTP program perhaps, would that be something that might do the trick?
I mentioned AFXTP here only because it directly operates on the NIC buffer. And then with the action, yeah, I could run some filtering, some matching also on it. But I only mentioned AFXTP here because I get it easily in user space directly from the NIC. That's what I'm doing. But with AFXTP action, yeah, I can say, okay, I get it directly in the user space, or I do it in the Linux stack, but yeah, I need to look into that.
Okay, thank you, Alexander.
Yeah, thanks.
Which one's yeah, I'm looking for the libs. Is this it? Tracing side? No.
Tracing side, yeah.
Someone close the door, please.
All right. So now let's talk about instrumentation of user space code. So there's a project which we call libside that we've been working on for the past 2 years or so, 2-3 years. And it's meant to be really kind of a redesign, a complete redesign of the trace points. So I initially did the trace points for the Linux kernel, on which Stephen built trace events. And then I ported those concepts to user space in LTTNG UST. But eventually, I mean, we faced some limitations or, yeah, with those approaches. And after some discussions with Microsoft, seeing how they did things on the Windows side, so I came up with a completely different scheme on how to instrument user space that is much, much simpler actually than trace events, but keeps most of the benefits we have from trace events and trace points. So I'm going to present a bit the recent, I would say, progress in those areas.
So one of the recent thing is we moved the scope of that project from only targeting C and C++ to really create a specification that specifies an ABI for runtime and various language instrumentation. So libsite becomes a reference implementation of that specification for C and C++, but it's not the only target. So what the site specification covers, so it covers how to describe events and field descriptions as an ABI, binary ABI. It has a type system. It describes how to serialize captured arguments and pass that over to tracers. That's also ABI. And it specifies how to sample internal application state. So it basically specifies how applications can be instrumented and how the tracers can connect to that instrumentation and query what is available. So one recent progress, so it's mainly Olivier Dion who has worked on this recently. So it's in a feature branch currently. So we've added static type checking between event descriptions and the call site that passes that pass argument, and it's based on macros. So before that work, I was not even remotely aware that this could be done, and actually that works. So we basically rely on preprocessor macros to emit two things whenever a macro is being used. So there's something that is emitted for type validation, and we emit whatever description we want. So that's at the event description site. And then on the call site, we also emit two things. So we emit something that does the type validation and that will cause the compiler to generate a compilation error if the type mismatch. And we generate whatever is needed to push the argument on the stack following the ABI. So that actually works. And there's no multi-header inclusion, nothing. It's just by having this idea of emitting two things when a macro is used. So, and I think that, so I don't have many slides on this topic. That's good. So it's the last slide. It's a discussion. One of the aspects I would like to discuss, so I've been interacting a lot with Bo Belgrave, actually with the TraceFS meetings that we have every 2 weeks for the past year or 2 years that I've been attending, something like that. It's been going on for a while. Yeah. So he seems to be very interested to extend user event to kind of, well, how I see it. So currently user event, when user space registers an event with some typing information that says, okay, well, the payload that is going to come when this event is hit is going to have this layout with those fields and all. So this is currently using a string. So the application needs to format as a string the typing information that of the event it registers. So I understand why people use string when they are on the command line, that's fine, but I feel like reusing a string as an ABI for an ioctl that register an event is a bit pushing the envelope. But it's ABI now. So, but we could extend that to eventually support expressing this typing information with the side ABI. So that would be, I guess, my proposal for that, to extend user event to allow that. And then user event could also be extended so that rather than receiving in terms of argument, well, no, not rather than. So the existing ABI will always have to be supported. But in addition, so there could be a new mode where passing the arguments over could be done following the part of the side ABI that describes how to pass arguments to a tracer. So those are ideas. If you guys have feedback on this or would like more discussion on this, that's one topic I'd like to discuss.
Well,
Steven?
I'll just say basically, I know the string parsing, that was probably because it fit in there. There's nothing that stops us from, like I said, if we create another call and do it. Because I mean, there's a lot of times we just always have a raw version of something. I mean, even like trace.printk, we have a trace.printk raw, which is actually made for writing data structures directly into the ring buffer and then extracting it. And ftrace just says, I got a binary blob, you read it, you do whatever you want with it. So, same thing.
Yep. Awesome.
maybe I'm too contaminated by Google way, but we can try to use that protobuf.
Protobuf, oh God. So one of the thing is, that is really on the tracing fastpath between the application and the kernel, or even, so this ABI is going to be in the fastpath between application and my user space tracer, right? So I care very much about minimizing the overhead of setting up those arguments on the stack, right? So currently it's really, it's laid out as an array of entries which will follow the typing information that matches the event description. So the idea is from a, let's say, bytecode that gets interpreted in a tracer, my goal is that this bytecode can directly go and read that input information from the array and make quick decisions, filtering very quickly. So I don't want to have a protobuf decoder in there at all, at all.
Okay.
No. Thank you.
Any other comments?
Questions?
Questions or discussion or? Yes.
Back on the scope of the project, you say this will allow you to trace runtimes other than C, C++, so that would be also interpreted languages, or
yes.
like Perl, Python, whatever, Java, Ruby, Go?
Yes. So the goal there, so I'm making sure that the parts that become ABI are kind of runtime agnostic. One example, so in libside, there's code to, let's say, do the call of calling libside from the runtime, the C++ runtime. So that call is following the System 5 ABI. It has a specific signature and all. So what I plan to put in the spec is just, we need access to those structures, that data, and this is their layout, but I won't specify that it needs to be a System 5 ABI call. That would be up to the implementation. So yeah, splitting ABI in the specification, the rest can be implementation specific per runtime.
I just want to always verify this because, you know, I'm always in the kernel, but just saying, because this would be like an interface for user space, you would be attaching to this. And once you have that attachment, then in user space, so if you use libside and you have, I guess you could put whatever you want in it. I'm assuming that anything then could say, hey, this has libside in it. I could write a tracer or something right now and hook to it? Or
but not necessarily just libside. I mean, you could have Go, using that ABI to emit its own instrumentation, have its own Go tracer connect onto that, and have from that Go implementation have its own hook to let the kernel know about the existence of this. So it does not have to rely on the C, C++ level library. It can be done natively in the language.
So you have a specification for this already written?
I'm working on that.
Oh, okay.
Hello. Question on the overhead for the interpreted languages. We noticed that even for minor version changes, for example, from Python 3.11 to 3.12, there are really hard changes in the runtime that are not affecting the Python API, so that does not break anything, but the runtime changes internally. And if you are doing traces, what is your expectation for the maintainers of such runtimes to be applied to site? So do they have to change every time with every change in the runtime everything? Or what's the idea?
The idea is, okay, so you're talking about Python, which would, let's say, try to implement side support.
Yes.
So side specifies structures that are kind of packed with the known size and layout and all that stuff. So I'm not sure I understand fully your question. So is it that the runtime have the freedom to move around the content of those structures?
Yes. From my experience, I'm doing tracing. Runtimes like Ruby, Python, Perl, they are changing internal runtime structures quite often, quite heavily between minor versions that don't affect external stuff.
So the nice thing about, so I'm pretty sure that those runtimes need to interact with the kernel, right? And they sometimes need to issue system calls.
Not really, because they are the Python virtual machine basically that is in between.
But if it's open a file, I mean,
sorry?
If it opens a file, it has to.
Yes, I mean there are some cases where you need a fixed layout.
The machine has to interact with the underlying.
Yep.
But I want Because you were saying...
Microphone.
Only one hand, by the way. I'm curious where Mathieu was leading with his remark, because the conversation was going, you were saying the Python developers, they change the runtime at every single version. My intuition was, well, it's up to them. I mean, if they want to maintain a tracer, they also have to change the tracer with those improvement to their runtime. You were saying, wait, but they have to issue syscalls, right? And then what's the next, where you were leading to?
The next point is, I mean, that runtime has to interact with the outside world, right? It has to format network packets and send them elsewhere, right? There are cases where you need a fixed ABI layout.
No, I think let me see. Maybe I'll get the question here differently. So say if you have you want to trace the internals, you're basically tracing the internal workings of Python. So you have Python, you're tracing. So there's a structure inside, and I want to trace, put a libside on that structure. But then later on, next version, they change the structure.
No. That's not how it should be done. So, let's say Python would want to add trace side events in Python, kind of describing the inner working of the runtime, right? So what you would do is you would pick what is really kind of high-level important information and put that as, well, this kind of becomes an interface that tracers can connect on. With a newer version, that the concept goes away completely. You remove that event. And then you change the semantic and everything, but then the tooling needs to adapt because that concept is gone. So
and also I'm assuming that if you're adding tracing for this, maybe work with the Python and Go or Perl or whatever maintainers that they want the trace, basically like the kernel. The kernel likes, we have these trace events all over the place. Same thing. If you're going, they'll put it in there, and they'll probably, if they want information out of it, they might want to keep those things somewhat consistent.
Yeah. And I mean, don't put implementation details, but put high-level concept and the relevant information that goes with it.
A follow-up, Mathieu, as much as you want to share, I believe that this is a very generic mechanism that can be adopted by the various runtime, but you probably has a goal in mind. Maybe there is one particular language that you are planning to support, I don't know, C# or whatever is your future project. So if you want to share what is the exact application that you have in mind, or it just...
The initial one I care about is C and C++. I mean, that's what my customers are using today. However, things like Python, I mean, AI is quite big right now, and I'm pretty sure in the coming years, it's going to be an important target. So I want to keep the door open to have support for that type of runtimes.
And Rust.
And Rust. Yeah. Other questions?
Any other discussion points? So you're all done? Oh.
Thank you.
And next up we have Mathieu Desnoyers.
Still me. All right. So do we start now or 1 minute left? Start now. Okay, let's do it. Okay, next topic, handling page faults from kernel tracers. So we had a patch set that we've done a couple of revisions, and I've been lucky to have the eyes of Linus Torvalds looking at my code and telling me it was wrong. So I changed my approach, and I think it was actually really a good improvement. So I'm going to show a little bit the context there. So the use cases we target. So we want to allow kernel tracers to read data from user space memory. So, and the main case would be syscall entry and exit trace points. So we, especially on syscall entry, we want to know what's the input data. So we open a file, we want to grab the path name that was specified in user space. That makes the overall trace really kind of usable from an end user perspective. So there you really get a strace-alike syscall tracer. And basically what I want to do is a strace-alike syscall tracer in the kernel with LTTNG. So which it currently does, but it has some limitation because it cannot take page faults. Another use case would be user events. User events could receive pointer to user space data, so having a way to basically take page faults there is important. However, user events is kind of specialized. It could take its own page fault beforehand. So that maybe that one is not so important. But Taking stack traces from syscall entry and exit is also another use case where this allows you to really correlate what is the causality link between application backtrace and the syscall. So let's say you find syscalls that are misused or called too often, then you want to find the offending user space code that calls those syscalls. Then with those backtraces, you just find the offending spot.
I'll also add, well, especially since lately, you, me, and Josh have been working on S-frames, so we were going to be getting really good stack walk tracers. By the way, just FYI, we're just at the GNU Caldrum, since we were early, I could jump in here. We're at the GNU Caldrum, and Florian was the libc maintainer is on board with S-frames, so he's going to rebuild libc with S-frames. Josh has a prototype out there already for the kernel to have it. What's S-frames? It's a way to do accurate user space stack walks without frame pointers. So we could, in Fedora, we could turn off those frame pointers stuff, build everything with S-frames, and the kernel will be able to walk the stack of user space. So we could do it in the kernel very easily. And one thing about the faultable thing, it requires a faultable context. S-frames are mapped in user space, so the kernel has to find the information of how to walk the stack trace from the kernel to reading user space addresses, which will fault quite a bit. So by having the faultable system calls, we'd be able to do that immediately. One other thing you could do with this, and I don't know if you mentioned this in your thing, is filtering. Now you could filter, if you wanted to, your trace, like say I only care about these system calls from this user space function. So when you hit the kernel does a stack trace, the filter could say, this has my function I care about, trace, otherwise throw it away. So there's lots of things you can do with this. I just want to throw that out there.
Yep, thank you. Yes, use case, action to perform. So I was coming to it.
Sorry.
So kernel tracers, ftrace, perf, eBPF, LTTNG can use this data for copying it into a ring buffer, that's clear. Perform online filtering based on input, exactly what Steve mentioned, especially on syscall entry, for instance, that would be really useful. It can be either on the syscall parameter, user space content, or on the stack trace. So indexing counters within maps. LTTNG next version will support event counter maps. For future versions, we also would like to do allow specify how much to increment the counters by. So you could use user space data to choose how much you want to increment by. And emitting triggers, trigger notifications to capture specific fields. So to have a kind of a more lower latency response to what is happening. So for lower rate events that can bypass the ring buffer. So just a few words about the current limitations. So there are some scenarios that lead to always unavailable data. For instance, if you execve a program and then you immediately do an openat and where you have the path name in your program data, that's not paged in. So you're taking a fault. So the tracers know nothing about that path name. So that's a problematic scenario right there. Basically, any data that is not faulted in from the program or library is an issue. And also, the stack walk is a good example where if you have pressure on your memory, or I guess that would require pressure, right, to remove the pages that are at the stack bottom?
Well, actually, it's not my thing right now. Is if you're going to go S-frames?
Oh, the S-frame per se. Yes.
The S-frames themselves are going to be faulted in.
Yeah, that's it. So just to grab this S-frame section content that describes basically how to unwind a frame to the next function, just to read this information, it's not paged in. It's just mapped. So you need to take those page faults as you traverse. Yes, I didn't think about it. Thank you, Stephen. So my proposal is to allow syscall trace points to handle page faults. So the kernel trace points, they currently disable preemption around to iterate on all the registered tracer callbacks. So I want to modify the syscall trace point to use task trace RCU, which has been created for that very purpose, actually, by Paul McKinney, for use by eBPF, but then we could use it for other means. And it would allow the callbacks to take page faults. So I have the latest version of the patch series sent. And yeah, so it's open for feedback. Let's see if how to. Oh, there's still content. Okay, good. I'm not done. So our tracer can handle page fault. So those are some ideas on how the tracers could integrate with this, because this patch series really just makes it possible for tracers to take page faults. And I adapt the tracer probe code so that if they depend on having preemption disabled, they disable it internally within the probe. So basically what it allows approaches the tracers can take to handle faults. So they can either decide to fault in all user pages in a preparation step before entering their preempt of critical section. That's one possibility. It's not 100% perfect. I mean, if you have extremely, insanely high pressure, they could be paged out, swapped out, but I would find it unlikely. So for practical purposes, that should be good and easy to do. They could decide to copy all user space data to a kernel area before copying that to the ring buffer with preempt off. That's another approach. Or they could modify their ring buffer to allow access with preemption enabled. So LTTNG modules has been created with a ring buffer that is also implemented in user space. So with a few tunable, I can make it work with preemption on. So but I cannot say the same for other tracers. They are not designed to do that. It would be a relatively larger change. By the way, there were some sessions about seccomp earlier this week, and this has been mentioned actually. So the difference there is for seccomp, the case where they would like to copy user space inputs into a in-kernel copy. The only difference there is the need to modify the syscall implementations so that whenever that copy is available, it go fetch from that copy rather than fetching from user space. Because for security purposes, they do not want to have a check time of use race. So that's the difference. For tracing, we don't care that much. I mean, if it happens, oh, well. So it's not being used as an attack vector for seccomp. So if we do the approach where we copy user space data to a kernel area, I think we should synchronize with the seccomp people, because that could be common infrastructure if we ever go there. That's what I have. If you guys have questions, comments.
I mean, we only have 19 minutes left.
Was that fast?
Well, you finished your first one early.
Oh, okay. That's
in fact, you're halfway through by the time you got to the time of your first one.
So now you have the time to review my patch set.
Why don't you pull them up?
It's not my laptop.
Well, yeah, you can put up. Well, you posted them. You can go open up, share a window.
Yeah.
So yeah, no, I'm way behind everything, and it's multiple things. Whoops, there you go.
So you mentioned using this for syscall trace points. At one point, you also said ftrace, I think. I might have missed
ftrace? Yeah, but the syscall. So ftrace can hook to syscalls in two different ways. So one way is the raw syscall, and the other way is kind of hooking on the syscalls with something that is aware of each of those.
All I'm trying to ask is this just going to be for explicit trace points or for other things? Because if we attach this to ftrace and so on, it would be possible to get recursion through, you trace something within the fault handling path, you get into that.
No. So it's only for the sysentry and sysexit trace points.
This is a add only. Like, it's not going to be just, hey, just hooked to anything else, like, the RCU idle. It's like, well, actually, we do have like trace points that we have to mark. Remember the old RCU idle, which you got rid of with the no instrument stuff going on. But yes, so right now I think the only faultable ones are just the syscall. I think it's just the raw syscall, right? We're not, because I think the other one, because it attaches to...
No, the two. So they both the syscall, sysentry and sysexit trace points are modified, so they become I don't recall, but kind of declare or trace event syscall or trace syscall event. So they become a different kind of thing. Yeah. And then the register function for the probe has a different name. It has an extra syscall in there. So you only register syscall probes to syscall events, and that's it. So, but those are the only case we foresee.
Yeah, it's funny. Just FYI, all the system call trace. Like when you look into the tracefs directory and you see all the syscalls there, those system calls are actually pseudo system calls. Or so, I mean, those events are actually pseudo events. There's only in Linux, there's only an entry on the entry of, and one on the exit, and then we build up on top of that. And now we're ftrace, because ftrace, the ring buffer, we usually do the reserve, the ring buffer, and then we end it. For these faultable syscall, or faultable, if you say, I want the stack, or for anything that asks for that, right now in the filtering logic, a while back ago, I found out that if you reserve space on the ring buffer, and then that's really fast. What ftrace really sucks at is saying, I want to discard that event. So if that's actually a very slow, takes several atomic operations to do it. So if you're doing filtering and you're throwing away 90% of your events, I found out that the performance of throwing away all your events after writing to the ring buffer was so effing slow, I found out it was actually quicker to create a temp buffer, copy into that, and just throw it away if you didn't do that. And so the copy was much quicker than trying to do this other thing. Now, with this, I'd have to just say faultable. We just say use the
copy.
The copy. It'll be perfect. Well, so I don't know. We have to do a migrate disable. That's the only thing we have to do. A migrate disable or something. Or we have to do something where.
Or decide to put the copy associated with the task rather than CPU. I mean, we'd have to figure that out.
That's implementation detail. But yeah, that's something we do.
So. I guess you ran this session early, so I missed most of that. However, I spotted this your talk essentially last evening and thought it might be relevant for something that I had an issue with like 15 years ago, and it seems like it might be a good fit. I mean, does this framework, and I yet have to have a look at your patch set, obviously, does this framework provide for something like being able to fault in pages when running a session attached to the kernel via JTAG debugger? Essentially, that's something that we did on x86 even. We had JTAG probes back then using the Intel Atom architecture. And there was this idea that we could actually sort of like, if you load the symbol table into your debugger, then you can even examine your user programs. However, the issue is, while at least on x86, you can actually walk the page tables using just by fetching the CPU registers. However, if a page has been swapped out, then obviously you can't reach that. And this looks like something that would be extremely useful for that.
Yeah, but I mean, if you're just to make sure I understand, so. You're talking about a context where the observer is a JTAG external interface.
Yeah, essentially GDB attached to the Linux kernel.
I mean, if you have stopped the thread, I mean, it cannot go and do what is needed to enable the page fault. Right?
I mean, you can, because it can be, either. Well, we actually worked on the sort of intermediate probe firmware, so it could even work beneath GDB. Essentially, it could execute whatever it wanted. Yep. So we had some automation in that. If there was like a particular symbol exported via debug information, obviously from the kernel executable, you could the probe firmware could actually sort of like issue a call instruction to run that code.
Yeah.
So if there's like an entry point in the kernel that you can invoke this way to get the page faulted in, that it seems to me like something that could work actually.
That's actually relatively similar to what I noticed. The other talk I just did before was about the side EBI for user space instrumentation, and I have in mind to have hooks there so that GDB can attach to that static instrumentation. So that seems to be another instance in a different context of the same thing. So you'd like to have some kind of symbol emitted by those trace points that identify a location where an external debugger could connect and then do whatever it wants, without having to register a probe or things like that. It just wants to hook on a symbol. So that could be done. There's a use case for that.
Great, thank you.
So I'm wondering with this faultable trace points, if this would help strace, if they could be able to do anything to hook. We have the strace maintainer right here, so I just put a spotlight on you. We had that discussion about using Perf or something, and it never went through. I forgot we had. I talked to Linus about it, and this was like years ago, and he gave me a solution. I forgot what it was, and I was embarrassed to ask him again. So, but yeah, because the idea is like if a lot of people say that strace is slow, but if we are able to have like strace enable stuff, and actually it could just say, okay, enable perf or whatever, and it could do the memory maps or even ftrace. Ftrace now does memory maps too, and just read the trace and then have a way of saying, if the reader can't keep up, it will stop the process. So basically, instead of stopping the process, right now I believe ftrace uses, or strace uses ptrace, which is a horrible interface, and it's also quite slow.
Oh, got a point there. So, okay, so I have that kind of scheme in user space. Optionally, the user can specify when the buffer is full, block, or block for that much time at most. So, with faultable trace points, we could port that concept to the kernel, because if you're within a faultable trace points, you could block.
Yes. Yeah, and you could say you're allowed to block if you have ptrace. Like basically, ptrace can block any task. It can. I mean, if you have ptraceability, then we could say we could block.
Wait. There's a constraint there because you are in a task trace RCU read side, and the contract there is all the users need to play fair and only block for faults, not for other reasons.
But what we could do is if we have an issue where like, oh, we're like not doing this, we could actually. If we say, oh, we want to block, you just release everything, and when you come back, you start from the beginning again, knowing that you've blocked, and then you already got, like you said, you got the information. If it's not there, you throw away the event, and then recreate the event the next time.
Yeah, that will require more discussion, I think.
Yes.
Yeah.
Well, I mean, we got another 8 minutes. But no, yeah.
What I'm wondering is there a way, so let's say we're a tracer, we notice that our ring buffer is full. Could we postpone that to later so that we are not in the execution context with the task tracer CU taken anymore, and we kind of postpone writing information into the ring buffer to later? That could be return to user space or whatnot. So then we can exit the task tracer CU critical section and have some way to block the application at that point.
Well, I'm saying, okay, where is the RCU taken? I mean, sorry, where like in this?
At the sysenter, sysexit trace points, which are part of common/entry.c. That's the generic C code that gets invoked when syscall tracing is enabled.
So I'm saying if you set a flag like a task work flag, or I mean, though actually that would return back. We want to actually stop the task. So,
but you could stop it in the work header, right? In the task work.
Okay, no, I'm saying because you got to schedule it out. I mean, you don't want to go further. You don't even want to do the system call. You don't even want, so you can't, no, you don't want to do the system call.
Ideally not, yes.
Right, because you are going to lose all the information. You come in, you realize the ring buffer's full, so it means you can't write anything new. So at that point, you have to block. You don't want to even continue further. So but you could release scope, like set a flag or a return call or something. So the faultable entry code releases everything, and then puts you on a queue or something like that, or the ptrace queue, and say you're blocked right here as at the entry level here. And then the ptrace, when ptrace or whoever's recording notifies it or could then release it, gets a signal, or I don't know. We can figure out the implementation.
Some notification. Yep.
Some notification or whatever, or we could just hook it to the ring buffer thing. So when the ring buffer has we have space available, it wakes it up.
Yeah. I mean, we kind of need something that is, well, the ring buffer detects there's no more space. It needs to inform the current thread that as soon as possible it needs to be blocked. and associate that with a kind of wake-up signal that can be sent from
like I said, whatever,
outside.
like when you call, let's say, so basically the, oh wait, shoot, you're right. So we're still in, so the faultable trace point might have to have something where it says, we're go like release and go to sleep.
Yeah, because we cannot do general blocking in a faultable
right. So,
trace
but you
point.
still have
That's
a macro around it, right? Isn't it? You still have the trace points still have. I mean, the trace point for okay. I haven't looked at like I said, I haven't had a chance to look at the code yet. So my feel is, so you're using SRCU or
no? It's a task trace RCU. So basically, yeah. So if we block for too long, we're preventing reclaim of all those.
Right. So no. So I'm saying so. But what my point was, somewhere you call the task trace RCU lock.
Yes. Around trace point and callback iteration, right?
Yes, right. But that's in a macro or whatever.
Yeah, in the do double underscore do trace. Capital
So I'm saying in that code,
Yep.
that we have it there. This is for the faultable trace, and what is faultable trace point? We could have a return value or some sort of global, or not global, like task bit or whatever that we could set, that we would come out of it and said, oh, we
need to block. Yeah.
We need to block.
Yeah.
And repeat. So basically, you come all the way out, and you hit it. You will block.
But you may not want to repeat for all registered tracers. The other ones have
No.
already
It's a per task bit.
Yes, but per task is not enough. You need it per task per registered tracer.
No, you're going to block for every trace. Well, it's because if you're going to block for one, you're blocking for all of them.
But you may have already written the event in some tracers. The third one says, I want to block. So do you call again the first two?
Well, actually, I mean, you have the bits. So basically, you could have some sort of like CPU mask or not CPU, or like how many tracers, if you have a bit mask of all the, like, you have a bit mask.
But I feel like this is like a continuation. The tracer that wants to block says, after you've blocked, please call me back.
Right.
Rather than just restarting.
No, I'm saying is, what I'm saying is you have a bit mask that represents all the, like your array, you have your RCU array that you say, you just go down the array of call this tracer, call this tracer, call this tracer, have a bit mask of that. When whoever says, I want to block, you set that bit,
But that's per task. So you want to add a bit mask per task? I mean, the array is
No, so the task would have, I mean, how big is the array? I mean, how many tracers do you attach? Right now,
there are no limits currently.
There's no limits currently, but we could just have this thing be like default to 64.
But we'll see. I feel like this continuation might work better. I mean, if you just have a way to say, please block and call me back with this callback and private data when you're done.
Yeah, I mean, so basically it would be up to the tracer to say, just store this in a private, like, have some sort of temporary buffer for the task.
No, you have a linked list of things to do after.
No, I'm saying the tracer itself that's going to block, because it could say, oh, I don't have buffer available, have a temporary place to put the event information, and then when you get called back.
No, it would be called immediately after having unblocked, still within the syscall entry code. So you're still at the right point.
Oh, basically, instead of just coming back into the loop, you just say...
Yeah, do this specifically. Call me back with this pointer after you've blocked. And block for...
So if you have 5 of them, you have to have a list of these.
Yeah, exactly. You got it.
And you have to do that per task.
Yeah, you got it. Yeah. Are we done?
Well, almost. Well, maybe. Anyone else?
Oh, one question.
But I didn't really follow. There was one thing I missed. At some point, Matthew said, wait, the contract in task trace RCU is that you can block, but only to fault.
Yep.
And this was not allowing for the idea of Steven. How did you circumvent this limitation? You seem to have it figured out, but I missed how.
So the idea I have, and then we have to look at the details, right? We might be a bit wrong there. But the idea is tracer notice it would need to block because its ring buffer is full. So what it could do is basically enqueue a function that has a pointer to its own data to be called after unblocking. And then it would basically set something, a flag or something that tells the trace point code to block after having completed the iteration calling all the tracers. So basically then when we complete iteration, release task trace RCU unlock, then we notice this flag, we block, we wait for something to wake us up, and then we look at the queue of things that were registered on the task.
You block after you release that trace, the RCU.
Yeah.
Yeah. Yeah.
Yeah. The requirement is we can't go back to user space.
Yeah.
We could block. We could when we say block, we could stop, but we can't go like we don't. Yeah, we can't depend on user space to.
Yeah, but I would say that ideally we would like to block within the syscall entry code, because I mean you could have side effects within the syscall that end up modifying the input arguments you wanted to look at. So that's where you want to block.
Just a comment. So that I will just comment. I will expand that T probes to say that so that refer that system call parameters or something like that.
Good.
Yep.
Excellent. Thank you. All right. I think we're out of time. Thanks a lot for all the feedback.
Thank you. Now I think we're entering the real-time portion of the tracing session. Okay, thanks everyone coming. This is tracing related. It's actually more somewhat safety critical validation using the tracers. So this is on the runtime verifier written by Daniel Bristow. So what is the runtime verification? So basically the idea is this. You create a model in, you figure out what your system is. And you're going to create some sort of model using Autonoma and a state machine. You write it up in a special format, you're going to compile it, and then you're going to put it into the kernel. It's going to hook to trace points. So the only thing that this is really related to tracing is it uses trace points. Okay, there's no ftrace itself, although we have ftrace is sometimes used in some other things, or LTTNG or Perf or anything. No, it's actually using the trace point infrastructure. Okay, so I'm going to go in for terminology because some people get confused. Like, well, what's the difference between a trace point, trace event? A trace point is just the hook in the kernel. There's nothing exported. When you look at tracefs, you don't see trace points. You see trace events. Trace events are infrastructure that hook to trace points. When you create a trace event, the trace event creation will create a trace point that it's going to use. So like the sched switch trace event is what creates the sched switch trace point, which is what you put in the kernel. So inside the scheduler, you'll see trace sched switch. That is a trace point. All it does, and this is mostly Matthew's work, is it will, that's what's called the static branch or jump label. So when it's off, it's a no-op. It's seriously a 5-byte on x86 5-byte no-op, and when you enable it, it turns into a jump. So there's no conditional branch unless you go into your menu config and you say disable static branch, which I'm going to talk about as recipes. Go on.
So I participated in the initiation of those ideas, put the people together, but I'm not the one who did the compiler implementation in ASM GoTo and all that stuff.
Oh, no. I'm saying, you basically wrote, I'm saying that okay, the static branch, I didn't say that's static branch. Yeah. No, I'm saying the trace point infrastructure has the RCU, do trace, and all that lovely stuff. I mean, you and I worked quite a bit together on that one. But no, that's like Peter Zylstra helped a lot in the trace point. So basically, a static branch, I mean, the ASM GoTo that's in GCC and Clang and everything, that came from this idea because we had trace points all over. Trace points started growing all over the kernel, and we're like, we need to make this faster. So we need a way to put in a no-op, but you can't go in ASM and have a jump to a label from ASM. Because GCC could do some really crazy things, so we need a way to tell GCC that this ASM, because in GCC if you do an ASM, it's just some blind, it doesn't know what it is. You can do whatever you want. So if you have a jump, you have to have a constraint there that says, hey, here's a label that this code or this ASM blob might go to. So GCC knows. So what we do is we put just 5-byte no-op, and then later on we dynamically change that to the jump to the label. And so it doesn't bother the branch predictor and stuff like that. And it has by the way, if you turn off static branches, I found out that's and then just run your hack bench and stuff like that, it's like a 5% slowdown. So last I did a thing on that. So it's a very, very fast thing. But yes.
But it's not only used for trace points nowadays. There are many fastpath that use AS.
Oh yeah, no, basically KVM. When you boot up KVM, something like that. But that's going off. Anyway, for the runtime verifier, it's very, very fast. So when we have a jump, you jump directly in, and then we go into the trace point infrastructure that could do callbacks. So that's just a trace point's just a way to do callbacks randomly in some static point in the kernel. K-probes is a way to dynamically do it. K-probe is where you say put a probe, where it just says jump to some code at some random spot in the kernel. So Daniel Bristott, through his PhD and stuff like that, came up with the idea of using this information to validate the running of the kernel. And what you do is you create the autonoma, you compile it, and it will load it as a module. It would register to trace points and sometimes K-probes, and then it would create a state machine. And when you get the information back from the state machine, it would just move it to the next state, and move it to the next state, and move it to the next state in your model. And if there's ever a time you go to a state that's invalid, then you do a trigger. And you could do just a print K, a warning, you could crash the machine. So the automotive industry is very much using this to validate. So they put this in, and what it does is for autonomous driving, and if it's constantly making sure that the kernel is doing what it expects to do, and in any case that it says, oh wait, this isn't what we want to do, crash, it actually panics the kernel, because that will put it into a safety mode. And so basically it will let you pull over nicely. So, like I said, it starts off with the autonoma, discrete event system. So if you remember your CS courses back in college and all that, I used to love these things back then, but since it's been 30 years since I've been to college, I don't remember it. But here's the workflow as I mentioned. So you create this dot file that he has a way of turning it into some code that you put up, and then you compile it, load it into the module, and this is how it works. So he has an example in there called WIP. And I keep saying, is it work in progress? It's the worst acronym. It's a joke, and he just left it there just because he just loved to troll us. So work in progress, no, it's not. It's wake up and preempt. So here's the very, very simple example. The idea is when you have preemption enabled, you want to know hey, I want to record if I have a wake up in a preempt section, I better not schedule. So he actually says, okay, so I keep track of my state, whether I'm preempt or non-preempt. Preempt, non-preempt. So that's basically, he has this little thing, so every time, if you're preempt enable, preempt disable with a flag of the counter, so if it could actually, probably should it should be non-preempt could stay in there as well. He probably should have had that in there where you could go from non-preempt to non-preempt if the counter's up there, but anyway. And when a sched wake happens, it better go back to the preempt section. It doesn't get out. So, I don't know how easy you could read that. The font isn't the best. But this is the dot file that represents that information. It's not that easy to understand. In fact, this is one of my asks, because I said, where do we have to go from here? One of the problems with things like this is, if you have something that's complex, no one will use it. This is one of the things he was working on. He was working on trying to have ways of making this easier to write. And I'm almost asking if anyone knows or of helping ways to say, hey, I could use a diagram and make this easier to write, because this is the work in progress. It's a very simple thing, but there's still quite a bit of code there, or sanitation. So he has inside the yep. Oh wait. Yep. Yes. Sorry. Yep.
I think there are applications to actually, from a graphical representation, to actually produce the dot file. Okay. Yeah, I think there are, but
hold on to that because you might be needing. Yeah, I asked him to be my backup because honestly, what's it called? Like I said, you know what? I trust you, Daniel. So I didn't really review it as much as I should have.
kind of the same situation, yes.
Yeah. So to enable like this, if you go into like kernel hacking, tracers, runtime, you can enable runtime verification, and this is the menu for runtime verification. The code is already in there for the work in progress. So this is the module code that you have inside. So you run the little, let me go back there. Oops. Yeah, so this is actually, when I ran his script, like in the tools, or was it? Yeah, it's tools verification directory. He has, this is a Python script. I believe that you could just run on the dot file, that first dot file. It creates this file. It's the code. I think it's almost pretty much complete that's up there. So it's not like it creates the code for you. And this becomes like the header file for your module. And when you go into your, like, so if you want to create a module to put it in, here's the module, you include that header file. And it's not, this is actually really simple code. You just have to go here and attach the trace, what's it called? You want to attach the trace points to your callback functions in your module. So it's a little bit of manual stuff, but this is kind of, it's all very much, it could definitely be automated. All this could easily be automated. Right now it's done by hand, but it's not, it's just basically just, I need to do X, need to do Y. So it's not something that takes really much brain thought to do. It's just making sure you do it correctly. So something that could definitely be automated. Here's the second part of the module. And when you execute it, that's all it is. So I think it's like my last slide, because this is where I kind of like want a discussion and stuff like that, is where do we go from here? This is, I believe, work that will be extremely useful. So Alexander Arling, the one that gave the talk earlier today, he actually came to me after one of our tracing meetings, like, Steve, I have a question for you. I need a way to verify DRM. And I was thinking, hey, it would be great if I hooked to the trace points and have some way to, as it's going through and running and validating the trace points, or validating the DRM code through the trace points. And I'm like, you just described a runtime verifier. He didn't know about it. So he looked into it. It's like, actually, he's like, this is great, because like, I don't have to write the code. I could just use this. So he's working on it. So if there's anything like in the kernel that you want to do verification of, so you can validate this. And by the way, in his PhD, Daniel's PhD, he basically he successfully proved the correctness of the scheduler. So the Linux scheduler has been proved correct after he fixed 2 bugs in the process. So his verifier found 2 bugs in the scheduler, because when he said, like, wait a minute, this isn't right. So basically he validated that it was incorrect. And he sent it. It was like it was really, really subtle bugs. And then when he sent it to Peter's Illustrator, Peter was like, yeah, that's a bug. And he fixed it. So he actually found 2 different bugs while validating the scheduler. So people said, like, the Linux kernel is too complex to validate. Well, we got a methodology to kind of do that for us now. So I guess, Yuri, you said that there's already application for the dot files then.
I believe there are. I believe while essentially studying the stuff that I saw them mentioned. So that's one thing. I'm not entirely sure if there are kind of open source, maybe like tooling used by the researchers for kind of working on automata. So they might be interested, if they are not, of course, to have something open source that does that. I guess continuing on to like ongoing or interesting things to do. You mentioned the BPF. So Daniel has already a repository with an auto3 implementation of the .2 BPF. So instead of creating a module, you create a essentially BPF instrumentation, and then you load into the kernel, and then you get the same results.
Yeah, but there was, I remember the Exist, did he fix the issues? Because when he first did that, everyone says, why don't you do this in BPF? And he said he tried, but it was extremely difficult and he couldn't quite get it right. Or something was with it, that there was something with BPF that he wasn't working. I think he said to me last time in OSPM that like he fixed it or something. I don't know if you remember. Yes.
So I imagine you might have several, let's say, instances of these state machines. Are they implicitly associated with a thread, or what's the deal?
So yes, you could have several things. So when you register, when you hook the state machine up, like the one thing about trace points is you could have multiple callbacks. So on the tracing side, I could have ftrace reading the sched switch. LTTNG could read the sched switch. Perf could do it all at the same time. It just creates an array and just does a bunch of callbacks. Same thing here. If you had like 10 state machines, it would actually be individual, I believe, right? You could individual state machines when you put in there, and it only cares about what it hooked to. So yes, you can have multiple state machines going at the same time, hooked to the same trace points.
Yeah, I'm kind of wondering, so in the binder driver, I could see some places where you could have a state machine per process using the binder driver.
That could be the case, but now the only thing is you have to watch out for, which is talking about performance-wise. If the thing is like when you, like you said, the trace point is a no-op when there's nothing hooking to it.
Of course.
When you have, I don't know, you probably want to do measurement. It matters how many trace points you have, but if you have something hooking to it, and then you say per process, and now suddenly you have, I guess it won't know. The trace point won't know that, only call this guy because I'm running this process. If you have 20, I would believe that if you have a state machine where you say only care for this process and you have them all hooked to say 20 processes hooked to the state machine, it's going to do a callback to all 20 guys, and only one of them is going, all of them would say, I don't care. It's going to do kind of filtering. It's going to get the callback saying, I don't care about this, boom. Now what we should do in that case would be, if this is an infrastructure we do, maybe we do the multiplexer in there so it only registers, you have a single, let's see, the runtime verifier, you register the runtime verifier registers like one callback from the function. So that way it will know, this thread only cares about this and says, on this thread, call that guy. So it doesn't do a callback to all 20 of them, and each one says, I don't care, I don't care, I don't care. So we probably would need, that's how K-probes hooks to, stuff or at least for function tracing. For function tracing and stuff like that, usually you just, you just have K-probes that, if you have two K-probes, like function graph tracing, if you have two K-probes that's going to look at two different functions, it will register a single callback, and the K-probe mechanism does the thing. Yes. Microphone? Yes.
So why don't we save the state machine per task, so that we can make define that per system, system-wide automaton, and also per task automaton, because that
I might be wrong, but I think there are at least 3 different monitors type. There is a per CPU, per task, maybe already. So that's probably already possible. I think, again.
Hello, I'm Matthias from Red Hat. And I think you can generate the dot files from a simple language, for example, if you want to describe the state machines. I mean, there are thousands of languages to describe state machine. And we were discussing about this with Daniel 3 years ago, actually. And also, what I'm planning to do, I'm not sure yet, but I wanted to use the runtime verificator for Virtio drivers. Because in Virtio, you have the specification, you have things that you can model with state machines. So it's just about to write a runtime verificator to detect violation of the spec. So there are situations that could be modeled with state machine, not everything, but at least a part. I'm going to present something later about that, an issue that we found that potentially could be, detected with the runtime verificator. So that is my plan at least. Let's see where I go.
Oh, wait. Oh, we have. Whoa, Hold on a second. Alexander's in there. Yes. Okay, Alexander, you could.
I'm using it already, but my use case is not very for production. I'm using it more for testing that if I do some changes for my logging subsystem, that the logging correctness is still valid. And there where I was introducing not a pair task struct verifier, I was introducing for a pair log verifier. And then I can, but I was doing it that I was able to see if exclusive log was used at the same time, and then I panic or I put a message out. That's what I'm currently doing. But I would like to have some way to, okay, when I panic or I print something out, I know I got into an invalid state of my automaton, which I was describing in dot. But then the way how I was going into this state, that would be interesting to debug afterwards.
Yes, one comment on this, Alexander. Hello, my name is Giovanni. I'm normally matching things I heard at talks, so I never used the Linux kernel memory model by Paul McKenney and co-authors, but for verifying the correctness of locking, that is at least described as the tool. So it has what they call litmus test. It doesn't take your source code. You have to extract the essence of the locking that you are doing. You have to write it in some, it's not pseudocode, it's a different smaller language similar to C, and then you run it through the tester, which has implementation of the Linux kernel memory model, and it kind of it does an exhaustive exploration of all the possible states, and it will tell you all the things that could happen. So for locking, the Linux kernel memory model seems more specific to this case. It's in the kernel. There is a. Just wanted to say, if you want probably to Google LKMM, Linux kernel memory model.
Okay.
Can you go back to the slide where you have the state machine? Because your explanation was completely wrong. So I just want to go back to there. So I've just looked at the code, and I was like, waking does not do that. Okay, so what it validates is that sched waking is always called with preemption disabled. So in try to wake up...
Wake and preempt, okay, you're right.
Yeah. So in try to wake up, there's a preempt guard first, and then it does all the sched waking calls. That's what it validates. It has nothing to do with schedule, with preempt off. That's the opposite.
I think the thing was like when we first did this, I actually talked to him about doing that, and he's like, "Oh yeah, it could be done." And then I just was assuming that I didn't actually go back and look at the code.
2 points on the validating the locking. Depends on what you want to validate, I think, because as far as I understand, the memory model thing validates if you have like race conditions or if you're using your barriers not the right way. For example, one thing, an additional use case I was thinking of, this is related to the proxy execution discussion that we had yesterday. So for sched deadline, for example, the moment you implement a locking mechanism that does the priority inheritance, you have, for example, for RT mutexes, you have the lock depth, of course. So that validates that you actually have, you're expecting the dependency, right? For deadline, you actually have to respect the temporal isolation among tasks that the theory that actually tells you what's the property you want to validate, and I think that's fitting more with the RV, and I don't think that's something you can do with the memory model thing. So it depends on what you want to validate, and that's another use case. And going back to the overhead, I think, so you mentioned that Daniel essentially used this for validating the scheduler and the preempt RT essentially, and he was saying that the overhead for doing that was really low. So I think it's essentially
yes, it's very. My worry was if you have 20 callbacks. Like I said, if you have, I mentioned like having a per process.
Right. Yeah, it depends on how you use it.
That means you have 20
but,
validators.
Yeah.
You know, yes, it could be very slow. Maybe, like you said, it only adds maybe, maybe like I said, let's say if it adds 100 or let's say 5 microseconds. But if you put 20 in there,
yeah, I guess it depends.
That adds up quite a bit. So, Alexander, did you raised your hand? Did you have anything?
Yeah, it's just that my use case is very special because I'm verify here a distributed log manager, and yeah, I don't. But I'm doing, of course, I'm not validating my own source code. I'm only having trace point to the actual user calls, and then I simulate everything over net namespaces to have each node acting like this. That I see a global view about my network. That's very connected with my previous talk with distributed tracing. I'm doing that currently with net namespaces, and then I'm validating it. I'm not sure if I can use logdep or something like that for this right now.
When anyone leaves, I forgot to do my beginning obligatory selfie. So everyone smile. I'll do both sides here. Smile. Yep, I should have done your camera. Yes, actually, let's do it. Okay, so this is, okay, there's a story reason why I use a camera is I've been doing this since 1984, doing this with the old yellow Kodak cameras. And he actually has a film camera. So the idea is to do this with the actual film camera, so you don't get a second chance or validate that way you get. So everyone smile. Wait, is that one right? This actually has a focus. It's like not. It's a manual focus. Smile. There we go.
I don't think we were in that photo.
Yes. Thank you very much. The which one?
I couldn't find it on Google Scholar.
I think if you go to bristot.me, his webpage, I think he actually has it. I think I found it there. So his last name .me.
That is
so. Oh, Daniel Bristot. That's the guy who.
Yeah, I don't know him, so I don't know.
So if you go to
Please have to know that.
Yeah. So I'm going to download.
Do you have a second at all?
Yeah. But actually, yeah. Before we do that, I want to copy all the notes to my.
Okay.
And somewhere under links. I don't know if okay, I'll tell. But if I lose it, it's because I just warning you.
Finally generated by because so it's if it's up there, if it's up down, but if it's up there, then people just sit down to
and eat it right there. Okay, I'll do that. I just have to download it.
Yes, actually it's been details that does it. Okay, fairly recent months of AI. Well, no, so we should be able to just get this strength section added. But the one thing, the support we need in GLC is to, and that doesn't exist today, is to have the loader. So currently I think you can do a string on the LPC universe because the kernel knows about all the sections, right? So the program per se, that's fine. The libc support will be needed to register the strength section because that the kernel does not know. Yeah, those are the two main targets, I think. Maybe others. I've seen in the talk earlier in the Cauldron interactions with the S390 guys as well. So I mean, because they have to know the ABI of the architecture to know what are the registers that are useful, how the offsets are done, and everything. So there's a bit of discussion there. Things like S390, they have some snippets of code where it's kind of not really possible. They kind of move the frame pointer information into some register copy. So in those cases, they need to have.
I would have said one more time that it was like.
The compiler to a subset of its possible ABI so that it does not compose the ABI. But it should have very limited impact on very tiny areas of code. So that
Yes.
And the actual strings
my next
in some cases,
so actually something of first. My point is, it's hard to learn, so we should clean this up. And my opinion is, know about it and get people to write these, and we should decide how to know, right? Because I think getting people to clean interfaces that are like when I'm getting my hands in and I see how ugly this is, I'll be like, hey guys, you know, the DRM is also doing it, and that other guy wanted to do that. Say, we need to talk, and how can we make this easier for us? Right?
I'm the best.
Oh, yes. Okay.
Yes.
Thank you.
Yeah, my point was just promoting the feature and not promoting we need someone to clean up the API. Or you
Don't want to forget this either.
The barrier.
So is it lunchtime?
Yeah, so
Let me just focus on promoting the feature.
Yeah, I wanted to do it well.
Okay. I'm at okay. Let's say now I recognize. Yes. Oh, nice to meet you actually. So I'll be around. I'll be at the safety critical system too. But yes, and you're the one who did all the OU, the Rust traceable stuff. And as I messaged you, wait till October or beginning of October, I would definitely try to get time. It's pushing up into my priority list, but because of everything that happened, I just.
Yeah, I know. It's not great.
Okay.
Yeah,
say he got promoted to VP and he was over all you guys now. I wouldn't buy it. But like I said.
It wasn't like alternative 3 was actually readable. No. I could, yeah, me too, I wrote it. But I couldn't read it and see now what alternative 3 was. Yeah. So from a user perspective, I think the recursive one is actually easier to use than the alternative 10. So the both guys, they were faced by alternatives. They didn't really know what to do. Well, this is post-jump optimization. So they do a profile of your kernel, and then they take the else image and re-interpret the text. Like they reconstruct all the basic blocks and control flow and everything. And then they will replace it. So they use the functions and the placement, so they get all the hot parts near to one another, and they optimize for non-taking branches or full taking branches. They do a lot of crazy stuff. Can we use the alternative stuff? Of course we do. Not only but they weren't quite sure how to deal with the alternatives. And what the only option you have is, because currently they ignore the complete function. They first an alternative and they fail. That's another function? Yeah, that's about 10% of the whole code. It's like static binding notation. Yeah. And I said you can, a better approach would be to just ignore the few instructions that are
so that's the first step.
Involved with the problem is alternatives are involved in the code flow. There is jumps inside.
So if you do the plus, I got them all in here. They're just called.
Then you need to record the alternative that was in effect.
So starting session 1, and not those are all ours. Cool.
And still not touched.
So I'll just go.
Yeah. So at that point you must also record which of the, it's easy to know for runtime which actual. So record that and then.
Yeah, we do keep it on time. But yeah.
What's that?
We'll tell we do keep it on time. We're not going to have it.
Yeah, I should talk to Keys Cook. I only thought about it today. I'm so focused with it. Thanks.
So you just switch here. How do you switch?
Do you see the arrows or
Oh,
can you
yes.
But I told them that we changed the metadata associated with alternatives.
I guess we'll have to make how on present. What if you control it from this side?
I think if you're a presenter, it becomes. I mean, you don't know the clicker because they're gonna stand here anyway for the mic. So. If I make somebody presenter, how do I make somebody presenter? Just go right click, make presenter. What is the output is there, right? Okay. Yeah, that's that window here. That part of the window is there.
This whole thing is mirrored up to all of this.
Okay.
Well, my only worry is they say if you're not careful about copying it out, that they'll go away. So maybe we should keep it somewhere else.
Put them in a text file. It says here authorization required.
Oh, okay. I don't know about that, but I can push them up from my computer.
Okay.
So I just, so you have a blank space again.
So Zen 6 will be good, right? No speculation issues. We've learned, yeah, I know. I've been asking the other
I know.
Okay, well, I guess the shared notes made their feelings clear.
You want to present it? You want to start or should I start?
But universities are doing a great job. It's on my phone. I had to buy a new phone because my old phone died. And this is just a junky Samsung something 15 or something, I don't know. But yeah, it has this feature. So in the bulk stuff, they will ask me in the 2.5 years. It's not easy to remove them, so when they go buffy, you really need to dispose of them. And they had a nice picture of someone They have this little CRT monitor inside the floppy drive. No, 86, it's 8086. Well, supposedly it's still inside of there somewhere. About the 8086. Okay, Boris was saying that he wanted an old laptop. So I reminisced about the briefcase for luggable machines, the deals and the 8086, the built-in CRT monitor, the two floppy drives.
I think the first one was the Osmo
Okay, so I missed that one. I wrote the program on the 8086.
No.
Amber scripting and stuff. Yeah, that legacy is still in the chip.
I think you need to see if you can hold longer. Yeah, for sure. Where are we supposed to sit? Okay, well, we don't have our first presenter yet, but we could just go out of order. I'm happy to do mine, get it over with. So, nope. Well, okay, well, I guess we can get started. Might as well start on time. Okay, everybody, welcome to the x86 microconference. My name is Dave Hansen. I work at Intel, and also to help organize this microconf, Boris from AMD helped. So we tag teamed this one. We figured it was a nice even way to split. The two major vendors get each pick a couple of talks. So I am a kernel contributor and one of the x86 architecture maintainers. So we picked a bunch of stuff today to go over, kind of things that we want to chat about. But a couple of ground rules. We want to make sure the presentations go quick. So we're thinking roughly 5 minutes to go through these slide decks, and then we're going to stop you and hopefully chat for a while. If the things end early, that's great. We'll have more time for breaks and chatting in the hallways, and then we can get a go and drink beer earlier tonight. So. And by the way, the whole reason we started this is we looked at the topics from last year, and people got microconfs, and we're like, RISC-V has a microconf. We can have one too. So that was our whole motto. Anyway, so we do have our first presenter. Pawan, can you unmute yourself, and we'll double check that we can hear you in the room?
Hi. Are you able to hear me?
We can hear you.
Okay, great.
Let me make you the presenter, and that should give you access to change the slides around. You want to give that a shot, make sure you can change it? And then I'll let you go.
Okay, all right.
And just remember, we're going to want to spend about 5 minutes on these slides, so and hopefully get to the questions and discussions pretty fast here. So welcome, Pawan. Go ahead and go.
Thank you. Hi, my name is Pawan, and I'll be talking about CPU side channels and the channels, the MIDI challenges that we face here. Sorry, I'm still sleepy. I'm in US time zone. Okay, so who am I? So I am a Linux kernel engineer at Intel. In the past, I've contributed to mitigations for BHI, TAA, RTS. Red Bleed, MMIO, and a few more. Okay, so quickly going on to the main agenda. So why we are here I'm talking here is because I want to present what are the challenges that I face, like I'm currently facing on mitigating these CPU side channels. So the first one is sorry. The first one is the trusted workloads. They do pay the penalty of due to these mitigations. While I'm sorry, can we switch to second one? I'll be back.
Press down at the bottom to move back and forth. Oh, I'm sorry. Okay, sure. I was not quite grabbing there. Okay, let's go ahead and do that. We could. I'm all ready to go, and I'm ready to get mine out of the way, so we can just do that out of order. I'm going to take. Let's see. I think. Let me go ahead and make us presenter again. Oh, there we are. Okay.
I didn't get enough sleep and I'm back blanking out. Sorry, so sorry.
Okay, no big deal. We'll just do this out of order and we'll come back to you in a little bit. Okay. I got to take the first one. Okay. So I wanted to talk today about the future of memory protection keys. Again, if you weren't in here 3 or 4 minutes ago when I talked, I'm Dave Hansen. I'm from Intel, and I'm one of the x86 maintainers. And protection keys is one of my favorite things because it was one of the bigger features that I got into the kernel kind of earlier in my career. So I'm a big fan. We'll give everybody the kind of the 10,000-foot view of what memory protection keys is. Basically, we take a key and assign it to some memory mapping, and we do that in the page tables. Basically, you put a couple of bits in the page tables, and that assigns a particular key to it. We do this with kind of a special mprotect call, like in Linux. But the really cool thing that it lets you do here is once you've assigned the key, you can change the permissions on the memory without changing the page tables. So changing the page tables is really expensive. You got to go in the kernel. You got to do TLB flushing and a whole bunch of other real expensive, slow stuff. So protection keys is really, really cool because you can do that. You can change protections on things by just flipping a bit in the registers. Pretty neat. What it does also is it gives you truly thread local permissions on something. Because right now, if you have shared memory between 2 threads in a process and you change the page table permissions to take permissions away from it or give it more permissions, everybody in the process, every thread has the exact same view of memory. So since this isn't a register and every CPU has its own register, every CPU can kind of have its own view of memory. So it's a pretty cool little feature. And like I was saying, it's way, way cheaper to just flip some bits in a register than to go into the kernel and flush TLBs and all that stuff. So it's way, way faster. The other really cool thing about protection keys is that this started off being an x86 thing in, I guess 2016 is when we got it merged. But there are similar enough features on PowerPC and on ARM. And I think there's some more out there. It seems like this is more common than not. But these are the ones that are in the kernel. So we have 2 other architectures that are able to basically reuse the same ABI. They're not exactly the same. Like x86 lacks the ability to deny execute support on memory, while the other guys have that. But otherwise, it's pretty similar. And it's pretty cool that we were able to take this x86 focused feature and system calls even, and the other architectures can kind of just reuse them. So it's been pretty cool. So, but it hasn't all been sunshine and rainbows. The register that we've got here on x86 is called PKRU, the protection key writes for user space register. And it is saved and restored using the Xave mechanism, which is also used for stuff like the floating point registers. This seems like a pretty good idea, except that the floating point registers they can be used in the kernel, but they're not used very often. And PKRU affects memory accesses. And so user space accesses memory, but the kernel also accesses user space memory. And so it turns out that this is the one bit of state that's managed by this Xave mechanism that is controlled by user space, but affects how the kernel executes. Because if you change permissions in this register, the kernel can actually fault when it goes to touch that memory. So this turned out to be really tricky because it's the only one that does that. And so when you want to do things like, hey, maybe we want to optimize our floating point save restore, and we want to wait a while to go restore our register state. Well, we want to wait a while, but we also don't want to delay, enforcing these permissions on the memory. So it turned out to be a little goofy, and turns out that it is a special snowflake in the Xave handling because it's the only one that does this stuff, and so it has its very own special code. But people have wanted to kind of expand how they're using this. The ABI has been around now for almost a decade. It seems time's flown. But people recently have started to look at hardening applications with this. And actually, this just went up to Linux this week. But there is this, people want to be able to take it and have some threads that have access to memory and some threads that don't. And they're actually wanting to run things that are more exposed. Like maybe they go parse some user data and you're worried that somebody might take over that thread. So they're going to go and try and deprivilege it with this mechanism. Except, when we enter a signal handler, we're trying to save the old register value so that the signal handler can see it. But at the same time, we need to write to that register to make sure that we can actually save the stuff off to memory. So we get into kind of a loop here. So I wanted to talk about this particular thorny problem, but it's been merged since I wrote the slides. So I don't know what else we're going to talk about. So thanks Thomas for shepherding that in if Thomas is around. But that's mostly done. But the really important part here is that it should be in shape where people can start to do deprivileging of user threads. This is not completely foolproof. This is not like a hardcore security feature, but people really think they can build things with it. So I just want to give people a heads up and say, maybe something you want to look into. So there's also an emerging set of problems that we have with protection keys assigned to memory. Because usually when you're sitting there in your user application, you write to memory, well, you got a CPU and it's doing a memory write, and you've got some page tables that you're writing to, and you might get a page fault. And you can say, oh, look, we had the register kept us from writing to that memory. And it's really handy when you have both CPU registers around, and that memory that you're writing to. But there are a bunch of cases where we don't actually have the register available. We have, for instance, APIs in the kernel that will go and get a reference to physical memory, and then go fling that off into some other subsystem, and the registers don't go with it. So we have memory that we're trying to write to or read from, but we don't have the register. So we have this PKRU register. What do we do when we've got memory, but no register to tell us if we're allowed to write to it or not? So we've kind of punted on this for now. We've just said, hey, if we don't have the register, we're going to let it go through. What could go wrong?
So physical addresses have a few spare bits.
They do have a few spare bits.
They're getting awfully overcommitted.
So, but there is also a problem here, is that like we have our get user pages mechanism, and or PIN, right? We have our short-term and long-term ways of getting access to physical memory, but it might have been.
One thing that's probably worth saying for people that aren't aware, this feature was put together partly in response to the original Heartbleed. So it was specifically designed to prevent accidentally calling a syscall on a piece of secret in memory that you didn't really want leaking out into the world. So it is by design that the kernel can't access it unless it's decided it's okay to access, which is why you get all the other problems with just passing the pointer around without the protection key with it.
So even if we could take all of our physical addresses in the kernel and take a protection key and kind of associate it with that and pass it around everywhere, we still have a lifetime problem because the get user pages could have happened long, long before the permissions got set. Use pages can last a long time. It can last, forever, essentially. It can last days or weeks. And the register could have a very different value now than it did then, and that can happen in both directions. So even if we could plumb it around, I don't think there's an easy answer to this one. So if any people have ideas on how to deal with this or how they think it would work in their environments, I'd love to hear it. But for now, we've just said, there's no register. You can do whatever you want to it. So.
Just like a quick comment on that. It's like, when you have code parse that you get user pages to grab references to pages, you can even have situations where by the time the page actually gets written to, like, it's been completely unmapped from user space or stuff like that. So it kind of seems to me like it would probably be a good idea to say that the permission checks happen at the point of time where you do get user pages, and then from then on, user space is basically delegating this access to its future self or whoever else actually uses the page reference. I think that would probably be the cleanest mechanism, right? Unless there's like some annoying reason why that doesn't work.
Yeah, that sounds about right. And so what we actually do today is that when we do the page table walk, we try and enforce it with the copy of the protection keys register that we have at that time, if we're in the current process and we're walking it that way. But there are some really thorny ones, like if you're doing, if you're running a debugger and you're poking into the process from a remote debugger, that process's rights register has really nothing to do with the thing it's poking into. And so there are cases where we really don't have any, the register that you have doesn't have anything to do with the memory that you're accessing. So there are some cases where you really just don't have a good clue. Or the really pathological case here is, if we have something like a device, and we have devices now that can walk the CPU page tables and access memory. So some of those devices, they don't have one of these registers at all. So, who gets to be to choose in that case? So what key do they end up using? They have no enforcement of this. It's not enforced at all on device accesses.
So with the talk of VTPMs, is there any way we can just implement a VTPM on top of these primitives?
I'm not quite sure what you're asking. What, VTP? Go ahead. Explain more if you could.
Well, a trusted address space within the kernel that's not just exposed to whoever wants it, but...
Oh yeah. So actually, that you're kind of skipping down to my last bullet here. Like I had on the last slide, what I've been talking so far is about protection of application memory. So this mechanism, the architectures, all three of them that we have so far, all three architectures that implement something similar, can protect kernel memory with this. Did Ira come back? Nope. There are patches. There are patches that do that, that have implementation to protect some stuff in the kernel. It is, again, it's challenging because stuff in the kernel is always annoying, right? But interrupts and trying to maintain this state as you're going around to different contexts gets pretty annoying. And even keeping it up to date and making sure that you're enforcing it when you want to enforce it and not when you don't. For example, does the protection key register, does it go with the CPU that you're running on? Like, is it for the CPU or is it for your task? Well, it kind of needs to be your task because the thing you're accessing can't, like if you get preempted, you wouldn't want the rights to change like in the middle of a preemption point. So it is new state that you have to track and kind of bring around with the process like any other register. But there is an implementation out there. Ira Waney wrote it, and he went looking at trying to protect page tables, I believe was his first try. But yeah, we'd love to see some more kernel work. If somebody picked that back up and tried to get it merged, I'd love to see it done.
It's worth saying that the protection for user and protection for kernel are in different processes because that got missed.
Yeah, and by the way, there is a different register that the kernel uses that tracks its permissions versus the user space one. They're totally separate.
Hey, this is just a small point, Dave, but on your previous slide, you said 4 keys, but isn't it 4-bit keys?
It's 4 bits.
Correct. Yeah, actually, I should have said bits of.
Okay.
Yep.
All right.
Correct. Yep, my slide is totally wrong. 2 to the 4. Yes. I would add space for it, but yep. Thanks, Gil. But yeah, I'd love to see, there's a bunch of stuff that we can do in the kernel with this. So I'd love to see them pick those patches up and do some stuff with it. There's probably a lot of hardening things that we can do, but too many projects, too little time.
So it's worth saying that I have the project I was looking at for protecting the direct map with it. So you can leave the direct map no access unless you're in a copy to from user. I haven't seen how well that nests. That is an exercise for future me, but that was certainly where because it allows you to get a lot of the address space isolation for quite cheap, which is a whole lot easier than rewriting memory handling from scratch.
Yeah, and there was some talk in the confidential computing, or actually must have been before that. We were talking about MFD during the KVM sessions earlier, and people talked about taking some of the confidential computing mechanisms and making sure that we remove from the direct, user VM data from the direct map. And so one thing you could do is instead of making it totally read-only, you could just protect it with one of these protection keys, and then when you need to access it, you can turn them on and off. It might allow for faster transitions and things. Well, maybe not transitions between shared and private, but it would at least allow you to get access to it quickly if you need. Okay, any other questions? Comments about protection keys? Any questions on how it might be used? You wanna?
Actually, I have one specific question. Actually, in the KVM, I find one. There's might be one issue, is that when KVM trying to access a page, right? There are several situations. One of the situations, like it will grab the page table entry if it does exist. If it doesn't exist, right? I think the protection key is respected. So therefore, which means that if the user memory is not say readable or not writable, the fault will, there will be a permission fault. However, there is a special case if there is already page table entries in the host, right? And KVM at this point trying to access that page, then it will go to a fast gop. That fast gop seems not respecting, protection key permissions. So are we going to try to fix that, or
are you thinking
no
there's a
intention?
bug in there? Like, you looked at it and you thought it wasn't respecting it?
I don't think it is respecting that. It seems to me like it directly grabbed that page table entry.
So it is well hidden. Kirill, are you in here somewhere? No, Kirill. So Kirill was asking me about this last week, and I actually went and looked at the fast and slow gut paths, and I wrote it, and it took me about 20 minutes to find it. So I'm pretty sure it's in there. If it's
there, okay.
I'm pretty sure it's in there. It is well hidden. I promise. It's very well hidden.
I see.
So I'll dig it out for you.
Sure. So that means if it is true, then that means that when the guest is trying to access a page and protection key rejected, saying it's not readable or not writable, the access from the guest will be respecting protection key effects.
Yeah, the initial access when you go to populate the EPT tables, like that initial access when you've walked the x86 tables to get a physical address, that initial walk should respect these keys, even for KVM.
Got it.
The FastGup should respect it.
Thanks.
And again, this is not bug-free code, so it is totally possible that we've got some bugs.
Yeah.
Okay. Thanks. Okay. We're on to attack vector controls. Yep.
We'll go ahead and move yours.
All right. Hi, everyone. My name is David Kaplan, and probably like most of you, I have lived through the last 7+ years of CPU side channel fun. And we have, like 15 different CPU side channel mitigations now in bugs.c. I would opine that there are very few people in the world that understand how to configure these correctly, especially outside of this room. And that's what I'm hoping we can improve. And so the approach that I'm proposing here, and there's an RFC series that went out late last week, is to add some new controls based around attack vectors. And attack vectors are things like a user process attacking the kernel, so that's user kernel, you know, process to process, a guest VM to the host, guest to guest, or cross-thread for the SMT scenarios. And the hope is that these would be easier to use because attack vectors are really a property of how the system is being used, such as, are you running untrusted VMs on your system? And so the theory is that a system administrator knows how their system is being used, could make a decision about essentially what the threat model is, which attack vectors they care about, and then the kernel will configure the mitigations appropriately for them. And that would have the advantage, first off, of potentially disabling mitigations that they don't need based on the chosen attack vectors, and also hopefully giving them protection over time, because attack vectors are really a property of how the system is being used, which is likely somewhat static, while mitigations get added frequently as new research is found and there's new updates. And so this would give them protection going forward from the issues that they need to care about, as well as disabling the ones that they don't need to care about that happen to get added as part of an upgrade. So that's the proposal that went out here. Now, the patches, as they currently stand, they do not change any of the defaults. So the defaults for these remain how the kernel currently exists. The individual bug controls will override the attack vector controls in either direction. So you can enable an attack vector but turn off a mitigation you don't care about if you really know what you're doing. Or similarly, you can disable a vector, turn on a mitigation if you want. That's pretty much what there is to it. So I'm looking forward to some discussion about this. Specifically, you know, I'm curious to know, is this of interest, right? Is this the right way to think about this problem? Is there a different way that we should think about this? Are these the right attack vectors that we should be looking at? And then also, if I missed anything in the table here that someone can point out a problem, that would certainly be welcome as well. Yeah.
So question, so for this ones, like how does it, with confidential computing, confidential VMs, so when you say here guest to guest, does it apply to all types of guests and things like that? So is there differences that would be between?
Right now, no, there's nothing different with confidential VMs. These would be mitigations that KVM would enable to prevent guest-to-guest attacks like IBPB in between guests. Confidential guests do need separate mitigations typically, but you can't really rely on the host to do those, so presumably the architecture like SEV or TDX would handle that.
So the question is, let's say I enable this mitigate guest-to-guest, but that's not going to help me for confidential.
Yeah, this is just what KVM would do. Yeah.
So I am still a little confused about what you mean with user to kernel versus user to user, and guest to host versus guest to guest, which is basically this, you know, the same thing. But you know it's not at all clear what the distinction you're making is, at least from looking at the slide.
Okay, so it's a good question. I thought this might come up. So I actually only have one slide. I want to make sure I got through them. So the user to kernel attacks are the ones where you are, of course, trying to exploit something in the kernel, whereas the user to user attacks, you're trying to exploit something in the target process. So if you think about like a Spectre v2 sort of thing, user to user protection means IBPB to flush the branch predictor on the context switch, whereas on user to kernel, you might be using IBRS, for instance. Now, there is a good question, though, which I do want to address about why these are separate. Because in reality, if you care about protecting another user's, another process's information, you really have to protect both, because if you can get to the direct map, then you get it all. And the argument that I have, which is open to debate, certainly, is that the kernel code and hardening techniques may evolve over time. And consequently, the risk of like user to kernel or guest to host attacks is somewhat of a property of how the kernel is built and what hardening features it exists. And so, whereas when you're talking about user-to-user attacks, you have no control or no expectation of what is in another user process. And so that was my argument for separating those, but let me know what you think.
And it's worth saying specifically that a whole bunch of research has come out recently and less recently, looking specifically at leaving poison in the predictors across a context switch in the kernel and then attacking the next piece of user space. So Pathfinder is an example of a recent paper that did that using details in the conditional predictor, which we've got no controls to flush at all. And that, I believe, managed to pull JPEG images back out of the conditional predictor with enough analysis. So there's certainly a lot of people concerned in the user-to-user case, even if you trust the kernel.
In the back.
So first of all, thanks for doing that. I try to mitigate some of those problems in production. And the levers we have right now are super hard. And that's going to help. And I'm wondering if we should go one step further and focus on the mitigation itself instead of what it mitigates. For instance, do I want to enable IBRS at entry and exit, or do I want to enable STI and STI BP? Things like that that we have better control instead of like what we are mitigating. Because if we focus from like what the kernel is doing exactly, like what is being mitigated is just a consequence. Because a lot of those vulnerabilities are kind of mitigated by the same mechanism. And somehow I have the impression that the way we start thinking about those mitigations came from an era where like, oh, we need to fix this as soon as possible. But that's been here for like, what, 6 years now? And we're still finding the same problems. And we are still behaving like with the same mindset, like, oh, I want to mitigate this, I want to mitigate that. Instead of thinking like, oh, this is a new feature that we have now on the microcode. Do I want to enable that or not? And we can make like spec v2 mitigate, depends on this being enabled. That'll be fine, but I think we're still thinking the other way around.
I hear you saying, I will respectfully disagree though for two reasons. One is that I think it's hard to make sense unless you're an expert in the space about what does STIBP get you just from turning it on. But the bigger thing is that for better or worse, I think much of the outside security community is still in this mindset of there's a CVE, I apply a fix, right? And so that's why we have to have that. Here's a Spectre v2, here's the fix.
Yeah, I was going to say very quickly before I pass it on, is everyone aware that STIBP is different between Intel and AMD, and the way you need to drive it is different, and currently no code does it like that because we only found out a year after the fact?
It's super simple.
Yeah, I was going to say, I mean, as a distro kernel maintainer with a lot of end users, I would guess that probably the large majority of my users have no idea what any of those mitigations are. So if we turn them on by default, or a lot of them on by default, but if we give some control like this, I really like this. I think it's something that end users, I mean, not sysadmins, not engineers, end users of desktop systems can look at this and say, oh, well, this makes more sense to me.
Thanks. That's good to know.
So I wanted to give the Google perspective on this because we really like turning mitigations off. Google has a strong desire for that. And we've hacked our kernels to give us ways to turn them off in certain cases. But I don't think, I'm not opposed to this because like you said, I envisage futures where they become useful, but I don't think any of the boundaries that we want to stop mitigating align with any of the things on this slide. So the things that Pawan had on his slide about like saying this C group is trusted because you can already read the kernel cake or whatever. I don't know if we have that in Google, but that's more interesting.
Right. So first off, this is definitely not an either or. We can definitely do both. Also, with all due respect, you're probably not my target audience.
Okay. Yeah. Sure. Yeah.
but yes, I'm looking forward to the rest of his talk too because these are still very coarse, and I think we are going to want finer grained things, but at least this is something.
Yeah, I agree, and I think it's really valuable. I would almost say just having the table is as valuable as making these configurations. I would say, and maybe we could talk afterwards about this, but yeah, I would say there should be 40 rows in there, like L1 Des and Snoopy, or I don't know if ZenBleed is included there. Branch type confusion. There's oh sorry.
Well, it's worth saying ZenBleed's not a speculative thing; it's an architectural bug.
Right.
ZenBleed is unlike everything else here.
Yeah,
Great.
And branch type confusion goes by rep bleed in the kernel, so that's why.
Fair enough. Okay, so maybe it's breaking out the AKAs, saying what all the other names are for these, and then perhaps we could talk about why some of them aren't in this category and what's the other table for those. Just having that documented would be huge. I think the closest we have to that today in the community is, well, there's the parameter documentation in the kernel, and then like the Spectre meltdown checker shell script, but I think getting something more comprehensive is going to be super valuable.
That's why I think the same mitigation applies to a lot of those vulnerabilities. So if you're thinking about vulnerability, as you said, like we need to have like maybe 40. I think Wikipedia says around 40. Kernel documentation says what, 10, 12? Because there is, like, we're seeing this from two different perspectives. One thing, and even if we look at the kernel configuration, like you mix like mitigations with things that mitigate problem. Like I want to have Spectre v2 mitigate, at the same time you have to have red Pauline. So I think there is a confusion here. What if we're addressing mitigate vulnerabilities, or if we are providing levers that will help prevent a bunch of mitigations. I think it's important to fix that, and this is in the right direction.
It's worth saying GDS is missing a cross-thread mark on it, which was something I noticed.
So I think I built this off the kernel, so we might want to check bugs.c.
That would involve going and reading bugs.c.
I'll follow up on that.
I don't think I do agree with the idea of configuring mitigations instead of bugs, but one point in favor of it is that we have mitigations today that we probably have some mitigations today that mitigate a bug we don't know about, and we might have users that, for that reason, might want to turn it on. I don't think I would do that, but maybe people would like. So I don't think it's possible right now, if the kernel doesn't think that your CPU is vulnerable to anything that's mitigated by it, I don't think it's possible to say IBPB every time you exit the VM, and that might be something that people want.
Yeah, that's true.
Yeah, I do think, like, we would never, maybe, okay, I don't want to say never. It would be nice. It would be nice not to have to do new command lines for every issue that shows up, and have a command line option for every one of these. It would be nice if in the future we could just rely on these. But you do make a good point that we probably won't ever be able to get rid of the mitigation-based stuff.
As a developer of this nonsense, having all the individual knobs and toggles is really useful while developing and afterwards for testing, which is why a number of them also have a force, so that I can force enable the mitigation and look at the end result in my kernel image to see whether or not this stuff is applied, even if I'm working on a chip that is not actually affected by the issue, or in a QEMU image or what have you that you are poking on at. So all the individual things and knobs is useful for me.
The same thing as well. The number of times we've broken XPTI on newer hardware that isn't vulnerable to meltdown, how, from a development point of view, both testing new stuff and testing interactions or combinations, because most of it is low-level assembly hidden in alternatives with things out of line, and there is no
So
yeah.
And since we're getting a little bit off the initial subject, which is fine, I do want to mention that, of course, the bug controls override these, so you could still do, something like equals force. Also, included in the patch series, for anyone who cares, I also try to clean up bugs.c a little bit and restructure it so that it's more consistent between the different mitigations on how they're handled. And I think if we wanted to enforce some commonality, so like everything has a force option, that would certainly be welcome. I don't know how valuable that is now because these things are older, but it's something to consider.
So I definitely see the value in here. I have one question. Is the plan, if you say I mitigate user to kernel, whatever, to on to have like full mitigations enabled, because some of the defaults, like for L1TF, it's like unconditional. It's not unconditional anymore from the flashes.
Yeah,
so there are some cases where you can still exploit it.
So currently the way it works is I'm just going with the default mitigation setting, but there's one mitigation here in particular, BHI, that actually separates the mitigation between like syscall and VM exit. And depending on which attack vector is enabled, it will enable one or both of those. I think there's some other ones on this list that could be implemented the same way, given that there is now a better way to control the different ones. And so it's not quite fair to say that it's mitigated if this vector is selected, because it may be different mitigations for the different vectors.
But I think it's probably fair to say that these are kind of the equivalent of, like, this would say, turn it into auto mode in most of these cases.
Correct.
Yeah.
But I think if you stick with the defaults, it gives a false sense of security in some parts.
I think
because
that would be
as a
then a
user
problem
would
for that
expect
mitigation. If the auto mitigation is not safe, I think that needs to be fixed.
Okay. And I think for L1TF, you want to have a check mark for user to kernel because it's fixed by default. Because the PFN is overwritten when it's paged out, for instance.
You're saying L1. You're saying you need the L1TF
like
for user.
for
kernel?
Shadow OS is basically L1TF.
Well, there isn't a mitigation to flip for, right?
Yeah, but it's fixed in a way.
Well, yeah, tell me, hopefully I'm not wrong here, but I actually think the defaults in general are actually quite sensible. And most of the time I would say the defaults that I've seen picked from kernel development are usually not the super performance impacting version. They're usually a pretty safe, kind of reasonable place to be. Maybe you also want to turn off hyperthreading, maybe ensure it's unconditional with like L1TF. But it makes me wonder what use cases there are. Like, to me, it seems like perhaps there's only one mode, which is like I want the default stuff, which you get today without having to worry about the parameters because the default one will get applied. Or I'm sort of going into beast mode and I'm going to pick what they are myself. So maybe you've seen, it would be interesting to hear like who is it that's like, well, I would prefer to have maybe more of the mitigations off because it noticeably impacts my performance and I don't need them because of my use case, but that person also doesn't want to have to configure each one individually because it seems like they might already be in that realm if they know that.
If you're that deep into the granularity of your mitigations, you know pretty much what you're doing, so you get the knobs we have.
Well, the default settings can be quite costly, especially on some CPUs. Some of these are pretty expensive, especially in some use cases. And I think many people that I've talked to don't know to turn them off because they don't understand what these things are and when they're relevant. And so the hope is that this is an easier way of saying that, like, if you don't run untrusted guess, you don't have to worry about these, and they don't have to go and read the paper about how the bug works and stuff.
Yeah, fair. I mean, rep bleed on Skylake is maybe a good example of where it really gets terrible to do IBRS. But that kind of only shows up if you're running guests too. So are there others where it's like it is so impactful and they're not doing virtualization? I guess I'm sure they're out there.
Yeah,
it would just be.
There are some examples, but then also some of this is to be future looking.
So we can do a break now, or we can continue talking in the break. What do you guys want?
The break.
Okay.
Right.
So 7 minutes.
Cool. Thank you.
Thank you. We have 20 minutes for every slot. Nothing's going to get out of this.
This is just starters.
Yeah.
I agree with that one. Be careful for the back. Yeah.
I know something's not okay.
We have trouble booting
Just a question.
I know, yeah. Are you going to go to the back for the rest?
Yeah, I'd be happy. Yeah, are you coming?
Yeah, I have to meet my dad. Oh, wow. With my dad. Actually, he just checked into our Airbnb, but I don't know.
I'm sort of split between worlds. Figure it out. I do both the Linux kernel stuff and I do not all change. So it's sort of, you know.
Well, cool. Glad you can make it.
So yeah.
Glad you can make it this year.
Yeah. Also, you know, not much Xave stuff these days, but this is very hard. So I thought because it's
that probably sounds like it's a bug in the kernel. I always
just myself from fast forward from
I rarely disagree with KVM.
Very cool.
Interesting.
I'm curious if that makes sense.
Especially this page protection keys.
The kernel people don't test.
Let's get it.
As opposed to inventing a CPU model. We're just using the subsystem. Did you do that?
Oh, these guys are here, right? Yep, these guys are here. These guys are here. Okay. They're in person.
So how do you know?
Oh, there we go.
I read it in 5 minutes.
Okay, great.
Yeah. But I it took 9 minutes.
Perfect.
Yeah, you got 20.
Cool. Good luck. Well, we got 20 minutes or something before. Next batch is on the hour, right?
No, it's...
Is it 10 minutes?
5 minutes.
5 minutes. Okay.
What is the
cache issue? Okay.
no cache, no
I have literally pages on paper of I've done stuff as well. We also need to get it. Yeah. But I have literally written it out around them.
These guys already do this.
Is this like on purpose, or is this more like a mistake? Because like this trade-off, use protection keys. I think there's one paper actually that's called UNcore, but they also they don't consider spectrum. I'm not sure if
Okay, everybody, we're going to go on the next talk here. Let's. Okay. Hello. I'll just close the door.
Hello. Hello, everyone. I'm Lai Jianshan. I'm from Ant Group, focusing on lightweight kernels and secure containers. Today, I will talk about an IST problem and a possible solution. The agenda includes 4 parts: the problem, the motivations, and an atomic approach, and a breeding issue with it. The 64-bit x86 design are constant bin. Many kernel developers complained about it. The problem of IST are actually from syscall gap. If there were no syscall gap, there were no events requiring IST, just except for the double fault. Hardware solution should fix the syscall gap like thread. Software solution have no choice. it has to use atomic weights. Here is 2 examples of the current approaches. The MMI approach used two stacks. The first stack is just 96 bytes. Used only for hardware entry and I return. The second stack is for software handler. It is 4,000 bytes. The VC approach has larger stacks and use C function to copy off the stack, but it has an ugly backlink. The atomic approach borrowed the ideas from these 2 approaches. The most important motivation is that we have to fix the problem. The other motivations include less ASM code, PVM switcher, and ASI. PVM is in production and aims for upstream. The PVM switcher is integrated into the host entry code. So we hope the IST entry code can be self-contained. The key point of the atomic entry is that all of the IST events watch for each other. If an atomic entry is interrupted, the later one should help the previous one complete its work. When an atomic entry is interrupted, it will never return to the original point. So its code must be abortable at all of the places. And its work will be completed by the innermost atomic entry. So its code must be replicable and idempotent. Here is the example. Let's figure out how to make abortable, idempotent, replicable atomic entry. For an entry, we have to save the context before handling. Second, for an atomic entry, we have to copy the context and switch to the new stack. The third, as an abortable entry, we have to it should be able to commit all the results. And the save stage have to split into 2 save stages because the save stage is not hardware atomic. We have to handle it differently. Both the 2 stages cannot touch any general purpose registers. The fifth, copy for the almost and copy for the nested are different. The last, we have to locate where is which is the almost. This is the place where syscall gap might hide, and we have to locate where are the contents saved and where to copy from. So we have a locate stage, and in the last line, the save stages and the commit states can be implemented in ASM code. Only the stages in yellow color can be implemented in C code. When we compared with the third line, we just named the C code. Give it a name as a copy. The C function name as copy. Here is the 2 narratives of the atomic entry. On the left is the procedure view. 3 IST interrupt one by one. All of them try to save and locate and copy almost for the first for the first event and copy nested for the second and the third. On the right are the data view. It shows the IST stacks of the 3 events, and there is a major stacks, and also show how the locate operation works. It need to locate where there is the almost places, and where the data save and copy to. For copy out most, it find that the exception head is on the A stacks, but the event A is interrupted so early that it does not finish in saving the general purpose. So the locate code find that the general purpose registers are saved here. So copy almost copy those contents from here. For copy nested, because we assume that atomic entry assume that the previous event had been completed at the commit point. So all the states are null. So we just reset the states. When the code finish copy all the data, you can return and use just one single instruction to switch the RSP, and this single instruction commit all the 3 events entry. This is all the atomic entry works, but there is a problem, as Peter G pointed out. Although we have stacks, but we cannot do function call and return. This is the problem. We have 3 possible choices. The first choice, we have option 1, just rewrite the C code with ASM. I think it's not feasible. The second tool, just eliminate the return instruction with some hacks. We make each function called only once and just use the jump into the instruction instead called into the instruction. The second choice, make the untrained code be able to use in the entry's early stage. I'm not sure it is possible. Maybe it requires splitting the untrained code. The third choice, add the code in the C function that to switch to the full kernel contents. This effectively implement the paranoid entry in C code. This is also in our mission, but it has to be implemented in the way that it meets the requirements of abortable, idempotent, replicable. So to meet the requirements, the steps are split to these stages. So that's my question, and I need your suggestions.
So first off, are you aware of the Fred spec?
The approach try to fix for the problem for the machine that have no thread.
Yeah, okay. So one of the things that came up during the discussion of Fred was the following scenario. And please tell me how you would plan to fix it. First, take an NMI, and then take a page fault in it because it was a profiling NMI. Then you get a machine check in the middle of the NMI handler, and you're towards the end of the machine check handler, so you've cleared machine check in progress, which is the bit in hardware that deals with re-entrance of machine checks. Then you get another NMI, and then you get another machine check on top of that. You're in a position where both the NMI and the machine check handler have recursed on each other and have clobbered the outermost exception frame.
And getting second NMI.
Yeah, you've
returned from the first one?
Because you took a page fault originally in the NMI handler and did an IRET, so you unblocked NMIs. In this position, you have both the innermost machine check and the innermost NMI, both on the instruction boundary at the start of their handler, and both of them have to copy sideways and decide to do that, one for the outer one, without without being able to spill any general purpose registers. It's not.
The atomic entry only watch the atomic part. If the MMI enter is handler, it will not watch it. The MMI handler will, the C MMI handler will watch itself. All the handler of the IST are moved to IST main stack.
Oh, so the problem is that until you have pushed the general purpose registers onto the stack, you may have to do that for your outer exception, or otherwise you've lost program state. And that was the corner case that we couldn't figure out any possible way of fixing without Fred. It is a narrow corner case, but in clouds you do it.
I haven't got the.
Yeah, and maybe I think that is a good point here. Is that this is the older architecture, and hopefully this is code. I mean, we have to update this for a while, but hopefully it's code that we won't care as much about, in the coming years. So is this? I think the bigger question is like, should we invest this time to refactor this? I mean, if we can find a way. I mean, there probably are holes in this. There are holes in the existing one, right? So like, is this from people who have messed in the entry code?
So I was full board on doing this.
So I was entirely in favor of doing all this right until all the mitigation mess happened. Yes, the C stuff is far easier to work with, but it also makes us susceptible to whatever madness the compiler does. The mitigations are so subtle that having everything in assembly, having everything fixed, is both a blessing and a curse.
Maybe one specific example there is like the problems with red. Like, had we invested in this, right, and we were used to having normal C with normal function calls and normal returns, and then all of a sudden we had red bleed thrown in. Would that how much of a problem would it have been to fix? Would it have caused us more problems in the end? I think what Peter's saying is, since we have so much more control over assembly, or let's say the compiler did something in C that made us vulnerable in the future, would we end up having? What are the odds we have to go back to assembly, or do we have to go?
So the thing that happens under C that really messes with the mitigations is the fact that at any arbitrary point in time, the C compiler is allowed to emit a call to memcopy and to mem0, and it can do that as part of setting up the stack frame. It typically doesn't, but it can, and as a result, you end up with a call and a regular call and a regular ret that is just not visible in the C code. And yes, you might be able to have ObjTool wander through and guarantee that there are no unexpected calls in your C code, and then that becomes problematic. What happens if you had ubisan active? Okay, maybe you care about getting ubisan there and you don't necessarily care about the mitigations, but all of these compound to a point at which we just decided it was easier to say we will write this in assembly so the compiler cannot screw it up.
Maybe we can use OBJ tool to track the result of the.
Yeah, it's doable, but it's hard because it depends on the other sanitizers that are on the other options that you. It's not simply a case of deleting everything.
Like I said,
I liked all this, but the mitigations have made it such a mess that I don't think this is really worth doing anymore. And I mean, all my hopes and dreams are for Fred at the moment, to restore some sanity to our entry code. And AMD is doing that as well, aren't they? Yeah, no comment. Damn.
The problem is you need to support the old ones, even with Fred. So it's going to be a.
They work today.
Yeah, I know.
I think part of what you're hearing, though, is that there's a good pile of people in this room that have hacked on that code. And I think none of us, enjoy the assembly. But it is it is workable for us. And maybe we need the group of people that can mess with it to grow. But I think part of the question is, like, would doing it this way be worth it to let more people hack on it? Or do we have enough is one question. Like, do we have enough people who can change it?
So, if you're crazy enough to understand everything that needs doing here, you're crazy enough to be able to do it in assembly.
And the step is so...
What he's talking about there is exec NMI. One of the examples he had here in the slides was the multi-layer stack that we have in order to take NMIs is nuts. So if anybody wants like some horrible reading, like if you're ever sad on a Saturday, a rainy Saturday afternoon, and you want to feel worse, go look at exec NMI. It's lots of fun.
One thing, this is kind of ironic in a lot of ways, but having code in assembly is to some degree a huge "here there be dragons" sign. There's a lot, it's really, really easy for someone who doesn't understand the subtleties of particularly fragile code to go in and say, oh, it's in C, I know how this works. And they make a change and suddenly something goes very, very wrong.
Saying that that's happened in the assembly as well. It's not like it's not like the review of the stuff that goes in there is perfect either.
Okay, thank you.
Thank you.
The difference is that you're at least not going to have a bug that appears on one compiler version and not the other.
There you go. Yeah, go ahead. That's what I got him for.
Oh, right, yeah.
I refer you to the misalignment bug on the jump to ret mitigation that was caused by a linker change. Sorry, I'll stop there.
Yeah, stop there.
Okay, hi. Yeah, I'm Brendan from Google. I'm working on address space isolation, which is...
That's you.
That's me. Hi. Well, I'm one of many, really, and there's been a sequence of us. Address space isolation is kind of like its attempt to take back the strategic initiative on CPU bugs. I presented at LSF BTF 6 months ago, and I spent almost the whole session explaining different details of how the implementation works. I'd quite like to skip over that today. So I propose to spend 5 minutes rushing through an overview and go from there. Is that okay with everyone? Sure. Okay, cool. So here's a simplified view of some exploits. The attacker, which is, let's say, guest or user space, sets up microarchitectural state very cleverly, branches into the victim domain, which is the host or the kernel. The kernel misspeculates, accesses some secret. The CPU detects the misspeculation and starts rolling back the instruction, but leaves some residue behind in the microarchitecture. And then the attacker leaks that residue out. The classic example of the residue is like cache entries that were loaded from a location that depended on some secret value, and then you can infer from the timing of which of the memory accesses, which cache entries are there, and from there you can infer some bits of the secret. So there are 3 places on this picture where we can intervene. The 2 straightforward ones are on the transition between security domains, so like temporarily, and the other thing is that you can't speculatively access data if it's not in a TLP, it's not mapped, because of, yeah. We hope that that's true, at least. We're pretty sure it's true. Oh, my slides were in the wrong order. So with those 3 things in mind, let's try and design a blanket mitigation for everything. So if you run your untrusted code without anything secret mapped, which probably you do anyway, and then after you run the untrusted code, you destroy your branch predictor. I'm not going to go into this, but you'd also like to turn off hyperthreading at that point. And then before you go back into untrusted code, if you destroy like your whole cache and your like load and store buffers and your TLB or something, then all of this stuff goes away. Obviously, all of those things that I talked about destroying are important and we want them.
You've also destroyed performance.
Exactly, yeah. So we don't want to do all of those things, but it's a good starting point to like illustrate that if you could do that and you could destroy enough things on transitions, then the problems would go away. So ASI is kind of about making those domain transitions less frequent by going into the kernel and executing kernel stuff without secrets mapped. And we don't want to make the whole kernel aware of that it has to like switch address spaces when it wants to access certain data. So we want to make that transparent. So we keep as much kernel code as possible unaware of it, and we detect it by having a page fault. In the page fault, we destroy some microarchitectural state that we don't trust. And then if we did that transition, then on the way back into the VM or way back into user space, we do another flush, whatever that might be. So that's the idea. And here's some evidence that it works. I guess you can't see this, but I'll walk you through it. So the top three lines, this one here, can you see the point that yeah. That's like if you have mitigations off, you trust your workloads. This is a throughput benchmark. It's a QEMU guest running on a Zen2 host. I rented a VM, I rented a server from Hetzner, and I was like, cool, the model number starts with 3, so this is a Zen3 machine. But model numbers that start with 3 are Zen2. So this is Zen2. So there's your performance with mitigations off. Like I said, we have some mitigations that are like pretty blanket that exist in the kernel today, and they probably mitigate loads of stuff we don't know about. So for example, this one is if you do an IBPB every time you leave a VM. Even just that alone just completely tanks performance, so this is like more than a 50% degradation. And then we have bespoke mitigations, which I guess like you guys have to like frantically develop every time a new mitigation comes out. So here is, which one is this? I forget which one it is. Yeah, so this is not SafeRet, but the one before SafeRet. Anyway, so we have some mitigations that are really generic and really costly, and we have some mitigations that are really fast, but they are costly to develop. I'll skip over this middle graph. Well, actually, no, I won't. So that top one there is my RFC. So this is like the stupidest possible implementation of ASI, and it's already quite a bit faster than doing an IBPB on every VM exit. I don't know what the VM exits are there that we don't do an IBPB on, but it's some of them, and that's already nice. And then down here is my RFC plus a bunch of hacks to make it faster and do transitions less often. And I hope that those hacks are like also viable, not as hacks. So what we have here is like instead of, we have the performance attributes of the bespoke mitigation, which is costly to develop, but something akin to the security properties of the generic mitigation, which works for everything. And that's the big idea. Any questions at this point? Yes.
If I'm reading this graph right, you're saying that your RFC is faster than the baseline?
The baseline of doing an IBPB on every VM exit, which is not a very realistic baseline. No one would, yeah. Sorry, so
okay.
Yeah, this is the baseline.
It's hard to read your slide because it's really small, but
You're sat too far away.
Yeah, it's like I'm sitting in the front row. I'm too far away. What is the lowest line on your 610 baseline graph?
So this here, the
lowest one.
Vulnerable.
The furthest down.
Oh, the furthest one is when you're vulnerable. Yeah.
Exactly, right. Yeah. Your bottom slide is actually faster than that.
That'll be noise if that's the case. So these aren't confidence intervals; these are quartiles. So it's not faster. that's a statistical artifact. But I can't actually see the bottom one on my thing. There's like a UI element hiding it. Yeah. Oh, yeah. That's a good point.
So.
Yeah. That's not real.
All right. So with your ASI, are you disabling all of the mitigations because once you do the ASI exit, then you're considered safe?
For this performance data, yeah. So this is like the only mitigation that's enabled here is the rep lead one. Yeah, so that's not realistic, but that shows you the relative cost.
The only mitigation that's enabled in the restricted address space or the full address space?
No, so when ASI is on, it's in this data, it's the only mitigation enabled. And it's only mitigating stuff like rep lead. So it's doing an IBPB on the address space transition.
So it's a CEDAR 3 switch and an IBPB.
Like Peter?
Yeah. Oh, actually, it would. So if I was to run this, I'm pretty sure if I remember in the RFC, the example I had was like it would do that on AMD, and then on Intel, it would flush L1D on the inverse transition, which is not. We obviously need to do more than that, but it just.
And you verified that the reproducers actually do not leak with ASI.
Yeah. So that's something I brag about in my next slide. Is so some people from Google have taken exploits for a couple of these exploits and turn them into self-tests. And so, my branch actually on GitHub has the one for L1TF in it. So if you want to have a look. And I've also bullied the security engineers into adding comments. So when there's like OX414 NOPs, I've been like, you have to say why there are OX414 NOPs.
Send patches, please.
Yeah, we will do. Sorry for the delays.
Have you considered using protection keys to speed this up?
Yeah, I'd like to do that. I think the only benefit of that is that we don't then have to flush the TLB when we're changing what's in the restricted address space or not. So the cost of this isn't changing CR3. The cost of this is like doing IBPBs and stuff. But I still think there is a benefit to that. We haven't like really researched it just because we have CPUs we care about that don't have that. But eventually I think it makes sense. Yeah. Okay, so go ahead.
So have you thought about a way to sort of separate the functions that run in the restricted address space versus the other ones so that mitigations can be applied to one or the other? Or how are you doing that?
What do you mean by functions?
So you exit the VM and you run in your little bubble, right, which is some KVM code.
Yeah.
Right? And then that might call some functions that, let's say, those functions require rep lead mitigation. But once you exit ASI, then functions that are called there don't require ASI or rep lead mitigation, right?
So that was covered in quite deep in the cover letter. The way Paul Turner wanted to do this originally was to say that you start like that and then you use profiling to find out which function is constantly wanting data that's not mapped by default. And then, because in the fast path in KVM, there's no mitigations. You let speculation go wild on the assumption that there's nothing secret to leak. You take the page fault when you start accessing data that is not deemed safe for rogue speculation.
Slightly different than what I'm asking about.
Oh, okay.
Yeah, I guess I'm asking, like, in the protected space, how do you prevent the code from calling, like, I don't know, kmalloc or something that does not have rep lead protection?
Well, we don't. It can do that, but there's nothing for it to leak, so we don't care. I might be misunderstanding the question.
Okay, maybe I.
No, so the difference is that you do a huge amount of scrubbing in the page fault handler when you first move into the.
Okay, so you don't need to protect anything.
Yeah.
It's dynamic.
Who wanted it?
The idea is you fault. So anything that can get at secret stuff, you fault. And then on the fault, that gives you the synchronous point to say, hey, I need to do all this flushing. And then you go in, you do your fancy secrety stuff, and you go back.
Yeah, and this means that, so in the past when I described this to people, they were like, what? So now every time I have kernel code that touches data, like kernel code, basically, I have to think about whether I need to switch address spaces, and so you don't, because the fault does it for you.
And I think that's a good segue into the part that you really want to get to, which is how the hell do we actually upstream this?
Yeah, so let's go from there. So I posted the RFC like 3 months ago, and somebody pointed out that I missed out a new line, but nobody pointed out that I broke the, freeing any kernel memory, so I don't think it got reviewed very carefully. So I'm kind of here to be like, I almost want to get the code up and let's read it together. But what should I carry on and turn this into a patch and go ahead and go for a review from there, or what's the most important thing for us to discuss? or if otherwise I'll just start proposing topics from the slides.
It does look very interesting. I mean, it can solve so many problems. It looks really interesting. I guess I'm just worried we're going to get deep into it and then realize that there's a hole or there is some kind of performance issue that is a non-starter.
The part that scares me and I think we really need to figure out is how do we maintain this once it lands. So profiling everyone's kernel that wants to build and what's their hotspots is not realistic. It may be realistic for Google, but it's not going to be realistic for upstream. That's the part that I think we need to figure out from how do we get this upstream in a maintainable way, not how do we get it upstream the first time.
So that probably comes down to first of all, I'll acknowledge that I think one of the biggest weaknesses is that it can have unpredictable performance in the sense that like my fear is that we have some like very hot path that doesn't currently cause an ASI exit, and then somebody loads a BPF program there and it does now, which is, that's a concern. So you don't, but yeah, I think the thing you're really getting at is that we have to decide what's sensitive and what isn't, and that's arguably different for different people, and has a big impact on performance.
Part of the problem there is that it's not even that it's a yes/no choice. The same piece of information might be sensitive to some people and not sensitive to other, and you can't really deal with that in a single build of the kernel unless you're having classifications of where do you allocate it.
Yeah.
Realistically, if you make this a completely stable API and have one single thread model for everyone, don't you arrive at PKVM? More or less, like you're effectively creating a new address space. In this case, like more like a tiny visor, whatever you call these things.
Yeah.
And that can then secret hide individual VM contexts, which is the one you really care about, right? So you just consider I/O to be unsafe.
Yeah. The two strategic differences from PKVM are one that this doesn't only protect or sandbox KVM guests, and two, it's something that you just kind of like spread on the kernel without needing to like re-architect your system. So that's, but yeah,
but I think you also
point my answer is yes.
run into the problem like PKVM doesn't have RCU support yet, which is just a minor wrinkle. Like I don't think we can go straight to full PKVM and still have all the functionality that we want in KVM and performance. Just hoist your stuff into PKVM into a low visor isn't a realistic option. Not in the next, because we don't want this 4 years from now for x86.
The other one I had is there are basically two fundamental, well, three now with PKVM, fundamental approaches, right? The other alternative to what you're describing is all of the secret hiding logic that we've been doing with process local memory, now MM local memory, guess memfs to hide memory from the direct map, so that anything that runs in the kernel is considered untrusted, always, right? What do you think about that concept instead?
So there was, I guess the closest thing to that is Mr. Roy, I keep forgetting his first name, Patrick Roy, presented on unmapping guest memory from the direct map using KESMEMFD, and I want that too, but because, that for two reasons it works nicely with ASI, because one, it makes ASI more predictable, and two, it also works against software bugs, which I guess is less important, but I still want ASI on top of that because ASI lets you protect. So their strategy, I think, there, which is not an unreasonable one, is let's unmap guest memory, then let's go and unmap vCPU data, and then let's go and unmap this and that and this and that. And ASI, you still have to go through that process, but you don't have to re-architect KVM every time you do it. You just have to find the place where your data is allocated and add the flag to say this data needs to be protected by ASI. And you can do that for user space too. So I want both of those things, basically, if that makes sense.
But they will converge eventually, right? Like if you find all these places, you did re-architect, you no longer leverage the slow path of ASI.
Potentially, yeah, but I think there's always going to be some data that we don't know if it depends on some guest register state. And yeah, and also I keep going back to the thing that we also want to protect against user space threads.
And isn't the hard to maintain and scary part tagging stuff, not the actual mechanics? So I think we should not focus on, is it ASI or are we on mapping? It's how do we tag stuff, how do we maintain it and support multiple threat models?
So can I start the discussion off here by so there are two like obvious ways to go here, and neither of them is pleasant. And one is that we say, we assume so what we call an allow list model, where we assume everything is sensitive, and then we like bit by bit we figure out what we can afford, how we can speed things up. And the other is the deny list model, where we start with like something that isn't kind of not theoretically secure, and then we slow it down bit by bit. The discussion at LSFM and BPF, somewhat surprisingly to me, lent towards the deny list model, because that lets us have something in the kernel quite soon that people can actually run. And we can go from there. And I don't want to stay with a world where we carry on having to like find things, but I think we could potentially evolve towards some hybrid where we're like we can wipe out broad classes of data all at once.
Yeah, I think we will never come to a conclusion what the best set is until we really start with the basic set and work from there. Anything else is over-engineering and falls under the category perfect is the enemy of good.
Right.
So what I really want to see is the basic infrastructure in there, and then we can take it from there.
And when you say the basic set, do you mean the most secure set or the most performance set?
No, the mechanisms which allow us to isolate.
Yeah, okay.
And then we apply it step by step to certain areas, figure out what is the problem, was this the performance hit was, and figure it out gradually instead of trying to fit something into it we never can agree on.
Right, yeah. So on that point, where do we go from here? What do I do next?
Last question.
Yeah, so you mentioned guest a lot, and does this only apply to KVM, or will it also replace PTI?
Well, replacing PTI is a complex, loaded topic, but it definitely, we really want it to sandbox bare metal threads as well. Yeah, and it's implemented as a framework that lets you do that, but we've only got the KVM client of that API so far. Yeah.
Cool, thank you. So we got another break coming up. If you want to keep talking about it, feel free to come up and continue. Half an hour break.
Thanks.
You know each other?
It's a big change. I heard your name. I know the name.
Daniel, you were operating for a time.
I'm still young.
You're still operating. He wants to move over to do more kernel work in the x86 area.
Good place, let's say.
And we'll get back. I'm on the way out. I'm on the way out. You know that. No, but we have a list of crap that needs to be packed and cleaned up. You have that list. But Daniel is looking for to export in and find some hopefully it's manageable area. That's fix a CPU ID in 1 hour.
I think much like I was doing
how deep is the knowledge about the local API and the IOA?
Not so much. But get started. Yeah. I was thinking about that because I was
So this is really an area.
Thomas wants to get rid of.
No, the thing is, I want to take myself back, and some of these young people here, these whippersnappers, they've refused to look at things like APIs.
Because they don't have time. You know, there's other stuff.
No, it's mostly about, there is definitely some room for improvement here in terms of cleaning up all the code, and I did a large sweep last year, but there's still enough left. But the main important part is to understand the whole shit show, how that works. It's pretty much encapsulated in x86 kernel APIC. That's the subdirectory. And there are three components. One is the actual vector management. That's in vector.c. Then you have the APIC itself with all the nasties about APIC timer, the different variants. This code could need an overhaul. It's horrible. It's 20 years technical depths here. Then we have the IO APIC, which is another. It's kind of cleaned up, but it could do some. It could need some love too. And then it's just the lost component is the MSI support. Alpha is clean code now. The vector management itself is pretty clean. So what you need to look into is, or what to get familiar with, is the way how we do this with stacked hierarchical domains. So the idea is the lowest on an x86, and it's similar on ORM64 and other architectures. The lowest domain is the vector domain, and then you have an IO APIC. You have the IO APIC handles the IO APIC chip, but it still needs a vector from the vector domain. So the parent of the IO APIC domain is the vector domain. Now, interrupt remapping comes into play. So, and that's the original interrupt remapping code was basically 100 callbacks between the interrupt remapping code and the vector code and the IO APIC code. So with hierarchical domains, we got rid of all of them, because once you have interrupt remapping, the parent domain of the IO APIC is suddenly the IO remap domain, and that has the parent domain in the vector management, which is easy because then when interrupt is set up, it doesn't care what the IO APIC code doesn't care anymore whether there's a remap unit or not. So it just says parent. We need to allocate, we need to activate, we need to whatever. And studying these concepts, and one great favor you could do to me is document it.
How it works? I guess
Yes. I mean, I help you when you have questions, but it's would be cool to at least figure it out, or if you run into a roadblock, ask me, I help you, I explain it to you, and then we document it so that, because when I go away, a lot of people are scratching their head. I mean, I'm guilty. But
So you are the main author of this code?
yeah, most of it. I mean, there's lots of historical code there. It's a combination. But if you try to understand and document it, and I can review the documentation and explain things to you when you go to kind of a roadblock, this will help you tremendously to understand the inner workings. So that, and it's useful work because we want documentation.
So do you want to implement documentation?
I usually prefer, so if it's more of an overview document, then yes. If it's documenting particular details, I rather have it next to the code.
Sorry?
Next to the code.
Okay.
Yeah.
So in the files.
Yes. So if there's an overview how this all connects together, and on the 3,000 meter flight level, this is material for documentation.
Yes.
But the details sit in the code, and here you want the documentation next to it.
So you would prefer if I, let's say, go from the code, understand how it works, and try to add comments to
Yes.
to code
Yes.
to improve.
And or if you see, I mean, you will find shit which doesn't make sense, then fix it.
Okay, sure.
So, but this is, I think, because that's one of the things Boris loves and other people, Dave, Hansen, HBA, they are, no, that's Thomas. It's crazy shit, but it's really low-level architectural thing and fun.
I was always interested to go deeper in this thing, but
and it's really deep.
Okay, that's nice because I didn't have the time.
Yeah, no, but this would be a great value to have that stuff documented, and you learn a lot of it because if you want to document it, you have to understand it.
Certainly.
And if you trip over things which do not make sense, and if you see the obvious solution, or if you don't, we talk and I guide you through.
Okay. So, do you want me to communicate to you over the email, over the RC?
So email for if it's a launcher thing, email because that's easier.
Okay.
If it's just a quick question, IRC.
Okay, so I'll take a look at that.
That would be a great thing to do, and a valuable in the long run, having someone who actually understands that line of code.
Certainly, I will start looking at it. Of course, I will still involved in maintenance, so I cannot promise that it will start. But certainly, I will.
Take your time, and when you come around to it, then you start.
Okay, I will.
I think that's a good area because it takes a little bit of the burden away from the other people, and it makes me sleep better.
Okay.
I think it was in my mind already.
Okay.
But this is definitely an area which needs some care and needs someone else than me understanding it.
Okay. So the ethics stuff was mostly prepared by you.
Yeah.
Okay.
So there was existing code, but then the whole conversion to hierarchical hierarchy domains. I didn't do the work myself. This was an Intel engineer a couple of years ago, but I did all the design, the architecture for it. And then the guy went away and vanished from the planet, and so I did everything on top, and all the future work I did.
Okay.
So I know that code, and you can look through the history how it looked 10 years ago.
Okay.
And you will barf. So a lot of the shit is gone, but there's still leftovers from really 20 years ago.
I can imagine that it is quite difficult code, so...
Yeah, but get familiar with it, and we can talk through areas I want to see improved because they do not make sense.
Okay.
But I didn't have the cycles to clean them up.
Okay, sure, understand.
That's valuable because it takes the burden away from Borislav and Dave and HBA.
Okay, sure. I will take it. By the way, I have one question for the Transition project and X86. Recently, my colleague posted V11, I think, version of the patch set.
Versus what?
Lost Phoenix.
Yeah, but what's the
currently,
what is it about the patch set? What's the patch set about?
This is the Transition project.
The Transition, yeah.
The TXT stuff. And currently, as far as I can tell, Art takes care about VFI is okay with the patch set.
Yeah.
We are not sure about x86 side. And who can help us to take this at this point with...
So Art is fine with it. It's definitely in my inbox, and I was ignoring it. Ask Ross to talk to an IRC, but not before end of next week. I'm traveling all week.
Okay. So at the beginning of October.
Yes.
Okay.
So you just should poke me on IRC and remind me to look at it, and I'll go through it. I was definitely on CC, but
I can also.
Yes, you tried this.
You can actually.
I should be okay.
Okay.
So I can look at it, but I'm on a business trip till Thursday next week. Next Friday I'm not.
Okay, so I understand. Okay, so it is in general the trend and tricks stuff is in your domain, as I understand. So TXT stuff is more or less.
We have no clear separation. I mean, it's more. Dave Hansen is more a memory management.
So when I do a presenter,
Borislav. No,
I can do a take presenter.
The general
and then when I share the screen, because I have a demo, live demo, so I do a share screen.
I'm running all the interrupts and
share, and it detects actually
TSC,
okay,
8cat, and all these crap.
It's not shown
so it's
there.
more, but we look at the things together.
Okay.
So you might.
Not shown there on the screen.
Told Dave Hansen about the TXT stuff.
Okay, I will talk.
He's here.
Yes. Okay, so I think that we have a plan.
Yeah.
And we are in touch.
Yeah, sorry for informing, because there was an email you can do demos, so I depended on that. So
yeah, you can, but you can, but you talk to people in the rack and
He wanted to. Oh gosh. Okay, I hope that.
Because yeah, you should be able to share your screen.
my apologies, really, I thought that this is reliable, and I thought it would be easy peasy.
Yeah, right. But you should be able to share your screen, but it's not working. But if you go to the slides, can you still show the slides from this laptop?
Oh, okay, yeah, good question.
mitigation. So it turns out it applies to both native and to equals.
Instead of sharing the screen, just try to pick up everything slider here, and then let's see if it's feasible. I don't have to go here. So you can go back to the back that is showing up. Yeah, it is showing up because I'm seeing it here. So there is a problem with screen sharing.
And technically there I'm
and I don't know how to fix it. Maybe you should and the other option, application window, whatever.
Let me try that.
So we need to go back to the screen sharing and now. Yeah, okay, that's working. Now the other option that we haven't used.
Yeah, just the terminal, that's all what I want.
Yeah, just to see if this helps. Yeah.
So it's actually showing here and not there. So
not there, yeah. So, but that's already happened before. So I'm guessing the problem is related to a mismatch in the screen resolution or something like that, which is not handled by I don't know how to fix this.
The whole thing is a demo, actually. Okay.
So that's why they wanted to, or advise people to have like a video to share, because you can share videos. If you prepare a video up front and then share it, then people will see, everything you're talking about. In this case, that's I don't know how to do this.
I use Mac for prioritize. No, there's an Emacs one for Mac. It's M8. And yes, it turns out there are some programs like this they can start using Emacs with Python instructions within the keyboard just so they can use there are genuinely people who start some sort of people. It doesn't have a stable business. So I wrote and get rebase origin master. You want double dash on. Get rebase onto where you can start somewhere on top of this branch. So a command line option double dash onto. Give it a parameter? Yes. So you say, I want to rebase from this to where I start, onto somewhere like this branch. So I do give, but okay, so I need to find the SHA hash and go to what? But that hash no longer exists. Okay, so currently, how did you create the branch? So the normal way of creating a branch is you'll create a branch and say, I have a much better don't destroy this branch.
No. Nobody can help with this.
What?
Nobody can help with this. Because the problem is only he uses it and maybe you.
I use Git, but yes, we're a small group of people.
First we have trouble with it. Yeah, because they turn there. Take the new branch. Yeah. talking about like not able to consumer things and like I don't know. Figure those out by now. You have things like EKS and then your picture would be good at that. You specify things and then cherry picks each one of them on the new and you give always off by one or I used to do it like that, and then I got confident. If the worst comes to the worst, it's all on raw. You can use B4 to back off and recreate. But yeah, get rebase. So get rebase will go to where you started and rewrite things. Starting from the same onto the start somewhere.
You just take this branch and you graft it onto the branch.
But the cherry pick one is easier for me to wrap my head around.
Cherry pick is much better because start with that. That leaves you the most options. When you graduate from novice to advanced,
I was quite worried when I'm getting these rebates and I'm not going to rewrite that.
That's what I'm saying.
So, one of the complexities, if you created a branch originally with an upstream tracking branch, then rebase will do it automatically. We'll move on to automatic. So if you did git checkout -b name origin /master then that's an upstream tracking branch. It says, I have a local branch and its upstream version is over there.
That upstream version goes away.
No, you change it.
Okay, but it's still.
Ours goes away. They rewrite it.
Oh, yes. I don't think that
maybe you should.
Yes. So you probably do have an upstream tracking branch, and they rewrite history, and that's where. In which case, yes, you do.
I've seen him around. Yeah, he was here. He had his laptop because he wanted to show something from his laptop. So he wanted to connect as a presenter here. So, and I don't want to destroy this setup here because it's going to take us years back.
Well, yeah, I'm like taking notes.
But I guess that works.
I made the same mistake.
I wanted to say that I really appreciate it. Very important. Forget about nitpicking on the names, because like I'm super excited to see it come together. Kind of like the RC and stuff.
So I used to CNC instruction. It's one line that doesn't exist anywhere else. That's usually for I want to mark several things and look at so that's for finding it in the disassembly. The other thing is pretty much you can execute it and it doesn't display even because who cares about it?
I used to use but running now. I've got one thing I almost put in. Fred's up next. Did I do my...
Did we do the ordering wrong?
I was specifically trying to fit some of the turns out that our vegetables are how much more
okay.
I can kind of come along with it. Sometimes it will be yeah, they are. I did not realize I've been running in production for 2.5 years. I'm sorry. Yeah, I that was mostly my fault. I did it as a secondary job in college, so...
Okay. We're going to go on to the next talk here in a sec. Next talk. Next talk. Okay, welcome back from break, everybody. I think it's time to introduce you to Fred. And this is not Fred.
Okay. Okay, supposed to? All right.
And just to make sure everybody can hear us on, if you can't speak up on the chat.
Testing?
I think that the muting is for that computer, I think.
Okay.
Yep.
All right, so this is this talk about is about Fred, which is basically, let's take the whole x86 exception architecture that's been around for 46 years and toss it out the window, except not really. So, right now, the x86 has a very odd mix of two separate things. One, the original interrupt descriptor table, which dates back to the 286, where it was a slight modification of what the original 8086 from 1978 did. This is what I call, but especially with the 286 modifications, this is what I call extreme CISC. And that was sort of the architectural thinking at the time, because every instruction you executed had to be fetched from external memory, which ended up taking a very long time. But you also had multiple tables in memory to do all the various protection things that was also thought to be beneficial at the time. It does have the nice aspect that it doesn't clobber a bunch of registers that you need. It does use stack as a result, but especially after the x86-64 modifications to it, the stacks, if you have to switch stacks for some reason, for example, because your current stack is no longer valid, it is not re-entrant. And for example, if you take an NMI, you don't want to assume that your current stack is valid. And you take another, and for some reason you take another NMI. Oops, you just clobbered your own frame. Then, well, this mechanism has a lot of data dependencies in it. There's a lot of reading one piece of data that then affects what you're doing with the next piece of data. So they're serialized. This cost a lot of time, so we ended up with the sysenter and syscall instructions that were introduced in the Pentium 2 and the K6 respectively. These are totally on the flip side of things. These are extreme risk instructions. They don't do any memory references at all, but they do clobber registers. They clobber general purpose registers, which means that this mechanism is completely unusable for any asynchronous events. Furthermore, at least syscall, which is what we use on the x86-64 side, it doesn't even set up a stack when you enter. But notice that the interrupt descriptor table wants a stack. So these two mechanisms combined creates problems that neither one of them alone have. So we're redoing it in kind of an in-between style, calling it Cisc Lite. There are no memory tables. There are no gaps, like where you have to run sort of in this, you're sort of in kernel mode, but you're not really. So no need for, running with the stack pointer set to user stack while you're in kernel mode. There's no need to do swap.gs, because all of that is handled atomically by, this sort of Cisc-like implementation. We do again use the stack, but we have redone the stack switching mechanism so that it's re-entrant. We keep track of a 2-bit number called the stack level, and we only change the stack if the stack level requested by a certain event is strictly larger than the currently executing stack level. Therefore, if you have the situation where you take, for whatever reason, say an NMI from inside of an NMI handler, it will notice that your stack level is the same, and therefore that you're currently operating on a busy stack, and it will not do the switch. We are in the general idea of trying to be of being re-entrant, we're trying to get rid of special registers that contain transient state. We have a lot. It's the current mechanism for a variety of reasons is not extensible, and when we have to, if we need more state than the 16 bits of error code, we have to put them in a register. Those registers are inherently volatile because if another event happens, they have to get overwritten. We can put them, but we can put them on the stack and have them too be re-entrant. So this is going back to the original concept of having one mechanism for entering and exiting the kernel, as well as entering and exiting any kind of event. Because modern operating systems, including Linux, generally want to have some common code to run on entry and exit, instead of doing this vectoring in hardware that we've been doing with IDT, we give you an entry point, and we let software do the dispatch, which is effectively what we're doing right now. When at least for interrupts, we actually have the IDT jump to a trampoline that saves the vector number and jumps to common code. And at the same time, we also have a bunch of code that's duplicated along a bunch of different paths we're just doing one copy of it. We have defined an extensible stack frame format. It is a superset of the legacy format, which otherwise basically we would have to redo PT regs, which would really not go over well, I have a feeling. But we do add some missing information there, including what type of event. It is no longer the case that, as it was back in the 8086 days, that you can tell, actually it wasn't even true then, what kind of event you're dealing with just from the vector number. So the virtualization architectures have already defined a disambiguation mechanism of that. We're extending that to events. We're also fixing some problems, including, but not limited to, the fact that IRET unblocks NMIs unconditionally. We lose n-branch state when we take an exception. We lose STI shadow state when we take an exception. And another one I didn't add was we don't restore part of RSP when we return to 16-bit user space, which led to a very ugly hack called ESP fix. I did that one. It was fun.
Another thing in the entry code to go look at if you're ever bored on a Saturday.
Oh yeah. It will hurt your eyes. So when an event happens, the CPU will push this the stack frame onto the stack. It is always 64-byte aligned. The software can request additional space on top of it, which we intend to use for call emulation. We can also eventually, if we want to use it to enable red zone in the kernel. But that is a compiled, that's obviously not compatible with running on legacy systems. But if at some point in the future, if someone is building a kernel to run on Fred systems alone, you could enable red zone. So the green fields on here are exactly the same things as on the legacy stack frame.
Worth pointing out, the error code, yes, you may get or you may not, and that's another one of the holes being fixed, because in the range from 1.0 to 1F, you can't disambiguate, for example, an interrupt hitting the alignment check vector, at which point the error code may or may not be there from hardware, but you get to run with a misaligned stack.
Yeah.
What are you doing about 32-bit error codes on AMD?
AMD, I'll have to I have to defer to David, but so the blue fields here are reserved fields, and what I would assume that they're doing is simply expanding their error code into the blue field on the bottom. Yeah.
Oh no, specifically Intel can only shove 16 bits of error code. AMD can shove 32 bits of error code. So can we just have those as not reserved, but like will be 0 on Intel so that we don't have to screw around with?
Yeah. Yes, they will be
right, but I want to
0
avoid this scenario
Intel.
where we're on Intel and then Intel says, oh, now these 16 bits that were reserved are magic value number 2, and on AMD they are the upper 16 bits of the error code.
So here's the thing. I work for Intel. I can't speak for AMD.
I'm asking you guys to collaborate.
Even if when we are collaborating, I'm not allowed to speak on their behalf.
Don't touch those error code bits, please.
So anyway, but yes,
one more question.
The location of these.
One more.
What?
One big crutch I have with the x86 exception model is the super limited number of interrupt vectors that we have. Right?
Yeah.
So especially when you have 8,000 CPUs but only 256 vectors, that's a bit small.
So
Does
to
it solve
answer
it?
both of your questions, notice that some of these fields are pretty spread out, and that there are 0 extended reserved fields next to them. You can presumably draw your own conclusions from that.
Thank you.
And it's not like with IDT where we have to extend a long list of descriptors to add more vectors. This is just stuffing numbers into a field. The event data field there is to provide additional information like CR2 instead of a transient variable. The other thing that we have an entire unused field that we initialize to 0, but we also reserve the right to add additional data on top in future to support future features. These will be opt-in features, but you should keep that when designing for the purpose of designing, you should plan for that to happen, because for all we know there could be a future event where there could be a need to put a lot more information available. Yes?
Kind of a harebrained idea. Have you guys thought about using Fred on VM-exit to push VM-exit information instead of having to define new VMCS fields?
It's an interesting idea. It's not. I mean, it's. I think this it falls a little bit under the category of we had to try very hard not to boil the ocean, but there may very well be some meaningful. We might be able to do something with it. It's an interesting idea, if nothing else.
Does Fred make supervisor shadow stacks easier?
Yes, yes, it does. And the reason why is that we have we don't just have an option for the kernel to request additional space on the regular stack. We also have a mechanism to add additional space on the shadow stack, which comes into play when we take an exception in the middle of code patching, and we have to simulate a function call, which is one of our, which is an incredibly ugly thing right now.
Can we still?
Yeah, it works, but
so, Oh, can we still continue to let's say rewrite that those are registers?
I'm sorry, what?
So that are, for example, change that are RIP to jump back to the different place.
So those are the registers. Yeah. That's the values that are saved from before the event. Because they are overwritten when you take the event.
No. Okay.
I may not understand the question, right?
How we can then back to the let's say that after the event, how we can return to the event place? Is that
Oh yes. So there are two instructions. There are two new instructions that replace IRET. They're called ERET-U and ERET-S, which return to user space and supervisor state respectively.
So that those are, let's say that instruction will restore that those are.
Yes, that's correct. Sorry if I didn't make that clear. Okay, we're apparently out of time.
Can I just ask one thing, going back to the more than 8 bits worth of vector? If a CPU vendor were to implement this, please could you make it possible to use it without interrupt remapping in the IOMMU? Just use the spare bits that there are in the MSI message?
Crazy talk.
Comment noted.
Can I close this or? It's okay. I make presenter, so it should be okay. So, welcome everyone. So, regarding this talk, this is a continuation of last year's talk. I was in the Plumbers referee track last year and presenting the CPU ID database project and the rationale behind it. So, in interest of saving time, I will not repeat the rationale in complete, but a summary of it is that the x86 architecture over its history has actually above 750 bits of CPU ID bits. And these bits are vendor dependent, and there is also a lot of historical details there. And historically, this was in the Linux just some header files, as well as in Zen. And there was also a need to consolidate all of that, both for security updates and for better tracking, and also to minimize bugs, because throughout history there was also mistakes in bit interpretation and so on. I would like to show a demo, so to share my screen to show what the x86 CPU ID database project about and how to move from there. The screen. So we tried it actually in the hack room and it worked. I hope it works here as well. So oh, so we tried it. Okay. So yeah, I asked actually with James, and it worked in the hack rooms. I will try. Let's just wait 1 second then. Yeah. Okay. Otherwise, I will just go on, sadly, just speaking, and then we can move from there. So. Yeah, so then it's okay. So I will actually share the slides, and I will then just talk about things. Okay, doke. So sadly, I will talk, but I hope that people will follow. So in place of the demo now. So what's actually the x86 CPU ID database project? It is a collection of XML files of all the CPU ID bits that are known so far, including all the security relevant bits. And we take these XML files and we generate, and we have a multiple transformers to generate data in multiple formats. One of them, for example, is a CSV file. And in that CSV file, we use it for the kernel KCPU ID utility. So this was the first use case. Did anyone use KCPU ID in the Linux kernel tree? I know that Susie used it, and Boris probably as well. So, and yeah, so, and the KCPU ID tool basically runs the CPU ID instruction, and it parses all the registers, and then it shows all the features on the CPU. And yeah, there was a tool recently, multiple years ago in the Linux kernel, and there was a CSV file with all the fields about all the CPU ID bits. And this was around 300 or so. And now that we have the x86 CPU ID database project, so at the first demo, we said, okay, we will replace that CSV file with a full details of all the fields. And this was actually merged 2 days ago mainline. And now we have a database of more than 750 bits of all the CPU ID bits going there. This was, of course, also a first use case, but we have more use case after that. So right now also, if people submit patches on to the x86 subsystem, what happens is that if there is a new bit, the maintainer will ask you that please submit the new bit information to the XCPU ID database project before actually getting the patch merged to the x86 tree. And Thomas actually has already sent some requests to people to merge, to actually first submit these bits to the x86 CPU ID database project before getting the patches merged. Yeah.
The onus on Intel and AMD to update the database instead of the people that want to enable a feature in Linux? Please.
Sorry, so quick.
Can we make Intel and AMD put the onus on them to get the database updated instead of having it be on random kernel developers that just want to enable a feature?
Yeah. So, yeah, Boris, you want to say? Yeah. So, Linutronic, yeah, we are owned by Intel in the last 2 years. We already implemented all the bits for both Intel and AMD. So this is not like a partial, sadly I wanted to show that in the demo, but...
There, like the day that the SDM goes public, I mean, just like in general.
When something goes public, or if it's not in there, you go yell at Intel or you go yell at AMD of like, hey, it's in the SDM, but it's not yet here, versus, because what I don't want to run into from the KVM side especially, it's a pass-through feature bit. The kernel doesn't care about it. It's just something we want to reflect into the guest. No one adds it until someone wants to virtualize in KVM, and then it's like some random KVM developer gets asked to go up the CPU ID database, and it's like, oh.
One problem that we've had is that we haven't defined our x86 feature bits until we've had internal kernel users for them. And often KVM has some need for it, and we don't, so we don't define it, and it's just magic otherwise. Okay. I think that's reasonable. I mean,
of the plans here was that the Thomas has just joined the room. He can explain. One of the ideas, as I understand it, was that the feature bits were automatically generated from the database. So if you want to reference code to use it in the kernel, you have to first add it to the database. And that's a way of forcing it to be in the database with hopefully a coherent description of what it does before it can actually be used.
And yeah, and if I also may add, since also Thomas just joined, now when actually even people submit KVM patches, and if there was new CPU ID bits, the x86 maintainers actually ask them to submit the bit first to the CPU ID database project.
Yeah, that's
and then
the part
get
I don't
the
want
patch
to do.
Sorry?
That's the part that I think adds friction unnecessarily.
No.
Oh, I'm not saying we shouldn't do that. I'm saying it should be...
I'm going to enforce it.
Yes, but have Intel and AMD, when they define the spec, go and add it to the database, not when some random kernel developer. That's all I'm asking for.
Yes, ideally the vendors do that, and they have people who actually have documentation and whatever, and the bits are defined way before it hits the kernel. But I really want to enforce it because the current situation is a shit show.
Say this is one of the things that Intel is actually really good at, is putting lots of process around things like this. We're going to put some project managers who are just going to salivate over this.
Question, mechanically, is this like a Git submodule? How are we enforcing that it's actually generated from the database?
So, yeah. So what happens is that, we will actually send, so what is merged right now is the KCPU ID utility. The next step, which we are actually in progress, is that all of the places in the x86 tree which parses the CPU ID bits will reference headers that are generated by the tool as a first step. But this is in the middle. Yeah, okay, Tom.
So the long-term plan is I want to get rid of all the places which parse CPU ID, except one. And we do it once. If you look into the code, it's insane. Every random driver, KVM, whoever, they all parse CPU ID over again. No, we should really go boot, read the whole lot into a data structure. I know people will complain about 3 kilobytes of memory. No, we are keeping it simple. We do it once in a central place and get rid of all this shit. Because if you go through, and I'm pretty sure I will find bugs, I found bugs before, every place which uses CPU ID directly, uses its own macros. You can't figure out what the hell the bit means they are looking at, or the value, and that's what I want to clean up with these data structures, because then it's consistent all over the place, and we can just hide CPU ID completely from the world.
And
no, there's no reason you need it.
Yes, there is. We have places in the kernel, for example, KVM self-tests and KVM unit tests also, that need to at least be able to parse CPU ID information.
Yeah.
Still invoke their own
So
CPU ID.
yeah.
Right.
So sadly,
are the bits completely identical?
So sadly, due to the technical, I was going to show a demo actually. In the tool, we have all of that in XML files, and the generation from that is totally automated.
Do the header files that you generate, you're generating header files out of these things, so you have defines. Are those defines actually reflecting genuine CPU ID information or some intermediate format like the Linux one was before?
I mean, it's of course genuine CPU ID information.
So I can just take the output of that file and basically use those defined numbers in components like KVM self-test to identify whether the CPU ID output is actually correct.
So, yeah, okay, Tom.
It generates data structures, not bit number.
Yeah.
It generates data structures with bit fields in it, and the bit field has the name of the CPU ID bit. Or if it's a more than one bit, it has the name of the whatever value it is, APIC ID. The field. So, because that makes it obvious what this is about. Right now, what we are doing, we write it into a long, and then we access bit 7. Seriously? No. That's what data structures, what really encapsulation is for. We have something which is readable. If you look at the kernel code, I used that exactly for the topology work. And if you look at the code, you can actually read it. The old code you couldn't read because it was extract bit magic bit 7 out of a random.
I see, but most of the CPU ID helpers were more like read this constant, this define, right, from some value, and that was readable.
No, we are not reading a constant from some define. What?
Yeah, mask. That defined mask and shift will define.
No, because was it before? But I found bugs in these macros, and they are stupid. If you have a bit field which says 8 bits is this value, then it's readable because you have a pointer and a member. It's readable, it expresses exactly, and you avoid the whole macro mess in one go.
So we only have 5 minutes remaining, so let me just...
I don't disagree. I would love, if you have some example code on the screen, that would be even nicer, so we can actually know what we're talking about.
Sadly, I was actually preparing a full demo. This was...
just example code to see how to use this, right?
Just look into the topology code. It's already using this.
So...
I used generated structs with the bit fields in the array.
I mostly care that we can use it outside of just the tiny kernel limbo and also in a bit in auxiliary pieces like
you can
Okay.
use it everywhere. Just because you know this is CPU ID 18 and you get the EAX and related things completely split up with the names. Yeah. Take a look at it.
Yeah. So
I wanted to say, for those who don't know the history, the reason why Linux generally eschews bit fields is because for a very long time, GCC Clang didn't exist yet. But GCC produced absolutely garbage code whenever you tried to access more than one field in a bit field. They have fixed that now.
Yeah.
It at least 10 years ago.
I can point you you evidence to the contrary?
Well, file a GCC bug report.
Assuming that would be the evidence.
Oops.
So I was curious about something related. So with confidential computing, in addition to the CPU ID bits, we also have policy information associated with which fields the hypervisor can mask and which ones they can't mask. And we document this in our PPR, which is our public thing. Is that something that you want captured in this, and is that useful to KVM?
Yeah, so what I was actually going to show in the demo again, sadly, was, yeah, not my lucky day, but it's okay. So what I was actually going to show is that we are not just the bit offsets that are in the database, we are also building a dependency model between all the bits across each other. For example, when there is, related to what you are saying, so for example, when there is a live microcode update or something like that, you want to know the entire dependency hierarchy of the CPU ID bits. In the same perspective, we are encoding a very large amount of metadata per each bit field. So it's not just a question of the bit field offsets, there is a large set including the dependencies between the bits, including extra information, and including as well the x86 feature offsets and any other dependencies. So the data model is by definition completely extensible. And yeah.
So I follow most of that other than the microcode piece, because I assume this database is architecturally defined CPU ID bits, right? That's independent of what any particular product supports, or you don't have any product information in here?
No.
Okay. So then why do we need microcode?
So, yeah, that's...
Okay.
If you get microcode and you have a new bit, you have dependency chains. I mean, one of the dependency things is, for example, the Xave stuff, where one bit depends on another bit. And if one bit goes away, you have to clear out the others. So we want to have this documented, because right now it's only documented somewhere in the code in hideous ways. So, but the metadata allows you to add this information. This is maskable by the hypervisor or not. And you can generate, again, data out of it, masks or whatever it takes, which you can then use in code. The manual translation between the horrible documentation of our x86 vendors and into code needs to die. It's horrible. And maybe the vendors start using XML for maintaining their CPU ID databases instead of PowerPoint and Excel.
So we are, yeah.
I know that they do.
So one other thing, that there is also an arbitrary description field, and I already have some plans for what to do with this, including things like this feature appeared in microcode on this date, so September 2024, things like that, because it is relevant when you are, it is relevant when several years down the line you think, hang on, when did this appear, or stuff like that. But that's ad hoc notes for future developers looking at it as much as anything else.
Okay, time's up. We have 10 minutes break. If you guys want to talk
you
about
can
this.
ask, you can
do
yeah,
that in break.
It's all good, so it worked out, so thanks a lot, by the way. No, thanks a lot. I learned my lesson. Next time I'll prepare for you, so.
I guess I need to recognize this.
Congratulations.
Oh yeah, thank you. Thanks for help along the way.
I'm paying who lives here. Oh, okay. So, hopefully 5-hour train trip if the train's still Yes, there was flooding.
Yeah.
I had to fly over.
You were going to get here when the rains were coming in. You were planning to take a channel.
Oh, it's a train. And then the rain started pitting. So I went to the airport. Trying to get a plane. And so flight got canceled.
Now I understand why you told us this one time. Second time. The first time was just stopping here. It's the first time I actually had to walk. It's nice. I don't know how much the area where it is.
Everything's like outside. Yeah, you can go into the city. You have time.
What we have done for the first thing is we're
going that we're then we get back.
Oh, yeah.
Yeah, but tomorrow is just traveling, and our train doesn't leave until 2. So I'll have one in the morning where I just a little bit of time.
Microsoft. So yeah, I mean, and I sort of switched
Java was like, don't worry about the train, now look at everything, so we're just assuming, we don't even know if it's not going to take us this far.
It's down.
Exactly.
I need to know
and when you're doing that,
Not to get on, but they might check. So we
Which train? The train to Brno? Oh, you mean like when you enter? The same.
we use the physical API
They might check.
rather than
There's nobody on the door.
because if we use the logical
And if they check, it's like
$100.
$100.
So this is only useful for physical API.
So the problem is the IO page you can't see the field.
To Brno?
IDs and you must use it.
Oh, did he check where the train is actually traveling?
Double check on the app. Train is still listed on his, but others we're trying to book at the same time. They said it's not showing it. So I don't know if it's showing.
Okay, so Vienna main station, Brno. And you're traveling tomorrow? What time?
2:45. So say we use this we define a extension for this, just document it and input it in somewhere and how it works.
And the reason you don't want to
You don't want to interrupt it now because there's no section, even on each other's file path. Because
Find it?
239 is
Yeah.
One stop?
We're like an get on, but we gave it a different name and all it did was
It's all okay. IC means intercity, so it's
I mean, not ideal because there are bits there. Why make us a mess? But okay.
That's intercity. It's German.
That would be good. What we have on Intel.
But you probably need to check it. He needs to check it a couple of hours.
Offering DMA remapping, no, we absolutely do not want that.
Yeah, if you want to check it, go to bond.d,
I cannot remember.
We would consider that a bug. You only have to squint at Windows. I was shocked when that's what
you need to check when it starts. HBF means the main in German.
That is actually a really good way of putting it.
I'll remember that. Maybe I'll copy it. I have to refresh
Well, and with Fred, this becomes much
No, you should
You should be able to encode all vectors directly.
HLN main station in
Why do you do more bits?
If you use, I need more bits because the guest has more. I don't need more bits. There was a very strong hint that there will be more bits.
Yes, that's what I'm hearing. Okay.
And if you do that, put them directly in the MSI message, do not let these threatened with more bits. Please don't make the same mistake that you made when they were more bits.
Directly in the message. Don't require the interrupt mapping because
the IOA can help you with this.
It's still there?
And they're shuffled around in a weird way, but they really are a bunch of multi-chip
No price information.
I think I got it.
So maybe that's what people were saying. They couldn't buy the tickets anymore. This one, I guess, maybe you could.
I guess no price information available means you need to buy from there.
Okay.
This needs to register.
Not supported on you have to use
Everyone keeps forgetting. There's so few people who care about Windows VMs that doesn't come into the conversation very much.
HBF, what is that?
Help bundle.
When I saw that,
I can bring it up.
I think I know.
They have their own. Alright.
I fell asleep almost.
I saw you like this. I thought you were thinking about something.
Because what we're fighting about?
Yeah. Having fun.
Okay.
Safe travels. Yeah, heading over there tomorrow.
Yeah.
Hi, Portuguese?
Okay, everybody, we're going to get going for the next session here. We've got a remote presenter on this one, so let's everybody sit down.
Oh, with the plus?
No, we've got Chang is presenting Xave, so session 7. Oh, wait a minute, we didn't. Oh, we got to take presenter back.
Oh,
that was the trick.
Okay.
Session 7 and Okay, Chang, I think you have control, and I think you're there. So if you want to start.
Yep. Thank you. Hi. I'm from Chang. I'm from Intel. Today I'm going to talk about the AMX. I'm going to describe first what is a Xave, and then provide some short review, and then closing with some discussion about the alternative. This is a kind of survey talk, so I want to build up a case to find some alternative claim here. Let's go. First, what is Xave, and then how Linux adapts this architecture, and how Xave itself evolved over the time. So this Xave is kind of an instruction set to save and restore a set of a register state. It has a predecessor, I think, Xave, which is a very feature specific. I think the idea people get to invent this is, instead of adding a bunch of instruction to specific to the feature, they think Xave can provide us some generic way to save and restore instruction. I'm sorry, save restore register states. This approach is kind of monolithically save entire set of a register at once. So it looked like a little bit conflict from today's point of view. I'll go more detail. It has a particular memory format, which is extension from the format that is used from the Xave, but it's a kind of redefine the format to address and host all the new register set. This usage is primarily intended for the context switch, though, but this usage was adapted to the as part of ABI. There's some history. I was able to look at that. So initially, when people pushed this Xave feature, there was lots of discussion about the format, how to define the format, how to extend the signal frame. So oddly, software-defined format was firstly suggested, which then needs some descriptor as a form to provide some size and offset information of each register set. But then people realized that that information can be retrieved from CPU ID. And also, there's with the fact that this offset and this layout is kind of fixed, it was determined this how to define the format. Xave format is as defined as a part of ABI, which is now kind of ugly from today's usage. I'll go in second part discussing further. But before, I will briefly summarize how it incrementally changed over the time. So it tried to save memory right in two regards. First, when the state is identified being remaining initialized, then it skipped the memory write. And also when there's a back-to-back uses a single buffer from restore to saving, and some particular state is identified as non-modify, then skip also saving right to the memory. The other aspect of improvement was saving area. One is, so formerly the original format was kind of a standard format, which is you have to reserve the features and its area regardless of its enablement. Even if you disable the feature by kernel, but you have to reserve that space. But new compaction format is defined to remove those reserved area. If you say disable feature A, then the area for the A is gone, so that you can save space. The other approach you recently make available is for the AMX in kind of a larger state. So instead of allocate large chunk of the memory for all, it kind of gradually reallocate the large buffer depending on its usage, which is backed by the mechanism to detect its usage. So in this slide, I was trying to summarize the history of merges from two aspects. On the left side column shows the years of those incremental changes on Xave architecture itself. On the right side, it shows, I think, a feature adaptation. It started from computation states and then to various states. I try to categorize the different colors. And then as you can see, orange color indicates some security feature and something else. The idea I can get is these features are so different as time goes on, and then it's kind of packed together as part of a monolithic approach, while this mechanism to save and restore those features or states being the same. That, I think, potentially conflict to today's feature usage model. So second part here, want to talk a little bit more as part of a retrospective of this architecture to try to answer those questions, how well this approach, whether it's just effective, particularly for ABI, whether it's really well scalable, and briefly touching on the optimization part. I heard that they've really explained what's the detail on the protection key here, but I just want to make a case against this monolithic approach. I know it's a goofy thing, but basically this protection key needs to keep the valid states all the time, but the rest of extended register are all restored right before the back to the user space. So I saw there's some revision to come along with the Xave buffer, but recently this feature save and restore approach was completely decoupled from the Xave and its buffer. I think it's possible because the feature provide instructions to save and restore, but I think that's a kind of oddity against this monolithic approach of Xave. The other case I could find was that of a supervisor state. These state that particular kernel needs to update while the task is run away, switch it off. I mean, with the compaction and along with the dynamic state like AMX, it really becomes complex to retrieve a state information out of the buffer. It's still doable, but it's costly. There are two cases. PSID originally thought it needs to, but it turns out not the big case, meaning there's no need for retrieval. But for the CT case, I saw Thomas suggest to, instead of retrieving the state information from the outer buffer, it was recommended to, I think it's a workaround to restoring all the register states and then modifying from there. So from those two cases, I think the cadence of restoring sometimes mismatch. It's not that, although I think a monolithic approach is not always a win, I guess. And also, speaking of a buffer, it becomes more complex. It's really not so simple to retrieve the information in the buffer. So it's there's some inefficiency there. Now let me talk about these ABI. I think this ABI is kind of embracing the Xave standard format, that is non-compacted format, but that format conflict with emerging of AMX use. So AMX is particularly larger states like 8K, but its usage is so dynamic. It's not all user thread is going to use this state. So it's a very inefficient to follow this standard format, enforcing to put all the states in the single frame. So the mitigation that was established for enabling this feature was kind of conditional expansion over the single frame. So AMX usage model is established as permission-based. So kernel can know exactly when the state is going to be used at an individual thread. It can distinguish in the individual thread whether AMX is used or not. So kernel can then selectively expand these signal for that's mitigation. But stepping back and then looking at this ABI as hardware defined is a little bit pessimistic because it is expensive to incorporate this detection-based expansion. Anyways, that I think we can discuss at the end about the alternative. Speaking of optimization, I think modify optimization requires this. Okay. Okay, I see. Okay, modify optimization requires some consecutive restoring and saving, and it's specific to a single buffer. So think then it enforces kind of a monolithic approach further. So let me close this by answering whether we need to consider alternative or not. I think possible about that. I mean, we need to find. I think it's a time to find some alternative. Against monolithic approach, I think some disaggregated approach might be needed, considering some features of so diverse usage model. And then also saving all at once in the buffer, we can reconsider that. I think maybe break down the pieces into different set of a buffer, saying especially for the dynamically used states or for differentiating the supervisor states versus the user state. And ABI, I think instead of how to define the format as using the non-compacted, instead of that, we might consider some software defined and then optimization. I don't have a clear idea, but since it enforcing the monolithic uses, so we may elevate this optimization approach. But before talking all how to achieve this, and I think about this alternative, I think at least minimum architectural changes somewhat needed. I think at least I expect some flexibility to save, restore individual state independently, so that then kernel is allowed to define some context layout by itself. I think that's pretty much it from me, but just want to expand the discussion about the and then build up some consensus whether Xave we need to keep still using pushing this further, or we need to find some alternative. Any thoughts? I'm sorry, I can't hear anything. Does anybody speak?
Do I need to use a different mic?
Oh, okay, I can hear right now.
You can hear?
Yes, yes.
So, I mean, would the Linux kernel be revised to use those new instructions, or things like PKRU already solved and nobody wants to touch that code?
I think
I think we'd use it, so, but I'm biased.
And kind of the same question too of, are we actually going to rewrite all the code to move away from Xave, or are we just looking at new stuff? And then the other comment was, most of this motivation is optimization. Like if we had blazingly fast single instructions or like write MSR took 5 cycles to write all of AMX state, no one would care. So it's really optimization.
There are incremental things that we can do. Like, for instance, the AMX state, what he mentioned was we allocate it dynamically, but we actually allocate AMX plus everything else in one buffer. And so the first thing that would allow us to do is not have that duplicated state. We'd have our, base Xave state, everything up through AVX512 in the task struct, or we started doing it out of line, but we do it in the main buffer, and then AVX512, or then AMX could be in a totally separate buffer without duplicated storage. I think we would do that pretty easily.
Yep.
Are you proposing that we're doing this manually without hardware support? Because if you rely on hardware support, you can't do it for existing CPUs, and then you have to maintain both.
Yes, there would be 2 different save paths if we had individual save states, for instance. Yeah, there'd be 2 paths.
The microphone is working. Sorry about that from earlier. One thing I did want to point out on the ABI that didn't get discussed is that the ABI for the uncompressed format used to be consistent between Intel and AMD, and it is not anymore. So even calling it the ABI is a vendor-dependent statement.
Yeah, that's true, especially for the offline analysis. On the online case, it's uniform, but yes, that's right. I mean, some CPU might implement some feature, whereas some vendors, the CPU doesn't implement that feature. Then there's a mismatch, even though there is you're gonna use a standard format.
Quick one.
The problem isn't whether you implement a state or not. The problem is actually that the same state is implemented at different offsets by different vendors.
Yep. Yeah, even standard format, if you don't, the CPU doesn't implement this feature A, then it's go away. So yeah, offset differs. True. So also core dump node expansion. So that's I think try to resolve that discrepancy.
Okay, thanks, Shang. Okay, everybody that's we got Pawan up again. You should have control. And thank you, everybody, for attending today. We had great discussions, some great topics, good presenters. So thanks. And I know this is the last presentation on the last day between everyone and beer. So again, thanks for coming. Thanks for all the participation in the audience. It's been great. So Pawan, can you hear us? Are you ready to go?
Yes, I'm ready to go.
Okay. Welcome back.
So, hello, everyone. So continuing from where I left, so currently the CPU mitigations, they are applied system-wide, and they affect both the trusted and untrusted applications. And for the cases where it is possible to know whether an application is trusted or not, we have an opportunity to optimize and skip the mitigations on per process basis. An admin can inform the kernel about whether an application is trusted or not, and kernel can choose to skip the mitigations for that app. This mainly requires 2 changes in the kernel. One would be a separate entry and exit path, or if there are other mitigation points, then we need to have separate paths for those as well. And the second change would be an interface to communicate that change, communicate the trust to the kernel. And that has to be done by an admin user who knows about their system and the workload, if they're trusted or not. For example, like if I've written an application myself, I know I'm not trying to attack the kernel, and I would not want that application to have performance loss because it's not it's not untrusted. So for that, I sent a RFC yesterday that does the selective mitigation. So it skips the mitigations for the trusted applications. And there are separate entry and exit paths for the system call. So it uses C groups to convey the trust level of an application. So there is a new attribute that was added in the C groups. It's called CPU.skip mitigation. And if an admin thinks that, okay, this application is trusted, so it just puts it in a C group and then sets this attribute.
Excuse me, question from the room. So trusted, untrusted isn't in the confidential computing sense, right? Because I think that was confusing to me earlier. So
It is not in that like confidential computing sense. But then this can be extended.
Is there a chance to change the name?
And then
I think this was
we can change it.
Yeah, names are not important here. Concept is.
Yeah.
Go ahead and keep going.
Yeah. So there can be a user space trust authority, like which knows that probably by verifying the signatures or something like that, and then puts that application in that C group. This can be manually done as well by an admin, or this can be automated as well. If the user space has confidence that, okay, so this application is trusted. This can be done using LSMs or any other like Xatters or any other way of communicating trust. I chose to do it with C groups because it gives us the inherent benefit of using core scheduling. And what that brings is the trusted and untrusted processes, they can run on separate cores. So like we are already separating the untrusted application to a separate core. So and we're doing the mitigations for them. And the trusted applications can run on a separate core, and they have a benefit that there is no untrusted process running on the same core at the same time. So this basically enhances a little bit security as well. The other benefit of using C groups and core scheduling is that we don't have to switch between trusted and untrusted apps if you use core scheduling. If the core already has all the trusted applications, we don't have to write the MSR to switch the entry points or make any other changes.
Question, is this specifically for the kernel trusting user space and not wanting to deploy mitigations against user space attacks, or are you also looking at user space to user space?
Currently, it is only about like user space attacking the kernel and kernel trying to protect itself. I haven't thought about extending it to user space. I think that should be the next step, but I don't know like how is that possible. Maybe it is. Yeah, we can surely talk about that on LKML. But yeah, that's the next possible change that we can do.
But don't you have to consider that in the initial design? Because if you say two things are trusted, but they are not trusting of each other, you have to mitigate against switching from A to B, but not necessarily A into the kernel and B into the kernel.
That makes sense, yes. So if an application is trusted not to attack the kernel, it should be trusted to not attack the other user as well.
That does not hold true. Because you could have no secrets in the kernel and you don't care if the kernel gets attacked, but you may have secrets in the user space, and so there are different boundaries there.
Yeah, I do think it's arguable. So I think certainly we could think of this skip mitigations as being something that happens for potentially every vulnerability or potentially every class of vulnerabilities, like we talked about earlier. So I think of this less as like the mechanism and more like the question here is more. Would we like to be able to do this in a group of processes? If we're going to group them, is C groups the right mechanism to group them? Like, does that sound like the right place that people would want this done? Rather than like, would we want an all on or all off kind of switch? Because I think you're exactly right. We can't do this in a all the mitigations are on or all the mitigations are off for the C group. It probably isn't fine-grained enough.
Yeah, and I guess what I'm pointing out is if you try and do it in C groups, you don't allow the user space application to express its desires. And you also, and it bleeds in because if you disable everything because you trust the user spaces, then they may be implicit relying on those mitigations to protect themselves.
Oh, you're thinking the problem would be like if you turned off the mitigations in C groups, and then the application expressed a desire with one of the explicit ABIs to go turn the mitigations back on, that there would be a conflict?
Or the user space was just expecting that it would benefit from the mitigations the kernel deployed to protect it against other user space applications running on the same core. Or because then you also have policy built into if you switch applications on a core, if you're doing SMT sibling scheduling, then you would have to have a policy to then turn off to do mitigation. I think you have to consider everything before you deploy one part of it. Otherwise, you're going to have whack-a-mole and just a spaghetti.
Right, so if a user space application can compromise kernel, isn't it like it can compromise the whole system? So that makes me think that if an application is trusted to not attack the kernel, it is safe for the entire system. That would be my thinking, but I could be wrong. Yeah, so any thoughts on what else we can use instead of C groups that would be a better choice?
No. I'm just saying think about the user space desires too, not just the kernel desires.
Okay, all right.
Yeah, I mean, it is a good point. Like, what would you, you're right, is this protection, like, let's say you turned it off. Let's say you turned it on. Or, I'm sorry, let's say you turned the mitigations and you said, skip mitigations in the C group. Do you skip mitigations among user to user in that C group? Do you do it across? Yeah, lots of questions there. Yeah, that's a good point. Because you could say, is it skipping mitigations just among, like, keeping it from attacking itself or worried about attacking another C group, for example? Go ahead, Pawan, keep going.
So,
about 5 more minutes.
That's actually the main thing that I want to get the feedback on. The other thing are less important, but then we should still go through them. So for a normal user who doesn't understand these vulnerabilities and mitigations, it's hard for them to decide whether to keep the mitigations on or off. So currently what we have is there's two options. Either we can turn off globally or we can turn on and take the performance hit. Sure, we do have option to turn each mitigation on and off, but then a user who doesn't know about those vulnerabilities is not in the right position to take that decision. So what we can do about it, yeah.
So I was just going to ask another question. This is maybe a little bit different, but it looked like in the RFC you posted, you were focused on the syscall entry path. Have you thought at all about how this can be done for like return thunks or indirect thunks? Because there's a lot of performance there.
Correct, but then it involves like patching the kernel. like if you want to replace the return terms, it has to replace all the return terms in the entire kernel. That's a costly operation, and we don't want to do it on every context switch.
I think there are
That's why
other ways.
they would not.
Yeah, I think there might be other things you can do, although they'd involve some nasty page table stuff. But I would strongly encourage you to think about it, because I think otherwise this isn't going to provide enough value, at least on certain architectures.
So I think you're saying the stuff that we patch in at boot time is where you feel like a bunch of the problems will be, and we can't turn them off easily once we've committed to them, as it stands.
You don't want to use SafeRed if you don't have to.
Sorry,
I mean, there might be something you can split the kernel page table, and then you can have a special page that has stuff that's different for the two, which sounds super easy.
So have 2 copies of all the sites that you want to patch, and then switch between those?
Yeah, this is Peter's smiling in the room. We've talked about some things like this, but yeah, it would not be trivial, and it would be not fun. I think Linus has voiced his violent dislike for those concepts.
So if we were to have, say, separate kernel and user page tables, this would be feasible, but nah.
Yeah, so Peter's suggesting what kind of hardware change might be required to make this easier to do in software. As everyone looks at the hardware vendors in the room.
All right, I don't know, like if we can do anything in the hardware.
I have
to go back to the CPU architects.
A question for maybe I can also start a nice fight before the beer time comes. So going back to the question of like what the alternatives to C groups, I think Google's kernel has wonderful hacks for like communicating trust, and I think they include PR, CTL, clone flags, and procfs file systems. And I don't really have an opinion on this, but I'm saying that maybe I provoke someone to express some opinions.
So the policy has to be embedded somewhere, and I think C groups is a good enough abstraction just because it can be done on the command line by systemd or some admin somehow. Going into PRCTL, etc., is just patching a whole bunch of stuff written already. C groups also seems like a reasonable abstraction because within the C group you can have multiple processes, and you can say, yeah, all of them trust each other. Just disable everything for these.
I'd like to ask, are the mitigations required if the user is only user on the machine, but if he runs JavaScript in a web browser?
If a user, okay, so in that case, we don't want to make the browser as a trusted entity because it can run an untrusted code. So anything that can run an untrusted code on behalf of an attacker, so that should not be trusted at all.
Yeah, so, and is it possible to set it up so that only the browser gets the mitigations? Such as, for example, the compiler doesn't need to have mitigations because the user is compiling his own code. You put it in a secret. Yeah.
So, I don't know if I understood your question correctly. So
the answer to the question is that you have C groups per task, per process, and you would put your browser into a C group that has much more restrictive mitigations than your compiler that's just building the kernel.
Yeah, and the other problem is like interpreters like Python, Perl, they can be trusted, but the code that they run is not, like they could be running an attacker controlled script that may try to influence the branches in the kernel. So anything that can run an untrusted code on somebody else's behalf should not be trusted.
If for say the example of like a Python interpreter, just trying to think where this is most applicable, because if you can potentially run some untrusted code in a Python interpreter, I think these side channels are the least of your worries, right? Yeah. Yeah, sure.
Take for example a branch history injection. So branch history injection should be possible with a Python script.
Yeah, I agree, but also, I mean, what would you anything you want to do potentially with the Python script, kind of depending on privileges.
You can't write C group files with branch history injection, I think is the key link, right?
Oh, I was mainly thinking, well, what if I just steal cookies from your browser database with the Python script? That's probably easier to do and more useful. Yeah. Not hard enough. It doesn't prove anything. That's fair.
Okay. Well, I think the questions are wrapping up in the room. Anything on the chat or any last questions in the room? Otherwise, we're getting to the end.
Beer.
Yeah, Peter's yelling beer. Okay. Well, thank you very much for everybody who participated today. All the questions were great, and I think it's beer time. Thanks.
Thank you.
What?
Drink.
I've actually gotten
it was
with the colored bag.
Being drunk.